So, hello everyone, and welcome to the first Great Lakes Graphics Workshop. I'm very excited to have you all here. I'm Itai, a postdoctoral researcher at the 3D Lab here at the University of Chicago, working with Professor Rana Hanukkah. And I want to share a personal note. About a year ago, I approached Rana and told her, let's organize a workshop at one of the upcoming major conferences. And she said, why go outside and why go to a major conference? Let's do an in-house one with a small-scale one. And after lots of emails and coordination, I'm very excited and happy that the workshop takes place. Okay, so why are we here? What is the workshop purpose? This workshop is meant to be meant to bring researchers across the Great Lakes graphics in order to present their recent cutting-edge findings in computer graphics. And today is not all about research. This workshop is also meant to strengthen the connections between the local graphics community so that we can have insightful discussion and explore innovative ideas together. And importantly, the idea is that we meet in a friendly and accessible atmosphere, so we'll know what each one is working on. We may find ideas for collaboration together. And think about it, we are all working on more or less the same field and located geographically close to each other. So I encourage you to take advantage of this unique opportunity and get to know at least 3 new people today. Who is here? We have representatives from no less than 7 academic institutes. The University of Toronto, Carnegie Mellon University, Washington University in St. Louis, Notre Dame University, the University of Illinois, Urbana-Champaign, Toyota Technological Institute at Chicago, and the University of Chicago. This is a very respectful list, no doubt about that. So what are we going to have today? We're going to hear exciting talks about 4 topics: representation, reconstruction, generative model, and emerging research directions. Each talk is meant to be 15 minutes long, with 3 minutes for Q&A after the talk, and I encourage you to ask questions. Between the sessions, we'll have 2 coffee breaks and a long break to enjoy lunch and engage with each other. We'll conclude with closing remarks, and then we have a surprise for you. We have an optional walking tour around the beautiful campus of the University of Chicago, which will be led by our PhD students from our lab, Richard Liu and Daily Cater. I encourage you to come join us. And then we'll have some more time to socialize with peers, and note that the workshop includes breakfast and lunch. The dinner is on your own. And there are great places to get grab dinner in Chicago. Richard curated several great places for you. What are the talks are going to be about? The talks cover a wide range of topics in computer graphics, including generative models, neural representations, simulation, optimization, physics, and much more. And I did a word cloud from the presentation titles where the word is presented larger, where it appears with higher frequency, and according to this, we are most interested in interactive 3D scene reconstruction, which seems like a fascinating topic to me and a great title for a paper. Okay, we also have another surprise. At the end of the workshop, we have a present that we'll hand out, which is very common to graphics gathering. Care to guess what it is? Okay, maybe. we'll use a diffusion model at the end of the workshop to diffuse these noise out and see what we have. Okay, I would like to express my deep gratitude to the University of Chicago for hosting and sponsoring the event, which what enabled the event to take place. I want to thank the organizers, Richard Liu, which is a PhD student. Raise your hand, Richard. Oh. Which is a PhD student at the 3D Lab. I want to thank him for, like I said, curating this amazing list of restaurants and cool stuff to do around Chicago, and for taking care of the recordings, and also for the tour that he'll do. I want to take Dale. Dale, raise your hand. For taking care of the present that we'll hand out at the end of the workshop, and also for the tour that he'll do. I want to thank Naman. Naman, where are you? for designing the amazingly beautiful logo of the conference and helping with and his help with the website, the workshop website. I want to thank Brian, which is Brian Kim, which is a graduate student at the 3D Lab, but unfortunately he couldn't be here due to visa issues. Hopefully next year he'll be here. And I want to thank Rana Hanukkah, which is an assistant professor here at the University of Chicago and the director of the 3D Lab, for orchestrating the staff from the university and helping with the workshop. The invaluable contribution of each of the organizers helped a lot in shaping the workshop and enriching it. Here is Rana. Great, and I want to thank you so much for making the effort and coming here. I appreciate it very, very much. I encourage you, like I said, to ask questions after the talks and actively engage with each other to get the most out of the day. So I wish us an enjoyable and fruitful workshop, and thank you for coming.
Thanks everyone for coming, and most importantly, thanks Itai for doing all the organization, because basically I just said we should do this thing, but he did all the hard work. So yeah, thanks Itai for putting everything together, and thanks everyone for coming. Yeah.
Okay, and now without further ado, let's move to the first session about representation, which will be moderated by Anand.
All right, so the first talk of the representation session will be from Anand Bhattad, a research assistant professor at Toyota Technological Institute at Chicago. He will be presenting emergent late intrinsic representations for scene relighting. Let's give the stage to Anand.
Did you give them the? Okay, the clicker too. We can find it here.
Alright,
You have your clicker?
Yeah.
Sweet.
Very good. Very good. Thank you.
That's the thing. Yeah.
Alright, good morning everyone. Thanks for coming. I'm Anand Bhattad. I am a research assistant professor at Itai, Chicago. Today I'm going to talk about latent representations for scene relighting. So the task that we are interested in is single image scene relighting. Let's say we have a single image like this, and our goal is to realistically change lighting given this single image. So let's say, for example, given this nighttime image, you want to turn off the lamp and the light you want to come from is only from a window. Or you want to switch on the far side lamp. Or maybe you want to adjust the light that is coming from the window. And this problem is hard for several reasons, and we want to learn good scene representations for this. The main problem that we want to deal with is we want to disentangle scene intrinsics, that is independent of lighting, like material shape and illumination. And this is in fact an ill-posed problem because same pixel value can result from various different combinations of material shape and lighting. And there are other challenges, like we want to understand where the light sources are, whether there is this lamp or windows. And we also want to understand the spatial layout and arrangement of the scene because the shadows, interreflection that we see is dependent on the scene geometry and layout. And finally, we want to model light surface interaction because different surface interacts differently with light, so we want to do this. And on top of that, we want to do this without using any labeled or computer graphics data. So let's take a step back and try to understand from first principle. We know that images are 2D projections of 3D world. So this is a simple cartoon image. There are 4 shapes from rendered. There is a cyan cone, a red cylinder, yellow sphere, and another sphere. Now imagine we have a camera and there's a spotlight that is going to cast light on these objects, and we take a snapshot and we get something like this. Right? So what we see is a grid of 2D RGB pixels, but what we perceive as humans is 3D shape, appearance, and arrangement in space. So what I just showed you is a simple concept of rendering in computer graphics, and if you abstract this, we have this 3D scene parameters, materials, lighting, camera, geometry, goes through a forward rendering process to give an RGB image. I come from a computer vision background, and one of the goals in computer vision is to recover this 3D scene parameters from a single image. And this process is called inverse rendering. As you can imagine, given just from a single image, it is significantly hard to recover all these 3D scene parameters. Objects may be occluded, the light source may not be visible. So in 1978, Barrow and Tenenbaum came up with a 2D approximation of this problem. They called it intrinsic images, where instead of materials, we estimate something called albedo or reflectance that is completely independent of lighting. You can see the ambient color of each object, red cylinder, cyan cone, and yellow sphere, and so on. And then we have shading that is completely dependent on lighting. All the shadows, interreflections that we see is modeled in the shading. Now, instead of measuring where camera is, we measure depth, that is how far away each pixels are from the camera. And then instead of measuring complete geometry, we measure surface curvature or surface normals. Now, prior work has studied this problem from various perspectives. One that stood out was this concept of physically motivated rendering, where given an input RGB image, we first inverse render all these intrinsic images, and then we have a rendering process to give us RGB image back. And these days, most often or not, all this inverse rendering and rendering is replaced by neural renderers. There is fantastic thesis by Genjin Lee from UCSD who did substantial work on this, like collecting data set, building early models to have this neural rendering get going. And most of our recent approaches is about fine-tuning diffusion models using, let's say, label synthetic data set. This is a very cool work, RGBX from SIGGRAPH 24, where given this input image, you recover intrinsic images in between that you see, albedo, normal. I talked about shading, but you could have other components like roughness, metallicity, or irradiance. And then you use a diffusion model, a pre-trained diffusion model, fine-tune it to get the synthesized image. And this is trained with a large synthetic data set collected from various synthetically rendered sources. and then fine tune to. Other popular approaches, most of you might be familiar with IC like V2. This is from ICLR 2025, trained over 10 million images from various sources, real photos captured with camera rigs, light stages, again rendered synthetic images, and also they come up with very nice synthetic illumination augmentations. But as you can see, one thing that is common over here is that all this method assume this intermediate representation must be human-defined intrinsic-like images or intrinsic-like maps. But why they have to be images? Is it necessary, or can we have some alternative approach? Why? Because in our earlier previous work, we found that in all these powerful generative models, we can find latent encodings of intrinsic images and lighting. So here we recovered all this normals, depth, shade, albedo, and shading. On the right, you see is a video of latent encodings of lighting. So we want to come up with an alternative approach where we can treat these intrinsic concepts as latent variables. So we train a very simple model, a latent factorization model to relight. Here is the setup. Given two images, same scene under two different lighting conditions, we extract two different feature maps. One we call a low dimensional lighting like vectors, and the another we call it intrinsic feature maps. It's a dense feature map. And we do this same thing for the bottom image that you see. Again, we extract the low dimensional lighting like vectors and intrinsic feature maps. And they both come from the same network, so they share parameters. Now we combine latent lighting vector from the top image and intrinsic feature map from the bottom image and decode to give us image. Now you can see that since we are trying to match lighting of the top image, the resulting image should have image that looks something like a top image. So you can have a loss, like a simple regression reconstruction loss. And then you also have some equivariant loss where you want to encourage this intrinsic feature map, what we assume to be light independent, to have similar features irrespective of which images they come from. Now, after we train this, one thing to note here is that we are using same scene under two different lighting conditions. But at test time, what we found is that after we train it, it really doesn't matter if these two images come from the same scene or not. We can have completely two different scenes, and we still are able to get realistic relight out of it. So in the top row, you see that there is a tire and some objects set up on it, and the other is a close capture of the kitchen. Now you would notice that these images are related plausibly. So let's zoom in a bit and try to see. So if you notice at the spherical balls, you would see that the light in the first image is faint, coming from the right, and in the middle you would see that the light is coming from the top, somewhere behind the camera. And in the relit you also see that there is a shiny nice point that is kind of equivalent to what you see in the middle image. And not just for the simple setups that I showed you, it also works for some complex indoor scenes like bedroom images. In the bottom you have this input image, in the middle it's some bedroom-like images where the light sources are not clearly visible, but the model is able to abstract lighting and still transfer light from the target image to the input image. Now, having this setup, we can compare with actual ground truth data, and we compare with this MIT multi-illumination data set from MIT. So here in the middle, you see this RGB2X that I talked about earlier, which is trained on massive label data set, and they use generative model as a prior. And the metrics that we are using are root mean square error, so lower is better, and structural similarity, higher is better. As you can see, we get about 12% improvement in RMSE and SSIM, but just by using a simple model trained to factorize latent components of lighting and intrinsic features. This is all good, but what is more interesting is that at test time, what we observed is that imagine you cut off the connection from lighting vector. What do you think would happen? Anyone?
It will use its prior of lighting.
Right. So what we see is something, the image that looks like a reflectance map or an albedo-like map. This is an emergent property where the model has never seen any albedo-like images during training. So let's see some hard examples. These are two of my favorite examples. In the top row, you see that there is a light around the mirror, and the bottom row it's an open refrigerator. So as you can imagine, suppressing this lighting effects is significantly hard, and to enhance what is invisible is also going to be hard. Now, if we compare just by removing the lighting connection from our network, just using intrinsic feature maps, you can see that most of the lighting effects are suppressed around the mirror, as well as we can see clearly all the objects that are present in the fridge, like a red ketchup bottle or you see. And if we compare with the previous state-of-the-art method, intrinsic image diffusion from last year's CVPR, you'd see that they are unable to suppress light-dependent effects really well, even though they have been trained with massive amount of label data. Now, this is a very simple latent intrinsic concept where we train a simple autoencoder like UNet model. Now, what if we replace this decoder with the powerful image generator like stable diffusion model? What we find is that now we can do even more complex scene relighting. So, for example, here is in the first image we want to abstract lighting, and we want to extract scene geometry and material from the second image. So we want to transfer lighting from the first image to the second. So let's try to understand what's happening in terms of lighting in this both state scene. So if you notice in the first image, most of the light is coming from the window. And in the second image, the dominant light source is from the ceiling lamp. Now in order to get a plausible relight out of it, we need to turn off the lamp, and then most of the light should be coming from the window. And we use the same process, just that we replace decoder with the modern stable diffusion model. And if we do it, we get a plausible relit image. You notice that the lamps are turned off. Most of the light is coming from the window. Even the ceiling off that you see is significantly higher as compared to the original image. So the model is able to abstract the light sources, how lighting is going to be in some latent form, and it is able to get reasonable relight without using any label data set or computer graphics data set. Now, coming back in terms of numbers, how does it perform as compared to the previous latent intrinsic and RGB2X? So what we found is that if we use this generative prior, we get even significant improvements. So earlier we had about 12% and 21% improvement. Now with this just adding generative prior, I have put under the rug some details how we do it, but I would refer you to the paper. But most importantly, we are just using a pre-trained off-the-shelf generative model. And if we do that, we get like about 35% improvement in RMSE and 18% in SSI. So to summarize, what we have from previous state of the art just by using a latent representation is about 43% improvement as compared to a model that has trained with millions of labeled images annotated. Here we are not using any labeled images. What this allows us to do is to relight in the wild images. What do I mean by it? You can just browse images through internet, put it in a model. Let's say if in the first column is our target light that we want to match to the images that we have on the second column. And if we compare with RGB2X, what it does is it mostly tries to modify the color rather than the lighting. You don't see any light sources being switched on. Most of the thing that you see is the ambient, the reflectance like that. And if we use our approach, we see that it is able to identify there is a lamp over here and switch it on. And again, there is a lamp over here and switch it on. And it is able to preserve the layout geometry convincingly, and it generates possible relight. And I want to end with one favorite example of my own, which we didn't find it until we submitted the paper, and it was in the supplementary, somewhere sitting in the supplementary. So here is the image. In the first is the original image that we want to relight. On the top, you see is the target light that we want to match. So in the first image, the lighting is nighttime. And most of the light source is coming from artificial light sources. In the top row, in the top right, you see that the light is coming from the window and it's a direction light. In the relight, first we get direction light coming from the window, which is nice. But I want you to pay attention to on the TV screen. Can anyone tell what do you see?
Reflection of the window.
Sorry?
A reflection of the windowless.
The table. The table?
Oh, yeah.
Right. So that's right. So it's a reflection of the table. that you see. And this is like an again emergent property. All the second order light dependent effects seems to emerge naturally in this model. And we don't know how physically accurate these models are because we don't have 3D geometry of the scene, we don't have material properties of the scene. But in order to get this type of convincing reflection that seems to be of this top right corner of this table is quite realistic. Not sure if it is visible on the projector. There is also a reflection of this table on this fireside place. So to summarize what I just talked about is that latent intrinsic emerge if we train a simple model to relight. If we have a right kind of factorization, they automatically emerge. And this allows us to relight complex real-world indoor scenes in a completely self-supervised manner by using scenes with as few as 1,000 scenes under different lighting conditions. And we can get plausible second-order lighting effects like soft shadows and reflections. With that, I would like to thank my co-authors and happy to take any questions you may have.
Nice. Yes. I'll pass him the mic.
Thanks for the great talk. So when you said when you cut off the lighting vector, you recover the albedo.
We zero out, just zero.
So you pass zeros. So is there? Could you say a bit more on like why that happens, and does that also mean that you could recover other things in the latent space of this lighting vector?
That's a very good question, and this is something that we are interested in. Michael is here, whom I'm collaborating with student Xiao, and we are interested in this question, and we want to know if we can recover other surface properties, like even geometry properties or roughness and other things. So it's an ongoing work, and so far we don't have any evidence of it, but I believe there is underlying encoding of that representations as well, and we just need to figure out how do we impose constraints to recover.
But do you know why it's so why is it that the zero vector recovers it? Like it's not obvious to me that that would be the point in the latent space that, you know what I mean? Like is there some sort of regularization that would make it be the zero vector that recovers the albedo?
Right, I think it is the fact that how we formalize training. So here the way we formalize training is that we wanted to recover the same scene. We wanted to recover the same scene as the top right. And another constraint that we had was this intrinsic feature maps has to be the same. So this is kind of mimicking, we are trying to model light independent features in this feature map. Only light dependent features are coming from in this low dimensional vectors. So that's why you can imagine that if you cut out, only thing that you see are light independent effects. So that's why that's the plausible explanation of why we see albedo like maps out of.
Thanks.
All right, thank you again for the awesome talk. Let's give another hand for a round of applause. So the second talk of this session will be from Chenxi, who is a postdoctoral researcher at the University of Toronto, who will be talking about 2D neural fields with learned discontinuities. Let's give the stage to Chenxi.
Oh, and here's a clicker if you want to use it
Okay.
for your slides.
So
Oh, it's not working.
it's not strong enough. Anyway, okay, I don't really need a clicker. Hi, good morning. So thank you for inviting me here. My name is Chenxi. I'm a postdoc at University of Toronto, working with Alan Jacobson. So I'm going to talk about our work, 2D neural fields with learned discontinuities. So this is a project done with Siqi Wang, Matthew Fisher, Ipali Anija, and Ali Jacobson. So I'm going to talk about images. So image is a major entity for graphics and vision research.
So when we mention images, many people probably will think about raster images, but this representation has some problems. For example, a raster image has a fixed resolution, and when we zoom in, we are going to see this pixelized artifact. More formally, we can consider an image as a function. So given a position on the canvas, it returns a radiance function, radiance value. So here we consider 2D positions xy and RGB values. This function continues almost everywhere, so there are occasionally discontinuities, for example, in this 3D rendering scene. So there are sharp shadows and highlights like those, and also more complicated phenomena such as refraction and reflections. So we can see they may have complicated shapes, and the question is, how do we represent discontinuities in images? So our previous work by Belki et al. Introduces a discontinuous neural representation. Their method takes discontinuities given as a prior, typically computed as contour lines of the input 3D scenes, like those red lines over there. And it is not easy to determine the shapes of shadows, refractions, and other more complicated phenomena. And because of those missing information, their method can still have some blurs around those missing areas, as we can see here. And our method can work without those prior. So here are zoom-ins. Our method closely approximates the input with noise removed. So before we dive into details, let's review image representations that support discontinuities. In vector graphics, it is often achieved by defining the image function on top of some geometric representations. For example, as the names imply, the gradient meshes are defined on meshes, and diffusion curves are on curves. Another series of work called Mumford-Shah functional started in the late 80s. This functional is first invented to denoise images with 3 terms in its objective function. Maybe slightly hard to see, and I actually can benefit from that, but probably can not very easy to see. Mm-hmm. So the first term is a fitting term, and the second one is a smoothness term to make the continuous region kind of smooth, so to denoise. And the last one is a term controlling the length of the discontinuous edges. And this is originally constructed on pixels, so discontinuous edges have to have like 1 pixel wide thickness. So later, this is adapted to 3D meshes for denoising and at the same time recovering the sharp features. So those red lines indicating the sharp features, and so as those yellow triangles. So discontinuities are also a research topic for neural field representations. ReLU field approximates discontinuities using very steep ReLU functions. So here are some examples, and note that no matter how steep those ReLU functions are, they are still not truly discontinuous. It's just a really steep ReLU jumping like that, and meaning that they can still be blurry after zooming in enough. So a recent vision paper constructs local patches of these continuous boundaries and blends those patches together into a single image. So most related to ours is Belki's method I mentioned before. So this is a mesh-based hybrid neural field with features that are discontinuous across labeled input edges. So these features are then fed into an MLP to get a more expressive image function. So the issue is, what if we don't really know these discontinuous edges in advance? So how do we solve this problem? We follow a standard hybrid neural field framework on a triangle mesh. So we do the barocentric interpolation of per vertex features and then push it through an MLP, just the standard method. So our innovation is these per vertex features can each be discontinuous across mesh edges. So in this way, we can represent the discontinuity of magnitudes as continuous variables and optimize using the standard gradient-based framework. So let's first look into this per vertex feature definition. For each per vertex feature F hat over there, so a query position indicated by the light dot, we can define an arbitrary reference direction. and put the query position into a local coordinate ranging from 0 to 1. This is just a simple normalized counterclockwise angle. And along each edge, we can define a discontinuous feature. So as indicated by this gradient over here. So we repeat this process and define similar functions per edge. So going from T0 to T3. So those are also their coordinates within this local coordinate system. More specifically, for each edge, we define a simple linear function. So because our domain is pair-optic, we create a jump across this edge. So here's an example. We have 3 parameters per edge, so L and R, and also W, controlling the magnitude of this discontinuous jump. So if we put all edge bases together, our f hat looks like the one on the top. So below is the individual basis function. And that's not very expressive, but if we push that through an MLP, we can represent more complicated 1D functions like in this example. So we also designed to store these features on the mesh such that each edge has a consistent discontinuity. So we cannot really have discontinuous on the one end and continuous on the other end. So they will be consistent. So with our neural field defined, we can see how it is fed to the input image. We start by initializing the mesh to be roughly aligned with the input discontinuities. So we first generate the mesh using just simple canny edge and the trivial triangulation. And then we roughly align this triangle mesh with the input using a simple differentiable rasterizer. And then given this roughly aligned input, we actually fit the field. We are refining the discontinuity alignment. So here's one example. After 30 iterations, we can see there's a little bit discontinuity emerging here. And those magnitude keeps increasing. And after 100 iterations, they are more unnoticeable. But still, we can see the alignment is not really good. And after more iterations, they actually get aligned more precisely. So here's a footage just showing kind of convergence on one more complicated example. So this is the final rendering using samples per pixel of 16. So one issue is that this results in many almost continuous edges with very small jumps. In this plot, the x-axis shows the discontinuity magnitudes. So we go from almost continuous from that end all the way to very discontinuous on this end. And the y-axis indicates the edge counts. So we can see the majority of edges have near 0 magnitudes on the very left. So those over there, they're almost continuous. And keeping them leaves small artifacts in continuous areas and also takes a lot of storage. Because remember the LRW parameters we saw before, so we have to store them for those unnecessary regions. So we enforce almost continuous edges to be truly continuous with an adaptive strategy similar to the standard mesh simplification. So after that adaptive step, we can see the discontinuous edges are free of redundancy at the end. So for this example, we can see those are the discontinuity recovered. And it's kind of interesting to see around the pupil. You can actually see it's more discontinuous in the right place, and there's a kind of gradient effect. So on our test set, on average, we reduce the number of edges to 1/68 and number parameters to about 1/5. So now let's see more results. And I didn't change the title for that slide. But anyway, our method is able to approximate the inputs, and with the smoothness bias of neural field, we can denoise the input. So apart from the diffusion curve example I showed before, we also tested artistic images. So here we compare to Adobe Illustrator image trace. So it approximates the complicated input with very simple region field, causing noticeable artifacts like those over here. And our method not only represents the true discontinuity, so we can zoom in as close as we want, and also is expressive enough for this interesting input. So in this example, we test on JPEG compressed vector image. So that's the input to our method is actually the one in the middle. So it's JPEG compressed, so we can see some artifacts. So we demonstrate that our method can represent standard vector graphics image and at the same time reduce the JPEG compression artifacts. So this is the result. And we also evaluate on diffusion model generated depth maps. So this depth maps is generated given the photo on the top left over there. It's kind of hard to see, but if we lift this one to 3D, we can actually see there are a lot of floaters near the depth discontinuity as shown on the left. And after fitting using our method, we are able to remove many of those floaters. And we can take a closer look, and many of them are cleaner after using our method. We also test on natural images. So here we compare to the two patch-based discontinuous representations. So those are the two highlighted in the middle. And we show that ours gives the best approximation. Apart from the previous qualitative results, our method also outperforms a large, kind of larger set of comparison methods for a number of tasks quantitatively. And we also show a small application of blending vector solid fields. So in these two input vector images, gradient colors are posterized into solid fields. So that's maybe hard to see, but you can see there's very clear boundaries between two closely, like very close colors. So you see kind of blending effect. That's because all the colors are represented by solid fields. So after fitting our neural fields, we can manually set the threshold. So that is the one I kind of showed before, and gradually blending those solid fields together. So here we see a kind of more interesting results compared to the one on the left. Our methods also have some limitations. So first, despite our fitting process works well, it's our initialization step, it can still struggle when the mesh edges are too far away from these discontinuities. So in this example, I disable the initialization just using very misaligned mesh to fit our field, and we can see some places it's okay, but others are kind of blurry. It doesn't recover all of that. And second, this representation works like an edge-preserving filter on natural images, so the representation can be less accurate. And additionally, we simply sample at the 0.5 pixel positions and feed those to our method. And using more advanced input filtering could improve the result. And for future directions, well, his method supports curved discontinuities. Ours does not support it at the moment, so that can be an interesting future direction. And also many hybrid neural fields such as Instant NGP, they use multi-level structures. Extending our method to include those designs can also be an interesting thing for the future. So thank you for listening. I'm happy to answer questions.
Does anyone have any questions?
I don't need a mic. I think I can speak up. It's very nice work. Have you thought about extending to 3D?
That's a very good question. The thing is, for 2D, it's easier to kind of control those triangle mesh not flipping over, although it's already kind of hard because we need to do some regularizer to avoid that from flipping. But for 3D, it's not very clear what's the right structure we can define this thing on. And defining this discontinuity is not that hard because you just use a simple function. But what's the kind of underlying structure? If you do that on tap mesh, that's going to be very complicated. So that's my take.
So you're saying that it's harder to define that discontinuity. Like in 2D, you're using the cycle with a mod function. In 3D, yes, it will be challenging around, like you have to decide if it's discontinued across a face or across an edge.
Yeah, and also the underlying structure, when you optimize it, it may go into very bad kind of status. For example, you may have flipped something and just going to be a total mess, and that can be hard to resolve.
Thanks.
We have time for maybe one more question.
Thank you, Chenxi, for the great talk. I have a question. How do you feed the 2D to the image? Do you use the image information, or do you have some other supervision? So feeding the edges of the triangles to the image to find these discontinuities.
I see. So the setup is very similar to just like inverse rendering or maybe the differentiable rasterizer. So really, you're just rendering those triangles using your specific function. And then I mentioned we only sample at the 0.5 like offset pixel center. We just feed that into the function, saying, oh, for this location, you need to feed this RGB value. Very straightforward like that.
Great.
Okay. Thank you.
Thank you, Chenxi, for the.
Thank you.
Thank you, Chenxi, for the talk. Let's go to the next talk, which is by Aviad Levis, who is an assistant professor at the University of Toronto. This talk will be neural fields beyond graphics, solving inverse problems in the natural sciences. Let's give the stage over to Aviad.
It was working. Can you check that the USB is? It's in there. Sure.
Okay, thanks a lot. My name is Aviad, and I'm an assistant professor at the University of Toronto, and I'm going to talk about a slightly different topic. So I'm not going to talk about graphics, but my talk will have both neural fields and ray tracing. So it's graphic adjacent. And so I'm going to talk about how we can use neural fields beyond graphics to solve problems like the one you see on the top, which is reconstructing the image of the black hole in the center of our Milky Way galaxy. And so you guys are mostly graphics people, so you don't need the context, but just to kind of put us all on the same playing field, the context is the rise of neural fields was roughly around 2019, 2020, and it kind of came separately from two communities, right? So the vision and graphics community, it got popularized by these set of papers, and then in the fluid dynamics, people were looking at how to solve fluid dynamical problems using coordinate-based neural networks, right? And for my work, both of these are relevant because I'm observing fluid dynamical phenomena, right? So this tie between these two different notions of coordinate-based neural networks is very helpful for the type of work that I do. Now in graphics, one of the main works that made these coordinate-based neural representations really popular was NeRFs. And one key thing why did this happen is they had really nice results, and you can see the number of citations. It's been going up exponentially every year. I took this plot from a previous talk, so I'm sure this has risen in the meanwhile. And so one key reason was they had a really good acronym, right? So everybody likes the acronym NeRF, and all the subsequent works really put this in their titles. I don't know why people do it, but everybody did it. But all jokes aside, the reason I think it got so popular is because it was so simple, right? So the concept was really simple. You have this neural representation, and it takes continuous coordinates as inputs, and it outputs something like color and density, right? And then you tie this together with what they call volume rendering here, which is essentially ray tracing through the scene. Okay. And so, there's a couple of other tricks to make this work. You have to add some positional encoding, and since then there's been many improvements. Like we saw instant NGP a second ago, and people are using now Gaussian splatting. But all these improvements are mainly targeting the world of graphics, meaning they're all looking at this part, the representation. How can we represent larger scenes? How can we make this real time? How can we represent more nuanced and complex scenes, right? And this is not entirely relevant when you're looking at the scientific applications that I'm looking at. So when we're looking at these type of applications like imaging protoplanetary disks or the large structure of the entire universe, things tend to be really smooth, right? We don't really care about such complex representations. We want a simple representation. And what we care about is this part. Actually, the volume rendering is the bottleneck. So what do I mean that by the fact that this is the bottleneck? What I mean is, how does volume rendering work? In other fields, people call it radiative transfer, but how does this work for the standard NeRF approach? Well, you assign a color value and some density, and you ray trace, right? And what you have is this simple exponential decay, right? Where all these points are going to be blocking off the light that's coming from this point. And so you're going to have this Beer-Lambert kind of law, which gives you an exponential decay, which is great, but it's not very general and it doesn't work for the type of scientific problems that I'm looking at. And so essentially when you talk about volume rendering or radiative transfer, you typically assume something much more nuanced than this. You assume a steady state scalar radiative transfer of emitting absorbing media, right? That means you're not accounting for scattering, you're not accounting for refraction, you're not accounting for polarization, and you're not accounting for transient phenomena of light. Okay, and so one line of work that we had, this is work done by Brandon Zhao at Caltech, is looking at refractive neural fields, right? So in this case, actually what the NeRF is representing, or what the neural field is representing, is not the color or the density. It's the index of refraction. So it's not inducing any change to the color, but actually the path that light decides to take. And it's interesting that this is actually a good model for how gravitational lensing works on large scales, the scales of the universe. So here, for example, you see all this light coming from different galaxies, and the path that light takes gets warped. And based on that, we can use galaxies as probes of what's between us and those galaxies. And mostly what's between us and the galaxies is dark matter, right? So using these kind of techniques actually enables you to see something that you wouldn't be able to see otherwise, which is dark matter. So that's really exciting. Okay, but I'm not going to talk about this work today. I'm going to talk about this other work, where here again, light doesn't move along a straight path. We're looking at extreme space-time, which is the space-time around the black hole, right? So typically when we ray trace, we're assuming light just moves along straight paths. We take that for granted, but that's only because we're in what's called flat space-time, okay? In curved space-time, actually light moves along these things called geodesics. And again, you guys, everyone who's from graphics might be familiar with geodesics, but the most well-known geodesics are latitude and longitude, which are the geodesics on the sphere. And if you took a flight here today, you traveled along geodesics. Okay, so around the black hole, the mass is the mass of the black hole is so massive that light doesn't move along straight paths anymore. It actually moves along these geodesics, which are curved. And if you have something very bright behind the black hole, it's not going to be occluded. It's actually going to be gravitationally lensed onto the image plane. And so points of light behind the black hole are going to manifest themselves as rings around the black hole. And that's the reason why that first image that I showed, the first image of the black hole in the center of our galaxy, looks like a ring, right? So we suspect that this is the black hole shadow, and this brightness is very bright gas that's orbiting the black hole called the accretion disk. And it's actually plasma moving at relativistic speed. It's very, very hot. And that's why we gave it a hot color map, right? So there's no meaning to this orange. This is just a choice. And we wanted to convey the feeling that everything is very hot. Okay, so today I'm going to talk about how we move past this image. So this is a 2D image. And can we actually extract something about the three-dimensional structure around the black hole? And how we can do that with using NeRFs and general relativistic ray tracing. Okay, and this is joint work with Andrew, Katie, Maciek, and Pratul. Okay. Okay, so I'm going to just highlight a couple of key challenges here. Let me see, how am I on time? I'm going to highlight a couple of key challenges. Well, the first challenge is, well, we have to solve this, we have to model this using general relativistic ray tracing. And it turns out that's not easy to do fast, but there are semi-analytical solutions. So I'm not going to go into this so much, but essentially, if we know the mass and the spin of the black hole, we can efficiently compute these geodesics and figure out how to map each pixel on the image plane into a path through 3D space. And that only depends on a handful of parameters that characterize the physics of the black hole. Okay, so that's one challenge. Now the second challenge is actually the black hole in the center of our galaxy is 25,000 light years away. So even if you look at Earth scale baselines, you have no parallax. You have no access to 3D information whatsoever. And so how do we actually recover 3D information? Where usually you would rely on multiple views, right? Both in medical imaging and in classical 3D reconstruction. You rely on multiple views for cues about the 3D. And if you don't have them, then what you have is essentially ambiguity along these geodesics, right? You can swap any brightness along this curve and you still get the same pixel value because that's an integral along these curves. And so we're trying to solve a 3D from a single view. And the key is that we have a good model for orbital dynamics. So orbital dynamics are also governed by the mass of the black hole. And so if we know how things orbit the black hole, it's essentially like trying to reconstruct the 3D structure of a person with only one camera and asking the person to move around, right? So you ask the person to move around, and if you can model that and you're observing this over time, then you have a good sense of what is the 3D structure. Okay, and again, both of these are governed by the same set of equations determined by just a handful of parameters. Okay, so in practice, how does this work? Where we ray trace an image and we want to compare it to some observations. And so let's look at a single ray. We're going to take every single ray and it's going to have some coordinate. We're going to integrate along its coordinates and we're going to ask where was point X t time units ago. Right? And point X was somewhere on point X0 according to our model of orbit dynamics. And then we're going to take this X0 and we're going to query our coordinate-based neural network. What is the emission at X0? And we're going to do that for every single pixel and every single point until we can ray trace this entire synthetic video. And then we're going to compare this to the observations, and that's going to give us signal to backprop and estimate the network parameters. Okay, so that's kind of a very hand-wavy explanation of how we do it. And in fact, we did that with some observations that we had from ALMA. ALMA is one of the most sensitive radio telescopes on Earth, located at the Atacama Desert in Chile. And we got this first 3D reconstruction of something called a flare that happened on the night of April 11, 2017, around the black hole. And a flare is very interesting scientifically because this image that I'm showing here is actually the steady state Sagittarius A star, where nothing interesting is really happening. And occasionally there are these cosmic fireworks. There's something really interesting happening, and we can pick this up in X-ray, in other emission, in other spectra. And we picked it up with radio right after we saw this flare happen in X-ray. And we were able to use that data to reconstruct this three-dimensional structure. Okay, and so, again, so far everything that I talked about relies on the fact that we know the gravitational physics of the black hole, and I kind of ignored the fact that there's all sorts of other physics happening. There's fluid dynamics around the black hole, there's complex radiation physics around the black hole. And so this is future work that a couple of my students are working on. And so this is David, and he's working on making this general relativistic ray tracing differentiable. Right? So if we make it differentiable, and he's using machine learning to learn these geodesics, then we can estimate the parameters of the black hole, and we can backpropagate gradients all the way to our gravitational model. And then another, Ali, who's working on this other part, which is what can we actually learn about the fluid dynamics? So gravity is really interesting, especially around the black hole. That's a unique place to test gravity. But also fluid dynamics are quite complicated. These are plasma fluid dynamics, and so the equations are called general relativistic magnetohydrodynamics. They're quite complicated because they couple both fluid dynamics and electromagnetic theory. And so the question is, what can we extract when we look at the dynamics around the black hole? And lastly, Rohan, who's Schmidt AI and Science Fellow, he's working on tying the radiation physics and the fluid dynamics to observations, and that's something that's going to be really crucial to actually constrain some of the unknown science that happens around the black hole. Okay, so nothing that I said here is very tightly linked to black holes in particular, and this framework actually ports to neural representation plus other forms of physics. And so other problems that we're working on is this problem of imaging protoplanetary disks, which are really interesting because those are the birthplace of solar systems and planets and so on. And what we're trying to do is couple neural representations with line radiative transfer. And line radiative transfer models the emission, very narrow molecular emission, and how it's being Doppler shifted by motion. And so essentially what you get is this spectral cubes that give you clues about where are things moving because things are spectrally shifted by Doppler. And so you have, for example, if this is the disk, then this part of the disk is going to be blue shifted, and it's going to appear here, and that part of the disk, because everything is moving towards you, and it's going to be it's moving away from you, and it's going to be red shifted, and so that's going to appear over here, and this slicing is going to give you information about velocities. And this is again my student Len, who's working jointly with Rich who's at MIT, and we've been working on this for quite a while, and this is very preliminary results. Okay, so to wrap up, again, I'm working on all of these computational imaging problems for scientific discovery. Nothing that I said is actually tied to black holes or to even astrophysics. And so working also on climate-related topics. And the key is modeling the interaction between these neural representations and the observations that we have to recover something about the natural world around us. And with that, I'm happy to take questions. Yes.
Really interesting talk. So you show this picture of a black hole, and your insight of reconstruction is that black hole is rotating. So you have, I guess, you have enough time frame to capture, enough rotation to get information. So I'm actually surprised that within 100 minutes you can see the entire black hole rotating.
Well, okay, yeah, that's a good question. Well, it's not the black hole rotating, it's the gas around the black hole that's rotating. Now, I said that it's at relativistic speeds. So things are moving at like 0.6 the speed of light. And so actually, on the radiuses that I showed, it takes about half an hour to complete an orbit.
The other question is, it appears from your picture that the rotation is around an axis.
Yes.
Do you know the axis, and how does that orientation of the axis affect your reconstruction?
That's a very good question. I skipped that subtle point, but we also reconstruct the axis. We don't know the axis.
Okay.
There are we have some constraint on the axis, so there are other instruments that give us an estimation of the axis, but in this problem, we jointly recover the axis of rotation.
So if it happens that the axis is somehow parallel to your view plane, then you're out of luck.
Yes, yes.
Got it. Thanks.
Yeah, so very cool talk. I'm wondering, like, when you're modeling the light transfer, does it rely on the geometry or the mass or other physical properties of the black hole, or you also optimize that during the optimization?
Yeah, so this is, it does rely on the mass and the spin of the black hole and the axes of rotation and how fast it spins. And so in this work, we actually assume that we know the mass from other sources. So there are other ways to measure the mass. For example, people have been tracking stars around the galactic center for 20 years. And so and that was work that got the Nobel Prize in 2020. And they fit an orbital model, and they figured out that there's 4 million times the size, the mass of the sun packed into that tiny space. And so we use that estimated values. But in fact, David is working on having a differentiable model, and so this way we can have an independent estimate of the mass and the spin.
See, so it's kind of like an inverse rendering of the black hole.
Yes,
images. Okay.
it's exactly inverse rendering of the black hole.
Thanks for the great talk. I was wondering when you're kind of trying to estimate like the like you're doing your inverse rendering of the black hole. Do you think that like this will like do you expect this to yield like different results from like other like measurements, or like to get new information about kind of how like the physics around a black hole works, in addition to kind of getting better estimates? Do you think something like that's possible? Like, is this a different enough approach that like things could be different from how people are thinking about it previously?
Yeah, I think there people are thinking about this from a variety of approaches and instruments. So, for example, we've been using radio telescope data, and we estimated one of the parameters that we estimated was this rotation axis, right? And we got something that's somewhat consistent with data that came from a completely different infrared telescope, completely different approach. So this is exactly how people cross-validate results in astrophysics, because you never really know what's out there, right? I don't have a ground truth to compare to. All I can do is cross-compare with other approaches from other instruments, and the more it's independent, let's say if it's the same data but a different approach, that's good, but if it's completely different data from a different observing instrument, that's even better.
Very awesome talk. Thank you again to Aviad. Let's give her another round of applause. The next talk is by Yuqun Wu, who is a PhD student at the University of Illinois Urbana-Champaign, and he'll be presenting NeRFs for large-scale scenes and mobile applications.
Hi everyone. Hi everyone, I'm Yuqun Wu. I'm a second year PhD student from UIUC, and I'm pretty honored to be invited here. And like I'm supervised by Professor Derek Hoyne, and I also work closely with Professor Shenlong Wang. And today I'm going to talk about the human-to-human 3D modeling. So let's say we want to train a NeRF and like from the beginning and then use it for like for human-to-human perspective. In the beginning, we want to capture the image, right? Like we want to use some like daily device and easily capture it, and then we want to upload it to the model and then do the training, and then fastly download the model for us to use. And maybe sometime we also want to share it to our friends, and so that we can do the like free view rendering for any angle. However, currently, the problem is still not pretty well solved because first in the beginning, it typically requires a lot of images when you capture it, when you are trying to capture it. And you also need to have a good trajectory to have a like, good reconstruction. And then you upload to the model might not be quite robust to the sparse view. And maybe it is not pretty small enough to really be convenient for you to download it or share it with your friends. And it might also be pretty hard to get a like realistic rendering and also the accurate geometry at the same time. So in this talk, I'm going to introduce two works from our group recently. In the first work, we try to create a lightweight, real-time renderable 3D object models. So it is like pretty light size, and it can be rendered on the mobile devices, and you can easily send it to a friend because it's only 150 kilobytes. And in the second one, we try to create a 3D scene model that can provide a good rendering results and accurate geometry, even in the given the sparse view in a large-scale scene. And I want to thank a lot to the mentors and collaborators behind the works, like Jay currently at Bhattad, Derek and Shenlong at UIUC, and Chih-Hao currently at Amazon. So the first work I want to talk about is the panoptic PNG, or we call it PPNG. We try to achieve a few things in this work. So first, we try to achieve a relative fast training time. We we want it to be trained fast. And second, we try to achieve a relative small size, like 150 kilobytes field size. We try to compress it to that size because it is also kind of the size of a like regular JPEG file. And also, we want to make sure that it can be real-time renderable in any devices, typically just your mobile. So if we revisit NeRF, in the very beginning, the Berliner NeRF rely heavily on the MLP layers to do the rendering. So it is relatively small because you just need to store the weight of the MLP, but because you need to get a lot of fitful layers during the rendering time, it will also be, the training time and rendering time will still be pretty like long. And of course, you can bake it to make it real-time renderable, but the baking time and the bake file are also pretty large. Later, we get the parametric neural radiance field, typically just like Panoxo and Instant GP. They are pretty good. They are amazing. Like they enable a pretty fast training time and real-time rendering time. And sometimes they can also have a pretty good geometry structure. However, because they need to store the features of each point of each voxel, typically they will also cost a large storage. So for example, like from 10 to 100 megabytes. And later, here comes to the 3D Gaussian spreads. It's even like better. It can be rendered in real time. It can train pretty fast, and it has a pretty good rendering results. But still, the problem is there. Like because you need to store millions of the 3D Gaussians, you actually still need a kind of relative large file size. And the key in this work, we try to achieve the fast rendering time and also a small field size. So the key consideration of us is that how we can try to map the XYZ coordinate into the density in a good way. In Berliner NeRF, they just use the XYZ and do the positional encoding and feed it to the neural networks. So like slow training and slow rendering. In Planoxo and Instant GP, instead, they try to store the feature of each point of each voxel or each cell. And then like they directly optimize the feature in those beings. And so by doing that, they can allow a shallow network during the rendering time. So it is pretty fast, but it comes with a large file size. And our approach try to follow the Instant GP way. However, instead of use the original coordinate as the index, we try to use the positional encoding as the index. So for example, on the right image, instead of using the 3.5 as the index to the being, we actually use the sinusoidal function value of it, like minus 0.5 as the index value. By doing that, there are multiple benefits. First, because we are still store the features and we can directly use the feature during the rendering time, it is still pretty fast during the rendering time. And second, sinusoidal function is periodic. That means multiple coordinates can have the same index. Or in other words, they are sharing all the features in the same location. That is actually pretty good for 3D scenes because in the 3D scenes, majority of the scene is actually empty and only few of them are occupied. So by enabling that, during the training time, we will let the model to optimize like the feature in the useful location and just to figure out, okay, which feature of which point of this feature will be used actually. And it is also pretty straightforward to apply the multi-scale resolution because if you apply the different frequency, that means that is already multi-scale for the sinusoidal function. And this is like a more complete illustration of the index process. So in the upper part of the image, it is the lower frequency index. So you get the index value, and then you take it from the low frequency grid. And then after you take a feature, you use the trilinear interpolation to get the feature. And after you take the feature from different frequency, you kind of stack them and feed it to a shallow MLP to finally predict the density and color. And like because we actually need a 3D volume during the rendering in the WebGL. However, like getting the inspiration from the TensorF and dictionary field, instead of directly build the 3D volume, we can actually try to build 3 1D vectors and then do the out product to actually build the 3D volume during the rendering time. So that means we only need to store the 3 1D vectors and transfer the 3 1D vectors when we want to use it. That is actually pretty compact, and it only takes 150 kilobytes to do that. So this is the full process. After we finish the training, we get a PPNG scene file, and then we have 3 1D vectors. And in the website, we just directly compose them into the volume, into the 3D volume there. And whenever you want have a viewing direction, you just sample the points along the array, and get a sinusoidal encoding, and use the sinusoidal encoding to trilinearly interpolate the feature, and then feed that into the MLP to get the final rendering results. This is a quantitative analysis about the model size, the rendering quality, and the training time. The training time, the larger market size means it takes longer for the training, and we only compare to the methods that are real-time renderable on mobile devices. You can see that prior to the 3D Gaussian spreads, actually the works, all the projects or all the models typically need a long time for training. And 3D Gaussian spread is pretty good, like it trains fast and you still get a pretty good performance for the PSNR. However, if you look at the file size, it is still kind of large. And here I wanna invite you to have a try on your mobile. So if you want to try, you can just take out your mobile and scan it, and you can just try to play it on your mobile. And this is the first work, and I will also show a few results here. So for example, in the page, I will show here. So in the page, this is the project page, and if you click the PPNG1 and of the all objects in the NeRFs dataset, you instantly get all the things out. It's because it's actually pretty small. All the models combined together is less than 1 megabyte. And even rendering all of them actually takes less than 200 megabytes. So you can easily play them. Although the quality is not pretty high, but it is still acceptable as a small field, given such a small field size. So that is the prior work, and in this work we try to make NeRF to give the good rendering results and also good geometry results given the sparse view. On the left is the prediction of our model. On the right are 3 baselines. So we all know that NeRF was typically designed for novel view synthesis, and it is only supervised for the rendering, for the RGB rendering. So I mean, it is pretty cool, but if the geometry behind it is actually not pretty good, even compared to COMAP, which is kind of an old method. So Volt SDF tried to add the SDF representation into the NeRF, and so SDF is explicitly model the surface, so the model can have a better surface prediction. And it will actually be better if you additionally add the monocular supervision. So given the training view, MonoSDF also used the model to predict the depth and surface normal, and supervise the pixel in the training view for the depth and surface normal. That actually gives it additional capacity for the sparse view scenario, and also it can reconstruct good surface for the room level scene or even larger scenes like Tencent Temple. But although MonoSDF achieved good geometry reconstruction, there is still some drawback of it. So first, the rendering results is actually kind of blurred. If you look at the novel view and training view, no matter which one of them, actually they are not, I would not say it is of great quality. And also, even for the geometry reconstruction, if you are given the sparse view, they will smooth out some thin structure or high frequency detail of the scene. If you look at the ground truth, there are some tables, there are some bicycles, but in the estimated geometry, they are all smoothed out. Because SDF representation is pretty hard to deform to such a thin structure. And there have been some methods, some radiance-based method also try to regularize NeRF to do with the sparse view input. So for example, RecNeRF tried to sample the virtual patch and train again to tell whether the sampled rendered virtual patch is actually good. And FreeNeRF tried to do the frequency occlusion and occlusion regularization to schedulely solve the sparse training view problem during the training time. However, although like they have better rendering results, but the geometry are still actually pretty bad. Like if you look at the RecNeRF depths, although it looks okay, but the ground depths are actually totally wrong. So here comes to our method, monopatch NeRF. Typically, with just the key idea is that we use the patch-based loss for the geometry supervision and novel view guidance. So following mono SDF, we still apply a geometry supervision. But like instead of applying the supervision per image or per batch, we actually supervise them per patch. The reason is that when you are using the monocular depths, you need to solve a scale and shift between it and your NeRF depths. So if you, but like the monocular depth is accurate locally, so if you solve it in a patch, it will actually provide better supervision effect than you directly use the batch. Additional to that, we also sample some virtual patch. But instead of training again to do to tell whether it is good using the general prior, we actually unproject the patch from the training view and back project to the sampled camera center. And then we do the rendering because we are it is a NeRF, so it actually can render the RGB value out. And then you can supervise the rendered virtual patch to the training view to tell whether the additional rendering is good or not. It is reprojection, and it will kind of eliminate the lighting effect, but in the sparse view scenario, it actually works pretty well. So this is one additional comparison, and this still the left one is ours and the right one are still baselines. And it is just a scene trained with 30 images. And this is one comparison, but I'll not play it full, but the left one is NeuroAngelo and the right one is ours. The model are trained only with 30 images, but I interpolate all the training views to really see how the novel based synthesis is. And for quantitative results, we kind of achieve a good balance between the PSNR and the geometry accuracy. And although our PSNR is the second best, like our SSM and LPIPS are actually the best among all the baselines. Okay, so that is like today's talk. In PPNG, we try to make a compact NeRF models, and in monopatch NeRF, we try to make NeRF render good images and reconstruct geometry given the sparse view in the large scale scene. And due to the time limit, I kind of go through the works pretty fast, but I'm pretty happy to answer any question. Thank you.
Do you have any questions?
Yeah. For the first work, PPNG, when you use different frequencies in the encoding, can we think of it as a level of details? For example, lower frequencies correspond to more coarse appearance of geometry, and higher frequencies correspond to more detailed appearance and geometry.
Exactly, that's what we believe the model is doing. So that's when we apply different frequency, just you have different level of details. And in the paper, we also show that when you apply the low frequency, typically it's just the coarse rendering. You will not have the high frequency detail or viewing effect from different viewing angle. Yeah, but if you had at the high frequency details, then it will be there.
Hey, thanks for the great talk. So I was curious also on the sinusoidal encoding bins.
Mm-hmm.
Is it is there a natural way to increase detail at the cost of more expensive training? Could you just increase the number of bins, and would you expect it to increase in detail, or is it a method the method only allows for some level of detail?
I mean, that depends on the capacity of the model, I think. Typically, it is generally true that if you add additional being, then that it can definitely bring a better result. But that's still like the limitation. I would say the upper bound of the limitation might depend on the image, because the image pixel is actually limited. So, let's say we don't use the mid-nerf, then that means like you can only reach certain of accuracy even just using the high resolution images. And but generally it is true. Yeah, but also come with a larger field size.
That's it. Thank you two for the awesome talk. And finally, we have Itai Lang, a postdoctoral researcher at University of Chicago, who will be presenting the last talk of the session. iSeg interactive 3D segmentation via interactive definition. Just a second.
Hello everyone, thank you Lamin for the introduction. Today I will be talking about, I'm very excited to talk about iSeg, a new interactive segmentation technique for 3D shapes. This is a joint work with Fei Su, the indicator, Sudarshan Babu, and Rana Hanukkah. Recent advances in 3D segmentation have enabled flexible segmentation of various regions on 3D shapes. For example, 3D paintbrush, such a text-based segmentation method from our work, can tell us where a cow will wear its heart-shaped sunglasses. But text cannot easily describe and localize every region. Take for example, this center region of this alien shape. How would you call it? How would you call it? Okay, so yeah, it's hard to tell, right? So I tried the word box with 3D paintbrush, and this is what it got us. So it got us part of the box region, but this part of the tentacle, but this is not quite what we want. In contrast, our method, iSeg, is a click-based segmentation method. So if we want to segment this center region, we simply click on it in order to, and then our method predicts the region that corresponds to that click. Now note that our method is also interactive. So we can update the segmented region interactively. Let's say that we want to get only the front extruded part of this shape. So we can simply add another click, a negative click in this case, and then we're left with the desired region. Now note that interactive 3D segmentation is a very challenging task, and we do not have an annotated dataset that tells us what the 3D segmentation should be for interactive clicks. Luckily, we have a 2D segmentation model, SAM, the segment anything model, where an image can be segmented interactively by point click on the image. But note that this is a 2D segmentation model, and if we want to leverage this model for doing interactive segmentation in 3D, there are significant challenges for doing this. To start with, there is the consistency challenge where 2D segmentations are highly inconsistent across views. Take, for example, this 3D shape and this click in 3D. If we project it into 2D images, render the shape into 2D views and project the click in 2D and feed them through SEM, the segmentation across views differs substantially, although it is the same 3D shape and the same click in 3D. What we want is a consistent segmentation method where no matter which view we take, the segmented region corresponds to the same region in 3D. And this is what our method gives us. Another significant challenge is the occlusion challenge. Now, for a click on the backside, the segmentation with the 2D model will be only for the region where the click is visible. However, we are interested in 3D meaningful segmentations, so we want to segment also the front part of the front region of this part, but with the 2D model, we cannot do that because the click is occluded from this view. Another challenging setting is that if we want to segment the 3D shape with two clicks occluded from each other, so here we add a click on the front part, but we cannot use the 2D model for this setting because the two clicks are occluded from each other and cannot be seen together from any single view. So what did we do? We designed an interactive segmentation method that operates entirely in 3D. Our method is composed of an encoder and decoder, and the encoder takes the vertex coordinates of the shape and map them into a deep feature vector that we distilled from the segment anything model. Then we take the per vertex features and the features of the click by the user, which can be a positive or negative click, and feed them to our encoder, which contains our novel interactive attention mechanism that interacts the vertex features and the features of the click to produce the updated features of the vertices according to the user clicks. Then we take the encoded features and map these two features through an MLP to the per vertex probability in 3D that tells us if the vertex belongs to the segmentation region that corresponds to the clicks. But as we discussed, we did not have supervision in 3D to tell us what the segmentation should be. So what we did, we projected the segmentation map over the 3D shape into 2D views. And then we rendered the shape and the clicks, projected the clicks in 2D, fed them into the 2D segmentation model, and got 2D segmentation masks for supervision. And we compared our projected segmentations and the segmentation masks from the 2D model. And as you can see, the 2D segmentation model, segmentation masks are highly inconsistent across views. But in our case, since our model operates in 3D, our segmentation is 3D consistent by construction. And as you can see, iSeg managed to learn a coherent segmentation function in 3D out of its highly inconsistent 2D supervisions. But it wasn't enough. We had to deal with another challenge, which is the click configuration challenge. As you can see, there can be many click configurations. There can be a single positive click, there can be another positive click, there can be another negative click, and there can be a combination of the two click types. So we could have trained an iSeg model for each click configuration, but this is impractical because we do not know in advance which click configuration will be used. So we asked ourselves, how can we train a single model that supports different click number and different click type? And the answer was our interactive attention mechanism, which is one of our technical contributions in this work. Let's dive in and see how this mechanism works. This mechanism takes the per vertex features, the encoded features, and the features of the clicked vertices by the user. Then, similar to the attention mechanism, we learn the representation of positive clicks and negative clicks, and by learnable matrices, projection matrices. So we learn the keys and values for the clicks. Then we project the per vertex features into queries which are correlated with the keys of the clicks to give us attention scores that are multiplied by the clicks values and give us the updated vertex features. Now note that this mechanism is interactive in the sense that if we add another click, it will give us another key value, which will give us another attention score that will be multiplied by another value feature of the click and will end up with the same feature size for the vertices. So as you can see, this attention mechanism supports different type and number of clicks, and it enabled us to train a single model that supports different click configurations. iSeg produces fine-grained customized segmentations for the shape at hand. So if you want to we can get the bulb of this lamp and we can add its outer region by another click. We can get the upper region of the shade and exclude its top part by a negative click. Now note that these regions are very hard to describe with text, and actually it's impossible to describe with text because this shape is symmetric, so it is very hard to say which lamp we want to segment, but with our method, we click on the lamp that we want in order to segment. Coming back to the occlusion challenge, since our method operates in 3D, it produces meaningful 3D segmentations. So for the click on the backside, now with iSeg, also the front part is segmented. And if we add another click on the front, which is occluded from the first click, the entire backrest is segmented. And this is very exciting. Let's see the result in 3D. And this is very exciting to me because these cases do not even exist in the 2D supervision data of iSeg. So it managed to generalize much beyond its training data and learn how to produce meaningful segmentations in 3D. As we've talked about, iSeg predicts the segmentation probability. However, it can be easily converted to hard and distinct part segmentation. So we've plotted the histogram of the per vertex segmentation probability, and as you can see, there are two populations of low probability and high probability vertices, and this can be simply separated by a threshold. And then we can convert the segmentations to distinct part segmentations. And now that we have distinct segmentations which are localized, we can do local geometric edits. So let's say I want to remove this bar of the chair. I click on it and remove it. And I can also do this fine-grained segmentation of the flame of the candle. And now I can extrude it along the normal and enlarge the flame. What about future work? In iSeg, we've optimized the encoder and decoder of the model per shape to capture its unique and specific regions. So if you click on this human face, we use the decoder that we've trained for the human shape in order to segment the face. However, we found that interestingly, if we fit the features of this click to a decoder of a different shape, in this case the horse shape, it segments a semantically appropriate region that corresponds to that click. So we get the face of the horse. Although the horse decoder model have never seen any human based features. And this result is very promising and may enable us to do cross-domain shape segmentation and find corresponding regions between shapes of different domains. To summarize, we've proposed in this work iSeg, which is an interactive 3D segmentation technique for 3D shapes, and it produces customized click-based segmentations of 3D shapes. iSeg is 3D consistent by construction because it operates directly in 3D, and it was trained and learned from highly inconsistent 2D segmentation masks. iSeg handles occluded regions and occluded clicks from each other, which are cases that do not exist in its 2D training data, showing that iSeg has generalized much beyond its training data. And as part of iSeg, we've proposed the flexible interactive attention mechanism that supports different type and number of clicks and enables us to train a single model that supports different click configurations. Our code is publicly available. You're welcome to check it out. We also have an interactive demo. And you're welcome also to check our project page for more information and results. And I'd like to thank my collaborators again, Faye, Dale, Sudarshan, and Rana. And I'm happy to take questions. Thank you very much.
Very good talk. I'm wondering if this method generalizes to more complex meshes like indoor scene and outdoor scenes.
Okay, that's a great question. So we are based our supervision with the same model. So if you take a 3D model like an indoor scene, an outdoor scene, you can render it and you can segment it with SEM, or the next 2D segmentation model that will be, for example, SEM2. This framework can distill the information of the 2D segmentation model into 3D in order to do the interactive segmentation of this 3D scene, which can be also not only a shape, but probably also an indoor scene or an outdoor scene.
So there is this whole bunch of work pre-deep learning that use interactive methods for segmenting 3D meshes, like sketching, either sketching the boundary curves or sketching different parts. You can use multiple sketches, positive, negative. You can use multi-color sketches. So how does your work fit into that?
Okay, so that's a great question. We've tried to compare our method to a classical segmentation work, graph cuts, and it sometimes works, it sometimes doesn't. But the main problem is that it is very sensitive and requires a lot of calibration. So one setting fits one shape, one case, and you need another setting, another calibration to fit another case, and it takes a lot of time to calibrate this, at least from our experience. But with our model, you distill the information to the 3D shape, and then you do not need any calibration. It is data-driven, so the model captures the mode, the segmentation modes of the shape.
So you mean that you can basically batch process lots of models by clicking only on one of them?
Come again?
So are you saying that the advantage of your method is that you can batch process a whole, a set of, let's say, similar models by only clicking on one of the models?
So this is hopefully a future work. So we're working on something like this currently. So like I said, in this work, we took a shape, we took a subset of these vertices for training, 3% of the vertices, we trained only on them, and then we can click whatever vertex that we want. But we optimize for the shape. And currently we are working on a follow-up work that we want to learn a model for several shapes and then give it a new shape that it hasn't seen to be able to segment it as well. So that's the follow-up.
Do you think this can be extended to maybe 3D volume data, that kind of thing?
That's a great question because we're working on it.
Can you repeat the question?
Yeah, okay. So you want to repeat the question?
Yeah, the question was.
You can get the microphone.
Okay, thank you so much. Hi, yeah, the question was about 3D volume data, and I think the answer is yes.
Yeah, so we are in the process of working on it. The architecture or the framework that we used here is not tied to meshes specifically. It can also be applied to other modalities. So we're also working on extending this model to other modalities like volume rendering and other modalities that I will not currently say, but yeah,
okay.
It's possible. Yeah, go ahead.
I noticed that in the interactive attention, so typically you have the each slot or each beam correspond to one voxel or one any point. So during the interactive attention, is the beam each beam correspond to one voxel or one point?
So what it corresponds to? It corresponds to vertex. The shape is composed of vertices. Okay, so we distill a feature vector per vertex, and we interact the vertices with each other. But since we optimized a field over the mesh that takes a 3D coordinate and produces a feature, we can click any other point on the surface and query the field at that point to get the feature, and then we can interact the vertices, the other points with the click point, and so it's flexible across the surface.
Then do you see there's any limitation when you apply to the larger indoor things for the resolution part?
We'll have to deal with that. Maybe we'll have to use a different representation for the interscene, or maybe use some tricks that can represent large-scale scene within a NeRF. I mean, such trick exists, like inverse scaling of the point. So as long as we can cope with the representation, I think we will manage to do that for large scene. I mean, for the 3D representation of the scene. Okay.
All right. Thank you, Itai, for the awesome talk and the questions from everyone. I think we will take a break, and you can feel free to go out and grab coffee, and we'll be back here at okay in about 20 minutes, so that we can enter the second session.
Okay, we are a little bit behind schedule, but I planned the buffer for last, so don't worry. Okay, now we will have the second session on reconstruction, and we will hear David Lindell, which is an assistant professor at the University of Toronto, and he'll be talking about the interesting topic of acquisition-aware generative scene reconstruction. David, the scene is yours.
Great, yeah, thank you so much. What a great event. Thanks to organizers and thanks for the invitation. So I want to start off by showing you a clip from one of my favorite YouTube channels. This is from Corridor Crew. Does anyone watch these guys? They're VFX artists and they like to react to different VFX shots. So let's see what they have to say.
And I would like for you guys to tell me whether you think this shot is CGI or not.
Exactly. Look at what you became. Oh! What? Go back. Just one shot. Okay.
It's so
that shot is not the same as the other shots around it.
Basically generated a shot from scratch to get a pickup.
If they're reperforming her face, it's very well done. Also, notice how like the rest of her head and face don't really move, but it's like the annoying orange a little bit.
Okay, so you can imagine being a director and you realize you missed a shot and you have to somehow come up with this shot after the fact. This is a really hard problem, right? You can maybe only work with an image. It's very hard to synthesize this actor moving around in 3D. There are complex changes in their topology, what they look like, the wrinkles on their face, the hair is moving around. That's very hard to synthesize or generate in a realistic fashion. And this is not an automatic process, right? Normally you've got some artist who's going to be laboring frame by frame for hours to try to stitch these things together. This is really hard. So over the last 2 years or so, I've been working to develop techniques that can leverage generative models to reconstruct dynamic 3D scenes that are consistent with acquired data and that can generate new data, images, or scenarios under novel acquisition settings, such as changing a subject's pose, changing the camera pose, changing expressions or head pose after the fact, after the capture, but yet be consistent with the data that was captured or acquisition aware in some fashion. And so, for example, using our recent technique, we can take as input a few reference images of a person, and then we can generate new images of these people from new viewpoints with different expressions, and we can generate all sorts of wrinkles, expression-dependent changes in the appearance, and I think get a very good likeness of what these people would look like had they been emoting or expressing in this fashion. And then we can use these images to create an avatar that can be rendered and animated in real time and achieve photorealistic quality. So this is a Gaussian splatting-based representation. And we can even do this with one image. So we can see what Abe Lincoln might have looked like if he were a little more lively during the photo session. We can even get some really interesting, wrinkles and expression-dependent changes in what people look like in these generated images, and from a single image also create these avatars that can be animated and rendered in real time. So I want to step you through the journey towards getting these results and take you at least through a few steps, starting on work that we've been doing in generating animated 3D scenes or 4D scenes from a text prompt, and then working on acquisition-aware 4D generation. And so what is text to 4D generation? Well, this is the problem where you take as input a text prompt and you try to generate an animated 3D scene that conforms to the text description. And there's not much 4D data, right? There aren't large data sets of animated 3D scenes rendered from multiple viewpoints that you can use to directly learn these models. So what you really need to do are to leverage image and video models for this synthesis task, this generation task. And what I would say is maybe the seminal work in this area would be score distillation sampling. There's also concurrent work on score Jacobian chaining, I think from here, right? Yeah. And the basic idea is to use image generation models to inform and guide the 3D generation process. So the idea is that you represent a 3D scene using a radiance field. So a volumetric representation that parameterizes appearance and geometry using a volume of density and color, parameterized at every point. And then you render this scene from different viewpoints, render images out, add some noise to them, and then you use an image diffusion model as a kind of oracle that denoises the image and tells you, well, given a certain text prompt, this is what it should look like. And from that procedure, you can derive gradients that you can backpropagate all the way into your volume representation, update the volume, and then repeat this procedure until you start getting a 3D object that pops out. So the optimization looks something like this. And you can get some reasonable looking 3D objects from just image supervision, which is kind of crazy. But this is not perfect. So at the inception, it only worked for 3D scenes, static scenes. We like to do dynamic scenes. There's also problems. This problem called the Janus problem, which I'll talk about in a second, which so the geometry that's produced by this method is not perfect. And at the time, the existing methods that took this technique and adapted it to 4D or dynamic scenes, it was closed source, and the visual quality was somewhat limited. So what is the Janus problem? Well, this is named after the Roman god of beginnings and endings, Janus. So when you look up the depiction of Janus, there's always two faces, a face looking back and a face looking forward. Well, it's a kind of cute moniker for this problem. And here's the problem. If you look at the generations, you see that there are like multiple faces and all these weird appendages sticking out when you start rotating these 3D objects around and looking at them. And why does this happen? Well, it's because if you think about the supervision mechanism, you're only ever supervising the 3D generation from one view at a time. So you're basically enforcing that from any given viewpoint, the thing you generated looks like the text prompt. But it doesn't necessarily, there's no constraint to inform that the whole object viewed from multiple viewpoints looks coherent. So you get these extra heads and things. So that's not great. So what people propose to address this problem is to train models that could synthesize multiple views of an object simultaneously. This allows the model to reason about what this object should look like from multiple viewpoints rather than just one viewpoint. And then you can use this model with score distillation sampling, backpropagate the gradients into the 3D structure, and then you go from something on the left side to something on the right side, and you can see that we now have one head, and we don't have multiple heads, multiple appendages. So this is looking better. But we're still only for static seeds, and these are primarily trained on synthetic data. So usually when you went from a single view generation model to using a multi-view generation model, the quality also goes down a little bit. And then you can add, so a couple of years ago, video generation models are starting to come out. And you can take these models and run score distillation sampling, and now you can start to get dynamic scenes. Okay, and this is doing something reasonable, but at the time, the method from Meta was closed source, and the visual quality, we're not getting photoreal results out of these methods quite yet. So we worked on techniques for 4D generation using score distillation sampling. We came up with an optimization approach that would use supervision, hybrid supervision from single view image generation models that really had the best quality at the time, multi-view models to try to get rid of this Janus problem, and then video models to bring in dynamics to the scene. And these were the kind of results that we could generate at the time, and this is what we showed at CVPR last year. And you can see the improvement in visual quality going from the top row, the previous method, to the bottom row, which was our results at the time. And then we also extended this technique to generate objects that can move along a trajectory rather than being animated in place. So the objects here are all generated separately, and then we can composite them together and create these more complex scenes with multiple objects moving around. And this is all supervised using a video diffusion model and a type of score distillation sampling that we created. But there's still, so I thought this was actually pretty good at the time for what we were doing. But there's still obviously room for improvement, right? One thing is that score distillation sampling is really slow. It's hours of optimization to generate a single object. So that's not so great. We're not yet at photoreal quality here with this technique. And there are other limitations of score distillation sampling, other reasons why it's difficult to get photoreal quality out of that technique. And the video models at the time were relatively limited. So here's a slide from one of my students in 2023 from his weekly update. And we're just trying to grapple with the limited quality of these video models. You can see that they output something meaningful, but like the skateboard's not the right shape. The paws of the dog aren't always like hitting the ground. They're moving kind of weirdly. This thing is supposed to be a dancing panda. So things aren't, I was actually kind of amazed that we could get the quality that we did out of these video models. But how do we move on from this and improve things even further? So we decided we would drop SDS. We need a different paradigm to generate 3D and 4D scenes. And part of the reason the quality is limited because we're tackling a really big problem. We're trying to generate any sort of 3D, 4D scene from a text ROM. So what if we focus on a specific domain? And let's try to use image models instead of video models, since image generation quality is so much higher than what we can get with video models. And that led us to this next direction, what I call acquisition-aware 4D generation broadly, but also in the specific project of generating humans. And there's lots of existing work on going from single images or even multiple images to animated 3D models of humans. But single image methods typically don't work very well when you try to create an avatar whose expression or pose deviates strongly from the input image, like you're seeing here. These are methods that usually try to predict an entire 4D representation or animatable 3D representation from a single image. And similarly, there are other methods that might take in multiple images as input, but if you don't have enough images or enough coverage over the space of expressions and poses, then these methods also don't work very well. And there are also, likewise, these same methods, if you add more images, they perform better. But again, if you try to synthesize views from very different viewpoints, you start to see artifacts. So we took a different approach to this problem and created a method that can work with any number of input images and generates strong results in each case. And we're inspired by earlier work on 3D generation. This is a paper called Cat3D from NeRFs 2024. And the idea was to take an input image, use a multi-view diffusion model to generate many views of this scene from different viewpoints, and then reconstruct the scene using a NeRF. And the results are quite good, surprisingly good with this type of approach. So this is like what I would call a generate and then reconstruct paradigm. Now, to extend this approach to our case, there's a bit more that we have to do. These are static scenes. We need to handle dynamic scenes and humans that can move around and change expressions. And fortunately, since we're working with human faces, they're really strong priors over what humans look like and how they can move. So in particular, we can leverage trackers that give us an accurate reconstruction of the 3D shape and expression of a person's face from a single image or a sequence of images. And we can combine this with large data sets, image and video data sets of people, and learn to generate what people look like and different expressions and so on. So we created a data set, a track data set of about 25,000 video sequences that we use to train a model. And we follow the same generate and reconstruct paradigm. We take an input image, generate hundreds of images from different poses and different expressions, and then we fit a 4D Gaussian splatting-based avatar to reconstruct this avatar that can be animated and rendered in real time. And here we're building on Gaussian avatars, previous work in this space, and we adapt that a little bit to improve the results as well. So the overall architecture looks something like this. We take at the input a set number of reference images that we're going to use to condition the generation. And this can actually be, in this case, I'm showing 4 images. It could be 1 image. And we can actually extend this to handle any number of input images. And then we take in some set number of images that we want to generate for a particular forward pass. These come in as sampled noise at first. So we're going to denoise them to generate the images. And then the key here is to add some conditioning signals to inform the network what's supposed to be generated and what should happen. So these are the ray direction, which tells the camera viewpoint. We also take the output of the tracker, which is a parametric head model fit to that image frame, and we take the XYZ coordinates of the mesh that the tracker outputs, positional encode those, and render these maps that basically give you the shape of the head from a particular viewpoint. And then we also render these expression deformation maps, which tell you how the vertices are deformed for that particular expression from the canonical mesh that's tracked to that person's face. So this helps to resolve some ambiguities that might be difficult to reason about otherwise, such as like the position of the chin and how exactly it's deformed in that image. So we notice this helps as well. These all go into denoising diffusion model with some cross attention between the layers and you get out these images that are rendered in a consistent fashion. And then we can take all of these images and reconstruct a Gaussian avatar. I'm not going to go too much in the details here, but you basically have a model that positions a Gaussian onto a mesh representation, and this can be animated using blend shapes in a 3DMM. And we added some additional features here to account for expression-dependent changes in the appearance and geometry. Okay, I'm going to show just a few results. So this works really well. We get better appearance modeling than previous methods. We can also do cross reenactment. So you can take a video of someone else and drive an image of a person. And we can even do like non-photoreal subjects and create avatars from them too. Okay, so let me just skip to some of the limitations and discussion. So we want to extend this to 360-degree generation. We're currently limited by the data sets of people, which are mostly forward-facing. So you can do 360-degree generation, but you can see the back of the head is not so great. So that could probably be improved with better data sets. And we also segment out the background. So sometimes you'll see some artifacts from the background segmentation not working so well. And some of the images have hands over the faces. So the network will also generate these hands sometimes. But again, I think this could be improved with better data curation. We've also been working on video models. So you can imagine bringing video models into the mix here. And these are getting quite good. So this is a model where we can control how the camera is moving through the scene. And here's another case. So you can render the same scene from controlled camera viewpoints. And so I think this is really a broader application of acquisition-aware modeling, where we can control, for example, maybe not just camera position, but other parameters of the acquisition process. And then I'm also excited about other applications to emerging sensors and computational imaging, which we're exploring in the group. So just to wrap up, this is work done with a bunch of collaborators. I'll highlight Sherwin and Felix, who led these projects. And if you want to see more results, you can check out our web pages. So thanks very much.
Thank you, David, for the great talk. Any questions? We have one quick question. Okay.
Yes, I had a question about when you added the other like modes like that weren't just like the image of the face. Which ones were like the most helpful towards like use? Was it kind of like if you include any one of the three, then that was like super helpful, and adding all three was like, marginal improvement past that, or were some like just marginally like just better for helping predict?
Yeah, we have some ablation studies on that in the paper. I think just adding the 3D positional encoding was probably the biggest thing, because from a single image, the model has to reason somehow about the 3D structure of the face and what it should look like from different viewpoints. So adding this 3D positional encoding helps somewhat, but there are still some ambiguities of like occluded regions and what's going on there. So the expression dependent deformations adds a bit more image quality. So each of these things improves a little bit, I would say. Yeah.
Thanks.
Okay, let's thank the speaker again.
Hello.
Next. No. Okay. Next we'll have Jiahao Li, which is a PhD student at the Toyota Technological Institute in Chicago, and he will talking about fast map dense and scalable structure for motion revisited. Take it away.
Yeah. Thank you. Happy to be here. So I'm a student from TTIC, which is an institute kind of very closely related to U Chicago. And this is a recent work from our lab on structure from motion. So structure from motion is an essential task in 3D computer vision. So basically what it does is that given a set of images, find the camera parameters, including the intrinsics and extrinsics for each image. So this is an essential step before almost any kind of 3D reconstruction methods. Either it's old-fashioned multi-view stereo or kind of modern methods like neural reconstruction methods like neural radiance views or NeRFs. So in the past few years after NeRF came out, people tried very hard to speed up the reconstruction part of the entire reconstruction pipeline. We have the original NeRFs, which are kind of represented using MLPs for every point in the 3D scene, which was very expensive to both train and kind of do inference. And then we have like innovations like instant NGP and Gaussian splotting after that, try to speed up the process. But if we want to reconstruct a very large scene like a city scale scene, kind of presented here, the bottleneck of the reconstruction pipeline is really the camera pose estimation part. So we kind of benchmark the kind of existing most popular pose estimation structure for motion pipelines called GlowMap or CoMap on like, I don't know, 12 data sets. So here we have like, we average the results for all the data sets. So here, this number represents the number of images in the data set. And we also calculate the average number of images in each data set. So numbers here are the timing results in seconds for these two methods. So if you look at maybe the first line, it's kind of acceptable for around 200 images. You have you need like you're gonna need around, I don't know, 10 minutes for CoMap, which is the current state of the art and the de facto choice for practitioners, and around 300 seconds for GlowMap, which is a new method that came out in 2024 by the same authors of CoMap. But this is acceptable for many people. But if you scale up to more images, like thousands, 1,000 or 3,000, or even to 6,000, the time scales very drastically, and it gradually becomes really unacceptable. For example, if we have like around 4,000 images, then even the fastest system before our method, GlowMap, takes, my math is not very good, but several hours. If you use like in these two scenes, there are like very dense matching and thousands, more than 4,000 images. Both GlowMap and GoMap kind of really fail to finish in our experiments. It takes like more than a week, so we just stop them. So this is how slow these current methods are. So what we're trying to do is to speed up this process, but we first need to understand why the current systems are slow. So if you have to learn about 101 of 3D vision, this is the basic, the very coarse pipeline of the structure from motion system. We first need to do image matching, which is that given a pair of images, we find the corresponding points in the image space. And then after that, we feed the results to the pose alignment stage, where we use geometry to kind of estimate the poses of the cameras. So in practice, when we have a lot of images and a lot of matched pairs, the matching stage is actually, the bottleneck is actually at the post-alignment stage. And also the matching stage can be parallelized using more processors because each process of finding correspondences for each image pair is kind of independent from each other. So what you really want to do is to speed up the latter phase, which is post-alignment, given the matching results. So the current structure for motion pipelines are very complicated systems, but there are two main reasons why they're so slow for the latter stage. The problem one is that the whole ecosystem of the current structure for motion is basically built on CPUs. They write code in C++, and it's not very easy to migrate it to run on GPU. And even now, the default choice in both CodeMap and GloMap are using CPUs. So this is kind of sounds very ancient. So we really need to improve on that. So the second problem is in the post-alignment stage, there's a very important process called the bundle adjustment, which is a nonlinear optimization problem. Basically, what we want to optimize is both the 3D points, like here, in the 3D scene, and the camera poses for all these cameras. So the problem of this is that usually the number of points in the scene is very large. Like in this matching stage, usually we can have thousands of matches between one pair of images. So if you have a lot of image pairs, it can be the number of points. The number of point pairs can be 1,000 times more than the number of images. So this process it can very easily scale up to 1 million points. So it's very expensive. Consider that at every iteration you need to compute some quantity that has complexity kind of linear to the number of points in the scene. So these are the two main problems why the current systems are so slow. So in our paper, we proposed a new structure motion pipeline, which is much faster than the previous methods. As I said, since the bottleneck is at the post-alignment stage, our method only works on the post-alignment stage after we get the matching results. We get the matching results from CodeMap, which is the same for the other two competing methods like CodeMap and GloMap. So I don't have time to dig into the details of this pipeline. It's a pretty large system, but I can talk about two main design principles for the system. So the first one is kind of straightforward, that we choose to implement everything in PyTorch. So basically, now if you just jump into computer vision, everyone does deep learning, and they know how to use PyTorch. But nowadays, students don't really know C++. So we implement everything in PyTorch, which is very convenient for parallelization on GPUs. And it's also very easy to for the new researchers, especially students, to read the code base and modify for future improvements. So this implementation requires we kind of implement all the essential, actually all the operations in all these stages using tensor operations. We don't really heavily use the backpropagation features of PyTorch, but we use the dense matrix or tensor operations in all these stages. So this is the first principle that allows us to accelerate the pipeline. So the second main philosophy is that we try to accelerate the nonlinear optimization part, especially the bundle adjustment part. As I said previously, in bundle adjustment, in every iteration, you need to compute something that is related to the number of point pairs. But here, in all these three stages that involve any kind of nonlinear optimization problems, we kind of formulate the problems in using some mathematics so that we do some pre-processing before the optimization loop and eliminate the computation in each iteration that is related to the point pairs. We basically merge all the point pair information for each image pair into some compact form so that during each optimization loop, we can only compute the quantities that has complexity linear in the number of image pairs. So that significantly reduced the complexity of these nonlinear optimization problems. So here are the results of our method. If you look at the left are the timing results. The first column is our method. So if you look at the the first row where we have in the case of around 200 images, the speed up of our method over the previous methods is not very significant. It's like a twofold speed up. But if we scale up to more and more images, for example, here, if we have around 4,000 images here in this scene, so the speed up can be 1 order of magnitude compared to GlowMap, which is the 2024 method. If we compare to CoMap, which is even faster, it's 20 times, I think so. No, it's much faster. But so if we scale even more, where we have more point pairs and more images, like in these very large scenes, our method can be 2 orders of magnitude faster than GlowMap, and CoMap doesn't even finish. So yeah, case. And we can look at the plot at the right, which is where the horizontal axis is the number of matched key point pairs, and the vertical axis is the time in seconds. Both axes are in log scale. So the red here we plot the results for all the scenes in all the data sets, and the red color indicates our method. The other two are the competing methods, CoMap and GlowMap. So as you can see, if we when we scale up the number of point pairs, the time our method requires is has better scalability than the other two methods. And in terms of accuracy, our method does come with some sacrifice. So if you look at the left table where we compute the accuracy of a relative process, where we just take the final global pose results and compute the relative poses between each image pairs and compare to the ground truth, and we compute the fraction of the percentage of the number of image pairs that have error less than 3 degrees. This is a standard metric in structure for motion. So this is a very tolerant metric, and if we look at the results, except for maybe one data set here where our methods suffer because of all the symmetric structures and repetitive patterns. For all the other data sets, our methods, the results of the accuracy of our method is very close to the other competing methods. And for some method, sorry, I should have put the data set names here, but the thing is, for some data sets, the other two methods fail pretty miserably, but our method does very well. But if we turn to more stricter metric, for example, here it's called something's called AUC. I don't want to explain it here, but it's a metric kind of put more emphasis on the sub 1 degree accuracy. Even if all the relative image pairs have relative angle error less than 3 degrees, it can still be very low on this metric. So for this stricter metric, our method kind of is not very good compared to the other two. So our method does come with performance sacrifice, but if you're not very kind of extremely careful about the final 1 or 2 degree accuracy, I think our method is fine. So as I said, like structural motion, yeah. Sure, yeah. So structural motion is an essential step for 3D reconstruction. So we also kind of evaluate the downstream NeRF results using the poses from our methods and the other two. So basically the story is if we use the state-of-the-art method Zig NeRF, basically the story is, for example, if we look at these results, our method is kind of close to what the other two methods can give for Zig NeRF, but it has a small gap between them. But if we turn to methods that also optimize the camera poses along the reconstruction process, the gap can be pretty much closed. So, and also we compare to the recent deep learning methods. It's a very hot topic, but we found that the deep learning methods are still lagging behind compared to traditional methods by a very large margin. Yeah, so that's the end of it.
Thank you, Jiahao, for the great talk. Any questions? Okay, go ahead.
I have a question. So you compare to master, but typically now, I think you have more work for the multi-view feasible model, like faster, ambidexter, or even like BGGT. How do you think of that, like that field? Do you think it is, if with enough data, it is able to achieve the same quality post-regression, or they can be used as the initial step, as the initial post-assumption, and then be refined by the Foley method?
Yeah, I think all these methods are promising in some cases. For example, if you have you take like 1,000 images for this in this particular room, and you use feed-forward methods, I think they can do pretty well. Even though, as I said, the accuracy will not be very high, but they might be able to be used for initialization. But I think if you want to reconstruct something very large scale, covering kind of geographically a very large area, like in this city scale reconstruction, I think at least the current deep learning methods still struggle. Usually they will just fail very miserably without giving you any sensible results. And my own kind of prediction for deep learning methods is that it's a dead end. I don't really like them, so that's why I do this work. It's because I think that we know very deeply about 3D geometry, right? Why don't we use that? Why do we trust the black box model? So yeah, that's my take of this.
Okay, thank you very much. Let's thank the speaker again. All right, next we will hear Arturo Russell, which is a PhD student at the University of Notre Dame, and he will tell us about the challenges of aerial computer vision for emergency response scenarios. Arturo, the stage is yours.
Hi, thank you everybody for having me here. As a fair heads up, this might not be too related to computer graphics in reconstruction, but hopefully interesting as well. My name is Arturo Russell, and I will be trying to give an overview of what we have been working to tackle the challenges of aerial computer vision for emergency response scenarios. And the work in this presentation has been done in collaboration with Dr. Jiahao and Dr. Walter Chiro. So kind of to start giving a context of our work, we work everything in the application of emergency response scenarios, and that means, for example, search for a missing person, search and rescue, some law enforcement scenarios, drowning situations, natural disasters. In general, situations where mission success is imperative as it translates to human lives. Now, our contribution to this context goes on the integration of drones, and that's because emergency response is one of the most promising fields regarding the integration of drones in applications such as aerial photography, videography, 3D mapping, inspection and reconnaissance, and delivery services. So for the past couple of years now, our lab has been working to build this platform called Drone Response, a platform made for multi-semi-autonomous drones. And it has the goal of deploying them on what we call intelligent missions, and that's thanks to the onboard computing that we integrate and all the collaboration mechanisms. We work in this environment of human-machine teaming, so there's always going to be this communication with the human, and that's because it's kind of a safety-critical application. Now, from the technical point of view, this is a system of microservices. Some microservices get deployed on the ground control station, while others get deployed on board the drone, and they communicate through MQTT protocol. Now, I could go deeper into the software and hardware of this part. It's very interesting. But to summarize this introduction, we're trying to deploy these monsters in time-critical situations where mission success or mission failure translates to human lives. And one of the things is that we're trying to deploy them in what we call intelligent missions, but to reach this intelligent part, the computer vision plays a crucial role. And this just, if someone's interested, that's where all our hardware goes in. It's kind of pretty cool because it's kind of plugged in to another drone, and now the other drone could be used. Nonetheless, utilizing the computer vision comes with a lot of challenges if we want to really integrate it to drones in emergency response scenarios. And one of the, well, first of all is that emergency response, the application itself brings with a lot of diversity of scenes, chaos of the real world, the need for real-time detection, and a lot of occlusion. So occlusion is kind of a big deal because, for example, if a person is drowning, you might only be able to see the head and arms stretching out. If a hiker is lost in the woods, there's going to be trees everywhere to cover him. If there's a natural disaster, there's going to be a ton of debris. And even in fire situations, the smoke becomes an occlusion source. So occlusion is kind of one of our biggest problems in terms of computer vision. And these are pictures just to exemplify kind of the chaos of the real world, because you want your computer vision models to be robust enough to detect the person in these very different scenarios. So this summer lake scenario versus winter building scenario, and we have several other scenarios. Now going to the second challenge, I would say. What we mean by aerial perspective is one of the strengths of the drones is that you can put them as high up as possible to cover a larger terrain, and you can bring them as close as possible to bring more details. That from the computer vision model perspectives brings a diversity of field of view visible features, because the human is going to be very different from 10 meters than from 90 meters. And then if you're going to go high up as 90 meters, then you are bringing the problem of low resolution. And to exemplify this part here is at 10 meters, and the second part right there is at 90 meters. So for us, this looks a very similar scenario. Forestry, there's one person in there. But for the computer vision model, this is a very different scenario. And the only change here is the altitude, right? And last but not least, we are deploying computer vision models on board the drone. So this brings a lot of constrained resources and computing power. So we started wondering how could we start tackling all of these challenges? Maybe not all, at least some of them. Well, if you were wondering where those very interesting images came from, they are part of our dataset called Nomad. So Nomad is our first contribution that I'm going to be speaking about, and stands for Natural Occluded Multi-Scale Aerial Dataset for Emergency Response Scenarios. And in Nomad here, we're trying to tackle the challenges of the real variance in the natural world by having different locations, a diversity of participants, the problem of occlusion, and I'll go over that, how we try to cover that, and to try to exploit the strength of drones to be able to perform at multiple scales. So Nomad contains rich metadata, videos, activity labels, imagery, bounding box, and a very specific visibility label that I will try to cover here. So to create Nomad, we filmed the participants at 5 different distances, starting from 10 meters to 90 meters. We also include a ground reference view of the participant, where they do a 360-degree turn, and this is for re-identification tasks, where in our application it translates to missing persons. And during the routine of the participants had to go behind obstacles to get that degree of occlusion, and they also had to lay down on the floor just to get the emergency response scenarios part. Now, this gave us tons of millions of frames that we could manually annotate, but that would not be humanly possible. So to make the annotation part humanly possible, we selected keyframes. And what I mean by keyframes is If the person was walking from point 1 to point 2 in a straight line, then point 1 and point 2 would become the keyframes, and those would be labeled. And then if you wanted to annotate the others, you could interpolate. So that's why we ignore that part. But in the other case, if the person was walking from point 2 to point 3 behind an obstacle, we would sample that part just to get that different degree of occlusion. And we would sample at different rates, depending, because some participants would go running, some others would go walking, so you have to kind of be aware of that. We include activity labels, those keyframes, such as walking, hiding, laying down, and we had some drowning scenarios also, so you would see some drowning and swimming activity labels. Now, to get to the visibility label, for every single bounding box that we have, we assign a visibility label, and it basically tells you the percentage of the human body that's visible in that bounding box. It's not going to tell you that there is a 53%. It tells you kind of in a range of 10 different levels. So to summarize Nomad, Nomad contains imagery of 100 different actors. We have more than 40,000 manually annotated frames, 500 routine videos. The video quality was 5.4K, so pretty good. And we have rich metadata to work for identification tasks and such. We did some benchmarks, so some of the out-of-the-box models just to see how they perform. We did RetinaNet, Faster RCNN, and YOLO. In that time, it was YOLO V8. Now there is like V11, or I don't know what number. But as you can see, all of them kind of perform the same. They do mostly well at 10 meters, and that's because they are pre-trained on the COCO dataset, and COCO dataset is a ground view dataset, so that's kind of expected. But you can also observe how the performance degrades as the occlusion increases. So that's one of the problems. So in a nutshell, Nomad could be used as an occlusion benchmark, or it could be used to improve person detection tasks, person re-identification, or even person tracking due to the strategic selection of manually labeled keyframes. And I guess that the best part of all for the community is that it's a public dataset, so you could access it. So now going to the second contribution that I'm going to be speaking about is you could use Nomad to retrain, fine-tune your models, and they would do better. We did that. But then comes the question, how could you improve further on? So we took the road of improving detection through human perception. And I don't know if the term psychophysics sounds here, but it's a very popular word in our lab with Walter. There's a ton of work done in that regard. Psychophysics, basically the general definition is measuring human behavior, the physical changes in visual stimuli. And how do we translate that to our application is, I could ask all of you with the task to find the person in the picture right here. And while you're doing that, I could measure your human behavior. That could be, for example, I could be measuring your accuracy or your response time. So that accuracy, that response time would be the human behavioral measurements that we would be collecting. Now, I could change the picture, and this one might be probably 50 meters, looks like. Now, I could change it to a picture from 10 meters. And I could do the same experiment and measure your accuracy and your response time. And so I'm changing a physical stimuli that in this case is the distance that's taken from the picture. We did it with distance, and we also did it with the degree of occlusion. So using Nomad, because we have the visibility label, I can test how do humans perform when there is a different degree of occlusion in the image. So we perform those tests. So the research question now becomes, can we successfully embed the human behavioral measurements into the detection model to improve person detection under aerial occluded views? This is a general view of our experiment. We created a survey that we deployed on MTurk, so we presented images from Nomad. They had the workers had the task to find the person in the picture, and we collected some search behavioral measurements. This with the goal of modifying a loss function to improve a computer vision model. So that brings us to PsychR. PsychR is a dataset, part of Nomad. So it's a dataset containing human search behavior that is psychophysical data of more than 5,000 aerial images from the Nomad dataset. These 5,000 aerial images were strategically selected so that we covered all the degrees of occlusion, all the degrees of distance or altitude through the 100 different actors. And we provide the search behavior, accuracy, and response time. And again, it's also available to the community if you're working on something similar. Now, from here we could have taken different paths to improve to modify the loss function. We could have used the heat maps and play with the activation maps. The path that we took came from an observation that when humans are given the instruction, find the person in the picture without additional explicitness, tightness of their selection is not a priority. And what we mean by that is the red circle there is the human selection, and the small red rectangle inside is the ground truth bounding box. We also computed a histogram of IU values just to confirm this, that's not just happening on one picture. And as you can see, the IU between the human selection and the ground truth box, the higher frequency is always on the lower bin. So if you evaluate humans with an MAP of 0.5, their results will tell you that humans are doing terrible. So basically, that's not a good method. So we started by mapping the bounding box to a Gaussian distribution. So we took the center of the bounding box to map it to the mean of a Gaussian distribution. And then the variance is where we inserted the human perception. So the variance is going to be guided by the human accuracy in this case. And what it does, it changes the shape of the Gaussians according to how humans are performing in these tasks. So for example, at 10 meters at 90% visibility or something like that, humans are going to have a very acute curve. 90 meters, the curve is going to be flatter. So we use this to create a human penalty that we added to the loss. And in summary, we force the loss to concentrate initially on the XY coordinates of the center of the bounding box, and it starts to achieve its focus towards standing in the bounding box prediction as the human penalty decreases. So we still keep the default loss because that's going to be responsible of creating the bounding box, but we add this additional part of focusing on the XY location of a person. We performed an experiment with trained the RetinaNet model for the netbox and Nomad, first just with the default bounding box, which for RetinaNet is a smooth L1, and then with our psychophysical loss, which is the human penalty plus the default loss. So we evaluated with an MAP of 0.5 to 0.95 just to verify that we are not hindering the tightness of the bounding box. In this case, the red lines are the baseline, and the other lines are different altitudes and across different occlusion levels in the x-axis. So we do not hinder the tightness of the bounding box if we use this method. And as you start evaluating with lower IUUs, you start seeing the more improvements, and that corresponds to the observation that we saw from the human experiment that we had. In this case, with a metric of 0.5, just to follow standards, we see how MOL starts to perform better at higher distances, specifically at 70 meters. But just as a note, they do start to do better, but if you compare, for example, 40% visibility, it's still a problem. So occlusion remains a problem, so it's something that we have to work on further. And I'm not really sure how I am on time, but so 2 minutes? Okay, awesome. So just to not leave out the last but least challenge, and I'm referring to the edge computing part, there's a huge difference between what we have on board, which is this one here, versus what could be on the ground control station or the cloud. And I'm not even putting the comparison to an A100, but there's a huge difference. Right now, our current project is trying to exploit the onboard and offboard capabilities. So basically, how can we compute a computer vision pipeline that optimizes and exploits these two parts? And huge thanks to all of my peers from both of my labs, from Walter and Dr. Jane, these publications, and huge thanks to you all to stay to the end of this presentation.
Thank you, Arturo, very much. Are there any questions? Yeah, go ahead.
I think great talk. It's great to learn. I have two questions. So one, if you go back to the second graph, the base in this graph seems like it's doing better than the YOLO base. Or is this the so what is the difference between that base and the YOLO?
Yeah, so the YOLO one is you take the model, you don't fine tune it or anything, just out of the box, and you benchmark it. And it's gonna do worse because it's pre-trained on the Crocodile set, and that's just ground view images. This one, the baseline, you fine tune it on Nomad, so that the only difference between the experiments is fine tune it with the default loss and fine tune it with our psychophysical loss.
And then a second question is. So I guess right now, and your setup, you're taking in the whole image, and you're doing prediction. Have you thought about at all some kind of trying to search over the image, or zoom in plus enhance or something along those lines?
Trying to patch it? Yes. So there are some problems when we're working with detection on the edge, and is that, for example, it's really hard to process an image on real time. So because the images that we're getting are, for example, 4K. And to process an image of 4K in real time, it takes a long time on the GPUs that we have. Now, we could do some techniques like cut it and then detect on the patches or something like that. But so far, we have not done it. That's part of the pipeline that we are building. And I don't know how it will do. Thanks. Yeah.
Okay, let's thank Arturo again. Okay, the last talk in this session would be by Jianjun, which is a PhD student at the Washington University in St. Louis. And he will tell us about implicit surface reconstruction from sparse samples. Go ahead.
Hello everyone, I'm Jianjun Xiao from Washington University in St. Louis. I'm a PhD student, currently supervised by Professor Tao Ju. Today I'm going to talk about implicit surface reconstruction from sparse samples. Here is an example of Barney model reconstructed from point cloud using screen person. Surface reconstruction is a classical problem in computer graphics and geometry processing with decades of research behind it. Many classical surface reconstruction methods require both point positions and normals as input. However, in practice, point cloud often come without normals or with noisy or incorrect normals, which can lead to poor reconstructions. For example, here is a close-up of Barney's ear from the previous slide. We can see from the picture when the normals are correct, screen person produces good surface. But when the normals are flipped or noisy on the right picture, the reconstruction results become highly distorted. There are some other surface reconstruction methods that don't need normals, but they often rely on densely sampled points to estimate normals. Unfortunately, in real-world scenarios, sparse data is very common. For example, these point clouds generated from scheduled curves are often extremely sparse. In thin structures like this helmet, point cloud sampled from the surface has a two-layer structure with very small gap in between. And in 3D scans, occlusions can lead to large missing regions, like this one. These practical sparse cases pose great challenges for current normal-free reconstruction methods. Now let's take a closer look at the helmet example from the previous slide, which has a very thin structure and very sparse sampling. Methods like winding number normal consistency produce a rough surface with visible artifacts and holes. And the method ISeg value constraints perform similarly, but in this case give us even slightly worse result. We also tested the relative person surface reconstruction, and the color on the surface mesh shows the distance error to the ground truth. The high errors are colored from the yellow to the red. So as you can see, the large portions of surface are yellow and red, which means the IPSR fails to handle this case. So to address these challenges, we propose a new method that can reconstruct surfaces directly from points without requiring normals, and is robust to sparse cases. Here is our reconstruction result. The surface is complete, smooth, and very close to ground truth. We built our implicit method upon a previous work called VIPS, which does not need normals and excels at handling very sparse cases. Here we show an example of extremely sparse point cloud from the doghead sketcher that does not contain the normal information. VIPS is still capable of generating a smooth watertight closed surface, demonstrating its strengths in handling this kind of challenges. And this is exactly the strengths we want to retain from VIPS. However, WIPS has high computational complexity. It can only handle a few thousand points efficiently. Our practical inputs generally are much larger than this. If we can scale up WIPS' ability to process much larger inputs, we might be able to tackle the challenging sparse cases mentioned above. Now let's take a look at the WIPS method. Hermite radial base functions are a classical way to represent implicit surfaces, and these functions are smooth interpolants that can effectively interpolate Hermite data values S and gradients G, given points X. In the HRBF function, A, B, P, Q are the coefficients that need to be solved. The symbol phi here is a kernel function, and in WIPS we use the triharmonic kernel, and the interpolant function then is called Duchamp's values S and gradients G, so that the Duchamp's interpolant function fits the data with minimum energy. And the energy contains two parts. One is the residual term that sums the squares of the Hermite data values S, and this is the residual term, and this energy term. The distortion term that measures the energy of Duchamp's interpolant. And fortunately, the distortion term is a quadratic, which simplifies the optimization process. To avoid trivial solutions, where all the values of S are 0, the gradient need to be constrained to have a unit length. The lambda value here in the energy function controls the balance between fitting input points and maintaining a smooth surface. When lambda equals 0, the input points lie exactly on the surface. As lambda increases, the surface moves away from the input points to achieve smoother result. And the matrix J in the energy function is ON squared matrix, which is the submatrix of the inverse of the matrix M. The M is actually the from the previous linear system. And this is a static quadratic optimization problem with constraints, and which can be solved with many existing optimization tools. However, this optimization has very high complexity. First, as we need to inverse the matrix M to build matrix J, and the matrix M is O(n) squared, and the inversion will take O(n) cubic 10. Furthermore, multiplying matrix J in each optimization iteration will take O(n) squared 10. So the problem is how can we reduce the computational cost and scale up WIPS to handle large datasets. Our motivation comes from examining Duchamp's interpolant in 1D, as shown in this diagram. The gray line represents the Duchamp's interpolant over Hermite data at points X, and the tangent lines represent the gradients. And we observe an interesting property. The Duchamp's interpolant over any interval between points xi and xi plus 1 is equivalent to the local interpolants over just these 2 points. So this means that Duchamp's interpolant actually can be viewed as a collection of local interpolants, each defined over a small interval of points. Additionally, we observe that total energy of Duchamp's interpolant can be expressed as the sum of the energy of these local interpolants. And we found out that using the summed energy to replace the global energy in WIPS can reduce the complexity to O(n). While Duchamp's interpolant in 1D has a clear piecewise structure, the situation is more complex in higher dimensions, and it makes it challenging to decompose it into piecewise structures. So therefore, instead of calculating one global interpolant, we generate local interpolants at the smaller regions and blend them together to approximate the global surface. And instead of calculating the energy of the entire global surface, we calculate the energy for each local interpolant and then sum that to approximate the total energy. And this strategy allows us to maintain the computational efficiency of the method while still ensuring a smooth and accurate surface reconstruction. And in higher dimensions, we define our local interpolants as Duchamp's interpolants over local subsets xi. Each subset contains a point xi and its natural neighbors. And for example, in this triangulation graph, the red points represent the natural neighbors of point xi. So using natural neighbors give us some advantages. First, each local subset overlaps with its neighboring subsets, make it easier to blend the local interpolants smoothly. Second, natural neighbors are adaptive to the density of points, so they work particularly well for non-uniform and sparse samples. And for points on the 3D surfaces, each local subset typically has O(n) size, meaning the number of natural neighbors remain constant. So this is crucial for reducing the complexity from to O(n). Yeah. Now that we have the local interpolant functions, the next step is how do we blend them together? We define our local interpolant as the weighted sum of local interpolants. Each local interpolant fits the Hermite data Si and Gi defined over local subset Xi, and is multiplied by its corresponding weight Wix. Where the weights are the natural neighbor coordinates. So how can we get those weights? Given a set of input points shown in the red, we first build a Bernoulli diagram as is shown in the dashed line. And for point X, it has a Bernoulli cell Ti. When you insert the new point X, it will form new Bernoulli cell T. And this new Bernoulli cell T will have overlaps with Ti. And so we can define the natural neighbor coordinate as the volume of the intersection between T and Ti divided by the total volume of T. And this blended scheme has several benefits. It produces C1 smooth interpolation even at the input points, unlike traditional natural neighbor interpolation, which is no C1 continuous at the input points. And it also can produce linear functions exactly if the Hermite data comes from the linear functions. So flat surfaces and features can be preserved without distortion. So to compute the coefficients of each local interpolant functions, we need the Hermite data values S and G, just like that in VIPs. We obtain these values by minimizing the energy function. But here, the difference is that we replace the distortion term with the summed energy of all local interpolants. And this change has big impact. Typically, each local matrix Ji involved in optimization is of size O1 rather than O(n). And this will bring down the overall computational complexity to O(n). And we call our method natural neighbor VIPs. And it defines the surface as a zero-level set of the global blended interpolant built over the optimized Hermite data S and G. So, and also in terms of the complexity, our setup with the denominator triangulation takes O(n) log n time, and each optimization iteration takes O(n). So, and they also assume that the local subset is constant sized. Here are some results we want to show. First, we want to verify that our methods retain the strengths of VIPs in handling very sparse and non-uniform points. To do this, we did some experiments on challenging cases, especially sparse cases with limited point numbers. And this is a torus sampled with only 1,000 points, all allocated along a few curves and leaving a large gap in the surface. And this sampling is extremely sparse and difficult for most of reconstruction methods. However, both our methods and VIPs were able to successfully recover a complete shape of the torus. And through the picture, we can see our results is visually almost identical to VIPs, demonstrating our methods can preserve its robustness even in undersampled regions. However, for many other state-of-art methods, they will actually fail on this case. Here is another challenging example, a Bhattad model with only 1,000 points sparsely sampled across the surface. And this case is difficult because the Bhattad has very thin layer structure. Its thickness is smaller than the sampling distance, making it easy for the surface to collapse and break. But though our methods and VIPs can still perform the good result and very close to the ground truth. However, some situation, other methods would fail on this case as well. Yeah. To further test the capability of our method, we applied our method to larger and more complex cases that are beyond the capability of VIPs. But our methods can still handle them while maintaining the robustness to sparsity. And this case is a highly complex case, a Mobius net model which contains more than 1,000 genres. And we sample 100K points from the surface. Despite the high numbers, the sampling is still sparse due to the extreme geometry complexity. And our method successfully reconstructs surface with fine details, closely matching the ground truth geometry. In comparison, the WNC fails to capture the many important structures, and the IPSR produces a very noisy and cluttered result. And notably here, our reconstruction preserves the generous count most accurately among all the methods. We also test our method on real-world scan data with missing regions, which is a common challenge in practical applications. In this case, the gaps between around the legs are particularly difficult to recover. Our method successfully reconstructs the missing parts, producing a surface closely matches the ground truth. In contrast, other methods incorrectly filled gaps between the legs, leading to unrealistic results. Okay. Now let's talk about timing. First, we compare our method with VIPs to evaluate the computational efficiency using the Q10 model. We increased the number of input points from 500 to 4,000. As you can see, the running time of our method remained almost constant. No more than just a few seconds, while VIPs slows down dramatically and reach up to 10 minutes for just a few thousand points. And this demonstrates our method scales much better and can handle larger point cloud more efficiently. Yeah. To further validate our scalability, we use a more complex model, the Dragon model, to test our method on 10 samples ranging from 100K to 1 million points. We record the runtime for 2 stages. The normal estimation step is shown in blue, and the surface generation using our interpolant function shown in orange. Our methods typically, other methods typically use screened Poisson surface reconstruction, which is pretty fast, so we exclude their timing from this graph. As we can see, our timing increases linearly with input size, and the optimization timing is comparable to other state-of-the-art methods. While we may not be the most efficient method, we achieve better reconstruction quality, especially in handling challenging and sparse sampling cases. So in conclusion, our method performs implicit surface reconstruction directly from points without requiring normals, making it simpler to apply in real-world cases. It's also more robust in undersampled regions compared to many existing methods, handling sparse cases without producing artifacts. And importantly, it's scalable to large point clouds, such as inputs over 1 million points, which makes it practical for real applications. Of course, we also have some limitations. The scalability of our method depends on the size of natural neighbor for each point. In practice, this is typically small, it's O1. But for the worst case scenarios, it can go to O(n). We also observe some slow convergence for large lambda and when the input data has higher noise. Yeah. That's all. Thank you. Yeah. Any questions?
Thank you, Jianjun, for the interesting talk. Are there any questions?
Yeah, thank you for that talk. I'm curious what I guess trade-offs do you observe since you approximate the global energy of VIPs with your global energy. Do you have any sense of what trade-offs you observe in the reconstruction quality between you and VIPs?
Trade-off between VIPs. I think first we are much faster than VIPs. We use some approximation strategies. There are some small, there could be some cases where there are some small errors. I mean, we may lose some quality compared to VIPs, but generally it has very close match to the results. Yeah. But with our speed is much faster, you can see from the graph. Yeah. Thanks.
Okay, I have a question. You showed that you can handle sparse points, but I wonder what happens if the point cloud is noisy or even has outliers. What happens in this case?
Yeah, for the outliers, because our method have a assumption that if points on the surface around the surface or very near to the surface, the natural neighbor size will be constant size. But if you have many outliers, then it would make the algorithm hard to deal. But if you have only a few, it may be handled. You may be able to handle, but it depends on the input size, how much points you are offset from the surface. And also, when you are having higher noise, you need large lambda values to optimize. And for our current method, it will take, because you need to propagate from each subset to other subset to optimize the results. So it will take a very long time to get final global result. So that means higher lambda values means higher optimization timing. Yeah. So. Yeah.
Okay, I understand. Okay, let's thank the speaker again. This concludes the second session of our day. Now we will have lunch, and you have tables here that you can sit and enjoy lunch. We will reconvene in 1 hour at 1:30 p.m. to have our third and fourth session. Thank you very much. Okay, now we'll continue with the sessions, and I hope you enjoyed lunch. We'll have the third and fourth sessions, and they will moderate the coming session.
Thanks, Itai. All right, so this next session, session 3, will be on generative modeling. And our first speaker will be Selena Ling. She is a PhD student at the University of Toronto. And her presentation is titled Improving Optimization Techniques for 3D Generation and Manipulation. So yeah, take it away.
Okay. So hello everyone, my name is Selena. I'm a PhD student at the University of Toronto working with Professor Alan Jacobson. And today the topic of my talk is improving optimization techniques in today's 3D generation and editing pipelines. So in today's world, we all want to work with neural networks in many cases, same in the geometry world. Novel geometry representations and optimization modules are invented to better work with machine learning pipelines, like differentiable rendering techniques to optimize geometry against images, neural radiance field, which defines a fuzzy geometry underlying it, and neural implicit surface-based rendering methods like you see here. So these novel ML-friendly geometry optimization algorithms make 3D generation easier, like the work here, which you must have seen over the past couple of years. These work distill the knowledge in the powerful 2D diffusion models into the 3D optimization process and generating novel 3D shapes from text prompts. And the brief add-on kind of our recent work presented last year at Sirui 2024, those techniques enable us to build a pipeline to do interactive controllable 3D editing. So now with some background, I want to emphasize the scope of my talk today is not a traditional concept of shape optimization, which usually can refer to a huge body of work related to topology optimization that has its own set of methodologies and representations. In my talk today, I'm more interested in the emerging trend of adopting popular optimization methods from machine learning for geometry problems, like what you have seen in the works mentioned in the previous slides. So many past work already kind of look at this emerging domain, such as the large step for inverse rendering paper. So it proposes to construct a gradient preconditioner leveraging the mesh structure during inverse rendering to kind of elevate the bad minima with exploding self-intersections, which you'll see here, that typically occur in differentiable rendering. Another work at BENF kind of look at neural sign distance optimization and proposes to leverage a grid structure in the input domain during training to enable level of details reconstruction of 3D shapes. So inspired by these works, the question I'm interested in asking is, how can we better make use of the structures that arise within these geometry optimization processes to improve convergence and the final quality? So I will start by briefly talking about my first work in this area, vector atom for rotation equivariant geometry optimization. So atom is one of the most popular optimizers for neural networks. We start to see an increasing use of it in the context of geometry as well, such as this paper tackling a very classic geometry processing problem, and especially in differentiable rendering type of work like NeRFs. The original atom algorithm makes use of momentums to adaptively rescale the step size based on the per-scalar gradient stats to accelerate convergence, which lends itself extremely well to neural network grids as they exist in the structure of scalars. However, when atom is used for geometry quantities, such as for mesh vertex positions, the gradient can exist as like a vector structure, like displacement vector. And atom, this way, defined by scalars, introduces diagonal bias, as we shown here. It snaps the gradient vector into diagonal directions and introduces this kind of axis-aligned intersection artifacts. So we propose a very simple fix, which is just to take the norm of the entire gradient vector when computing the second moment. instead of doing component-wise operations, such that the vector gradients direction are preserved, and their magnitude is normalized as Adam intends to do. This small change has many geometric significance, including rotation equivariant optimization, and we just show some results in the context of inverse rendering. It effectively avoids self-intersection and improves convergence. So next, I will focus most of my talk on my most recent work, stochastic preconditioning for neural field optimization. It's a project from my last internship with NVIDIA, working with Milan, Alec, and Nick Sharp. So neural field is probably a representation that most people here are very familiar with. It is a special type of neural network that learns to map the input coordinate to its target representation values, which can be pixel, signed distance to surface, and density for volumetric rendering. And since it's mentioned, it has been adopted effectively for a variety of applications. Just to show a snapshot here, and you should look into the survey done by Melame for more details if you're interested. Essentially, neural field samples into some coordinate space and overfits to some target signal values. And this input domain is usually structured as a Euclidean space. So this structured input domain gives rise to many interesting applications, such as the level of detail reconstruction work that we saw earlier, and also some deformation work that other people did. So what else can happen in a signal defined in a Euclidean space? In our work, we noticed that one can define the blur operation that convolves the value at x with its neighboring value. Here we show the formula for a Gaussian blur. And this formula can be interpreted as the expectation of a function value with an offset term delta drawn from a normal distribution. So simply perturbing query locations according to a normal distribution gives a stochastic estimate of the blurred neural field. Although we mainly target neural field, this observation concept applies to other forms of field representation as well, such as grid-based field and others. So before I introduce more details about the method and results, we kind of introduce the concept preconditioning to make sense of the title you see here in every slide. Preconditioning is the application of a transformation called preconditioner that conditions a given problem into a form that is more suitable for optimization. So most commonly, you will see it used in numerical solving methods in the form of solving a system like AX equal to B. You transform the input X into Y by multiplying it again with a matrix N such that we turn an ill-conditioned system into a system with better conditions for easier solving. Intuitively, a preconditioner makes the landscape easier to navigate for first-order optimization methods to improve convergence. So now go back to the problem context earlier on neural field. By simply adding a stochastic offset on input X, we approximate a blur operator on the field that we are optimizing, and therefore can be seen as a form of preconditioning, which will also make more sense with more results later. So now you probably could have guessed what our method is. Yes, we propose to simply perturb the sample location according to Gaussian noise to instead of query at the location x plus delta with delta drawn from a normal distribution defined with a standard deviation alpha. Otherwise, the rest of the training, sampling, loss evaluation, and auto differentiation are all performed as the same for the representation of the task at hand. So first important aspect of our method is we only query one stochastic estimate at a time during training, so there is minimal additional cost and extremely easy to implement with basically a few lines of code. Secondly, motivated by coarse-to-fine optimization, we anneal the scale parameter alpha from some initial non-zero value to 0 during training, as you can see here in the figure. Training with a constant alpha effectively blurs the image that you learned with the neural field, with the scale parameter alpha controlling the amount of blur. So next, I will just show some results to speak for the method. So the first task we apply our method to is the surface reconstruction task from point clouds. A neural field such as neural sign distance function has been quite effective for this task, which has a wide application in self-driving, robotics, and heritage preservation, as there's often the need for surface reconstruction from light-up point cloud. More specifically, we'll adopt the loss function from the state-of-art method Siren and experiment with a variety of neural field architectures, including the ones that use hash grid encoding with Fourier feature encoding and triplane-based encodings. Note that the different type of encoding introduces very different kinds of artifacts for this particular task. So hash grid is very often you see those kind of floaters due to the overfitting. And with Fourier feature, we usually see this kind of repetitive jagged surfaces around sharp surfaces. And with triplane-based feature, the one we adopted here, we see missing surfaces. But training with stochastic preconditioning, as we described earlier, kind of gets rid of those artifacts in all cases. And we noticed that our method is especially effective for neural field fitted with hash grade encoding, as we talked about, which often has this flowchart artifacts that we highlighted in orange here. With stochastic preconditioning, we easily arrive at the result without such flowcharts. We also experiment with neural surface reconstruction from images. In this problem context, one learns a neural sign distance function from images via implicit surface-based neural rendering algorithms. Many methods are proposed for this task, and we specifically experiment with one of the most widely used one called News. We measure both the PSNR for the render images and the chamfer distance between optimized surface and the ground truth point cloud for evaluation. Both are improved with our method, which is to simply perturb the input according to a schedule during training. Regular News comes with Fourier feature encoding. We again replace it with the state-of-art encoding hash grids and observe even more improvements, which align with our observation results earlier. Neural is another state-of-art method that you probably seen earlier from previous talk that built upon News with a specialized hash grade unlocking, coarse-to-fine training scheme, and other techniques. And our method introduces improvements here as well. We especially want to emphasize our techniques makes the underlying method much more robust to hyperparameters when it comes to tuning the overwhelmingly many parameters associated with hash grid. As you can see here in the table listed in the original paper, the range of values for each hyperparameter is large, and one might need to tune for each specific scene you want to train the network against. However, with stochastic preconditioning makes the training much more robust to the hyperparameter choice. Here we experiment with a range of hyperparameter choices and plot a histogram of the PSNR scores. So the baseline, which is the purple here, basically fails for most of the hyperparameter choices. But with training with stochastic preconditioning, many of them succeed. And since we're talking about neural field optimization, we do not want to miss out on neural radiance field. More specifically, we experiment with two especially challenging optimization scenarios for which our method improves. One is the few shot NeRF optimization, which is to fit NeRF against very few images, like 3 to 6 images. Regular training, as you see here, catastrophically fails. Yet, leveraging stochastic preconditioning for a coarse-to-fine training scheme greatly improves the result in this scenario, which we show more results here. Another NeRF optimization scenario we look at is ReLU field. So usually NeRF is optimized with MLPs, but the training time is long. And ReLU field introduces an interpolation-based, grid-based field representation that is faster to optimize, that matches the quality of regular NeRFs. So as you can see in this animation here, which I unfortunately didn't label, but you can kind of tell they train with this like staged coarse-to-fine mechanism, which is they use a progressive finer set of grids to optimize for this representation to avoid overfitting. If we remove this staged progressively finer grid-based optimization scheme, which we call a hierarchical training scheme, the fitting basically fails with this kind of flowchart artifacts. But if we add back our stochastic preconditioning, you can see also successfully fits to the ground truth image. And here I show more results. You can click for this particular method that we're testing our method on. And this concludes my talk about this particular work. And please check for an official paper release on my website for a paper release soon. And next, I want to briefly talk about future work in progress that also falls into the same problem domain that we are interested in, of improving geometry optimization. As we talked earlier, neural implicit surface function is an important type of neural field representation that enables surface reconstruction and novel view rendering like News. With it and any other implicit defined surface, there's often the need to do sample uniformly on the level set. For both improving the optimization, like some earlier work have tried to do, and also deformation, and also just surface quality evaluation, because we often use chamfer distance that requires a uniformly sample set of points on the surface for computing. And the most common approach for this problem is to extract the mesh via a Martian cube algorithm and sample on the mesh, or rejection sampling in the bounding box. Both are quite expensive. And there's some other method that aims for the same task as well as with its own drawbacks. And we are interested in finding a novel method for this task that samples uniformly on surface and much more efficient than these methods. which can inform us of the intermediate geometry during geometry optimization and improve the final quality. So now concludes my entire talk. Thank you for my collaborators and thank you for listening.
All right, thank you so much for that awesome talk. I wanted to open the floor to any questions.
I'm wondering if there's any connection between the stochastic preconditioning and other cross-to-fine strategies, such as like we first train a neural field from a lower resolution of images and then increase the resolution step by step. Is there any connections or is it equivalent?
Yes, exactly. Like, let me go back to that slide. So, for example, this particular experiment ReLU field, like you can observe, they're basically training with like a very coarse grid first, and they're also training against a very coarse ground truth image first, and then they slowly like upsample it. But the thing with this is like you have to design this. Like basically, you can see like for every stage, you kind of have to tune how many steps you go for that stage, and usually you converge already, but you cannot find the right tuning parameter to train for that particular resolution. Yeah, so you can kind of see like if our method effectively achieves the same coarse to fine mechanism, like just kind of provides a more straightforward way. Yeah, but I wouldn't say they're equivalent.
Okay.
Yeah, because we're basically blurring the field during optimization, but they're basically training against a blurred field as ground truth.
Do you need to design the strategy of a annealing strategy during the optimization
Yes.
for the stochastic preconditioning?
Yeah, we experiment pretty extensively, and in the official paper, we'll provide like our empirical choices of the optimal schedule for this parameter. But yeah.
Awesome. I think that's all we have time for now. We can ask more, I guess, after the session. But thank you. If we could thank our speaker one more time. All right. Next up, we have Sirui, and he is a PhD student at the University of Illinois, Urbana-Champaign. And today he will be talking about scalable physics-driven generation of human-object interactions. So yeah, once you're all set up, take it away. Thank you so much.
Awesome. So hi everyone, my name is Sirui and I'm a second year PhD student at UIUC. And I'm very glad to be here to introduce our recent progress on dynamic 3D human-object interaction generation.
Microphone, sorry. Right here.
So our research aims to develop models that can create extended and realistic 3D simulations of human interactions with a diverse array of everyday objects. So being able to generate such an animation or simulation is central to developing like human-like interactive agents and digital humans, for example, gaming, films, and virtual reality environments for education and entertainment requires lifelike HOI simulation to deliver immersive experience within the virtual world. And also the simulated data accurately reflect real-world human interactions could be used to drive imitation of robots, reducing the need for the real human demonstration. But the simulation like the one we are talking about is hard to achieve. So unlike the image or video generation, human-object interaction simulation faces inherent and unique challenges that current state-of-the-art methods struggle with. So first, the limited scale of motion capture data sets resulting in insufficient object diversity and a narrow range of actions, limiting the models to scale up. And second, ensuring the physical realism, especially contact accuracy, is important, but challenging for generative modeling, and it becomes even more difficult if dealing with noisy artifact-prone mocap data, which is quite common in existing data sets, as shown here. So relying exclusively on mocap data confines models to idealized scenarios. But the reasoning about holistic environments, incorporating the geometry, semantic, and goal-related context is often beyond the capability of existing models by learning only from mocap. So we first dive into synergizing large models to address data scarcity issue and incorporating contextual reasoning So in our work InterDreamer, we leverage them to do text-driven human-object interaction generation. So to achieve synergy, our key observation is that the interaction semantics and dynamics can be individually harnessed and ultimately composed. The semantics of interaction can be harnessed from a large language model with the pre-trained motion generative models for context-aware motion generation. But these models can offer high-level motion semantic modeling. They lack crucial low-level dynamics knowledge. And we address this by developing a world model that predicts the subsequent behavior of the object driven by the human interaction. So remarkably, our model of synthesizing large models generates results that demonstrate high-quality interactions with longer and more complex text descriptions, and shows proficiency in synthesizing interactions involving dynamic contact, such as handover. And next, we go to the challenge of physical fidelity. And one of the improvements that can be attributed to a simple but important observation, while overall human-object interactions might appear complex, the motion of an object relative to its contact often exhibits a straightforward and predictable pattern. So for the motion clip showing here, the relative motion on the right revolve around the static axis or remain almost static. So we draw inspiration from this observation. In our work InterDiff, we integrate coordinates transformation to formulate a classifier guidance into a diffusion model that synthesizes the interaction with improved plausibility. While these kinematic masses can generate a wide variety of motions, the results are not guaranteed to be physically valid. So in our recent CVPR highlight paper called Intermimic, we aim to address these issues by distilling imperfect kinematic reference through physical simulation and control. So essentially the task is defined as given any reference that can be extracted from mocap or video, we want to synthesize the physical motor skills that can reproduce the motion showing on the left. So essentially, human-object interaction imitation in the simulation is challenging for the two reasons that we've discussed, the mocap imperfections and the difficulty for scaling up. And we aim to utilize rich yet imperfect motion capture interaction datasets to train a control policy capable of learning diverse motor skills while enhancing the plausibility of these actions by correcting errors. And our approach is grounded on the key insight of tackling the challenges of skill perfections and skill integration progressively. So we implement a curriculum-based teacher-student distillation framework where multiple teacher policies focusing on imitating and retargeting small subset of interactions. And the student policy integrates these skills from the teachers. So essentially, the objectives of our physics-based interaction imitation is to assign a series of actions that is a PD target or the drawing torque applied to each drawing of the humanoid body so that we can define an entry function called H, and our goal is to minimize this entry function subject to the equation of motion, which is basically abstraction of the whole simulation process of forward dynamics. And in this case, the animation task is rewritten as a constraint optimization problem, and we leverage reinforcement learning to solve this problem. And basically, we use the teacher policy to do the imitation as perfecting. Essentially, we utilize teacher policies to unify all training data into a canonical human model by embedding the HY retargeting directly into the imitation, the whole optimization process. This is achieved by reframing the policy learning to optimize both the imitation and retargeting objectives. And second, our teacher policy refines interaction motion through learning from it. As accurate contact dynamics enforced by a physics simulator inherently correct inaccuracies in reference kinematics. And to support this, we also introduced some tailored contact guiding rewards and optimize the trajectory collections. So a major hurdle in scaling motion imitation is the sample inefficiency of the reinforcement learning, which can lead to very long training times. So our teacher-student approach mitigates this through a space-time trade-off. So multiple teacher policies are trained in parallel on smaller, more manageable data subsets, and their expertise is then distilled into a student policy. So essentially, by leveraging teacher rollout, we effectively distill raw mocap data into a refined HOI references, with a unified embodiment and enhance the physical fidelity. And this refined reference guide the subsequent student policy training to reduce the negative impact of errors in the original mocap data. And we begin with a demonstration-based distillation to bootstrap the PPO updates, reducing the reliance on the pure try and error, and enabling more effective scaling. And as training progresses, the student gradually shifted from heavy demonstration guidance to increase the reinforcement learning updates, and ultimately surpassing simple demonstration memorization. And we'd like to highlight some results. So our policy can do returning, go beyond human-to-human, but also human-to-humanoid with a very different embodiment. So this visualization shows that we enable a unique retrieval humanoid robot with inspired dexterous hand, exhibits scalable interactive skills. And the additional benefits of our method is the ability to enhance mocap data with greater physical plausibility, simply by learning from it. So here we demonstrate that our method effectively corrects the contact floating issue presented in the original mocap data. And similarly, our HI simulation rollout eliminates the contact penetration issue found in the original mocap data. And for severe jittering observed in the mocap system, our method also produced significantly smoother and more realistic contact interactions. And we leverage the same philosophy for curating and scaling out the data that we can use in our another recent CPPR paper called Interact. We aim to address the problem of data scarcity and contact artifacts presented in the ground truth data. And we collected over 20 hours of full-body dynamic interaction data with improved quality. And we believe such data is important for future research to advance the large-scale HOI learning and simulation. So to wrap up, human-object interaction animation is an emerging trend that pushes the boundary of digital and physical simulation. And we've developed like kinematic motion generation methods by integrating a diffusion model with a kinematic product that is iterative. We are able to achieve more realistic motion synthesis. And the use of contextual reasoning powered by large language models provides the necessary layer to understand and generate complex interactions. And equipped with a dynamics model, we can do HOI generation and simulation. And we also show that imperfect kinematic reference or generation can be perfect by the physics simulation control. And it also holds significant promise for real-world humanoid local manipulation. And finally, by addressing the long-standing challenges, we introduce a curated large-scale HOI data set and sets a new benchmark for future research in this space. And we believe together with these advancements, not only drive the frontier of animation, but also open up new opportunities in like robotics, gaming, and virtual reality. And that's all of the content. Thank you.
Thank you so much for that great talk. Any questions? I have one question. On the section when you were talking about this idea of like perfecting first and then scaling up, does that have any like effect on the diversity of the motion? Like does that, or is there like ways you correct for that kind of thing?
I think basically the correction would not hurt the diversity because we still use the same set of the mocap and it contains a large scale data like more than 10 hours and it contains like a very diverse interactive skills. So correction is generally just mitigating the contact artifacts like the penetration, the floating between the human and object surface, and also some jittering, probably due to the sense limitation or human object occlusion when having the motion capture pipeline. So essentially, we don't modify the data significantly. We just have the cleaning, and then we find out those teacher policies not only supports the data cleaning, but also like improve the scaling up by having the demonstration memorization RO.
Awesome. Thank you so much. Any other questions? Okay, we can move on to our next speaker. Thank you so much again for your talk. All right. So our next speaker will be Zhang, and he is a PhD student at the University of Chicago. And today he will be presenting on nested diffusion models using hierarchical latent priors. So yeah, once you set up, you're good to go. Yeah, we have time. So also let me know if you need help with that. I think it is. Yeah, it's on. You also can clip it to your shirt too. That's easier to hold it. Sorry.
Okay. Hi everyone. I'm very excited to present this work, nested diffusion models using hierarchical latent prior. This is a joint work with Roxy, Rebecca, and Michael. So nowadays we have seen this amazing progress of general model, especially diffusion model, which can generate high quality images and also the videos. Here I'm very surprised by the state-of-the-art video generation. It's can get a very detailed structure, also like physics, and follow most of the physical law of the real world. So to understand the diffusion model, let's temporarily move back from the exciting like generating images to this simple point data set. So in this data set, we just have 2 points in the 1D space, x0 and x1. And diffusion model basically have 2 process, one forward, one backward. In the forward process, we take the data point and add noise. So that's indicate. So here I'm showing this kind of forward process in the x-axis where this t indicate the noise level. So you can see from the left to right, you span this kind of support of the noise data. And then the backward process, essentially, we are training a diffusion models that take the sample noise data point, try to estimate what the clean data it is. So let's take this origin point example. So we can see during training, this origin point, with half a chance it could come from this x0, or with another half chance it can come from this x1. So theoretically, the optimal diffusion model will try to give the average estimations because that's if you train out to distance, that's guaranteed this kind of optimal solutions. But if you train with say like this kind of the red point from the topology, it's basically exclusive come from this S1. So essentially, that means even the 2 data point at the same noise level, but they have a different data structures with respect to this original data point, they have different solutions. So that means the diffusion model is highly dependent on this kind of data structure. Also, they have very severe this kind of averaging effect, which is okay for this kind of simple toy data set. But now we're talking about images, these high dimensional, very complicated structures. So now we're still like doing the same thing. We have some noisy images. We want to try to train a diffusion model, try to guess what clean images it is. Because it's still like we're training everything using the R2 distance. So we follow the same philosophy. So essentially it will have some averaging effect. So, but the problem of images is that we're doing this average in the pixel space, which doesn't make sense because you see, that's the optimal solution will essentially some like weird averaging of some images, which doesn't make sense at all. So now people may say, if we're not doing this diffusion on the image space, we're not doing say latent diffusions, we are using some like pre-trained VAE, which makes the generation easier. But actually we are doing this kind of analysis on the VAE space. So what we're doing here is basically we take input images and we're querying some nearest neighbor using different resolution. So you can see still like this kind of nearest neighbor is still very similar to the image in terms of like low level gesture or some low level context. They're not actually give some meaningful or semantic corresponding. So that means if you train the diffusion models on the Latent space, you're still averaging this kind of textural level space, which also like end up with some like non-meaningful target. So that means instead of training the diffusion model on some like low-level textural space, you want to train a diffusion model in a more meaningful space. So that in that space, average is more meaningful. So you can see here we're showing this nearest neighbor using similar analysis procedures to show nearest neighbor using clip. We're showing different like resolution of the clip features, and you can see all these kind of neighbors are kind of semantically meaningful. So that means if you try to run general models in this space, you still get average effect, but averaging is more makes sense. So that's the only difference. So following this analysis, we instead of doing this kind of diffusion in this left part, doing this kind of scale space diffusion, we would prefer to do the generation on the right path, which kind of following some like underlying semantic hierarchical structures, which also like consistent with how human perceive or understand this word. Also like maybe it's also following this how human generate images, because if you ask a human to draw images, we don't do the pixel-wise denoising. We first draw the sketch and then add the details. So basically on the right path basically more consistent with how humans do this kind of generation task. So with that in mind, we design our models that's explicitly following this kind of hierarchical semantic structures. So what are we doing here? We take image and we do this kind of patch-wise operations. So basically we have image and we split image into patches. And we feed each patch to this pre-trained video encoder. Click Daniel, you name it. So that's each, the output from each patch will like capture some like global part, some local part of the representation. So if we do this kind of at different scale, for example, at the top, we just take the entire image as a single crop. So that means the vector we get basically some very high level abstract features of the images. And then if we go down, we like have we split image into two by two patches, and then we get like this kind of local representation for each patch. So for example, you can see the top left is basically only have the information about this kind of the sky, also this tree. It doesn't have the information about the building. So basically, it just focuses on a very specific part of this images. So we have this kind of nice like decomposition of semantic meaning. Then if we follow the path, eventually we build in this kind of hierarchy from very top to the end, which is the pixels. So those are the target for our generation paths. Then what we do is train the general models to follow that path to generate images. So at the very top level, we have diffusion models that try to generate this kind of very high level vector representation. Then we can keep doing that, where we train the second level, conditioning on this kind of high level representation to produce this kind of mid level representation. Then if we keep doing that, we have this final diffusion models that generate pixels, but it's conditioning on this kind of all previous generated features. So that's basically mimicking this kind of how we generate images following this kind of semantic tree. Okay, this sounds simple and should work, but actually we find a very like surprising effect, which we call bypassing. So what is it? So we find actually, even though the very top vector is just like 1 by 1 by 128 vector, is very high, very low resolution compared to the entire pixels, but actually it's have very rich information about the images. So that means the network can just use whatever the top vector encoded to reconstruct images, bypassing whatever our predefined hierarchical paths. To show that, we train a model that directly take the Z3, it's a very abstract vector, and ask the model to directly generate the images. So we can see, even though Z3 is very low dimension, but it can still almost reconstruct everything about images, even the details. So that means we need to do something to make sure the model doesn't do this bypass. So our solution is to add noise. So what does it mean? We still have this kind of condition diffusion model, but it's conditioned on some noisy signal. So this noise will remove this kind of details of the vector. So you can see after adding noise, this generated images is most likely following this structure of the image, but not exactly copy the details. So that means the model has to leverage this intermediate path, intermediate like Z2 features to reconstruct images. So that means that would effectively prevent the model from doing this bypass. So that would arrive to our final pipeline. So we still have this kind of hierarchical condition general models, but we're now conditioning this we're adding noise to these condition features to prevent the bypass. Another benefit of this kind of adding noise to this condition signal is that during training, we're using the ground truth or the oracle feature from produced by the local variant encoder, but for generation, we actually generate this kind of features. If you're building this hierarchical system to more level, the gap between training and testing will be increasing. So that means you cannot train very deep models. Adding this noise will like to mitigate the gap between training and testing, because the condition signal is essentially it's very noisy signal, so it doesn't care. Maybe there's a gap between training and testing, but this noise will like help to remove such gap. Okay, now come to this performance, because we want to train a powerful model, so we compare with the popular big models. So now we are comparing on this kind of standard image net 1K benchmark 256 resolution. Those are very standard large scale data set. And we're comparing with the DIT XL2. Those are pretty huge models. And our models only have a quarter of the total flops. Here, the size of the diameter of the dot indicate the flops or this computing complexity of the models. So we have a very smaller models compared to our compare method. But our models, the green dots, actually has better performance compared to this kind of blue one in terms of the training speed, conversion speed, also the FID. Also, we also compare with the recent state of art. Also try to integrate the feature representation into general models, which is called REPA. And we find actually our models, the green dot, still outperforming them, even though we have only have 1/4 of the total compute. Also, most surprisingly, our unconditioned models, that means during generation, we are not providing any condition signal. It's much more complicated task. Or like the red dot actually outperforming this kind of state-of-art bigger model with conditioning. So that indicates the effectiveness of using features to generate images following this kind of hierarchical path. So on the right, we're showing we can scale our model by building more hierarchy. So on the we're showing this plotting the model at different level hierarchy from 2 to 5 level, and which with increasing with the flops showing on the x-axis, but actually we can see this consistent improvement of the FID. And all this kind of we are comparing with the baseline, which has a similar computing complexity, but we are significantly outperforming them. Here is the kind of visualizations, and we're showing we have improved quality with deeper nesting. And another application of our models, so we can have this kind of controllable hierarchical generations. So what we're doing here, we can generate images by sharing some piece of the features. For example, all these kind of second row images are sharing this kind of high-level feature with respect to this kind of top left corner images. So you can see all the images share some high-level content, but they're kind of differ in some mid-level structures. And we can keep doing that by sharing, this kind of high-level, mid-level feature and generate images with only different on this kind of detail structures. So those are kind of this the final row. You can see those are pretty similar, but they're still different in terms of detail structure. So that indicates that our model can actually to replicate to respect this kind of hierarchical structure of the images. Here is another benchmark on this COCO dataset, which is more complicated datasets. Here we are comparing our model with a very huge model, closed source huge model, which has 7 billion parameters and training with much more data. Our model only have 2.5 billion parameters, much fewer parameters, and only train very limited data. But actually, we are better than this model. So that indicate the effectiveness of our designed hierarchical models. Okay. So this is an abolition study. So here we are comparing the setup of adding noise of training the hierarchical model without adding noise. So those are this kind of the red column, and so basically you can see this model can struggle if you increase this small level. But if you train the model with some noise to the condition, you can see it's better. The model can scale better to deeper nesting. So that means that noise injection is key for scalability in our models. Okay, so in this work, we're basically investigating the questions of can we use the representation to improve general models. So what about other directions? So can we learn better representation from general models? The answer may be positive because all the kind of general model, including diffusion model, including autoregressive model, you can group them as the denoising autoencoder, which is kind of very classic model to learn representations. But in this work, we are trying to see how should we further improve the representation of the general models. This is a joint work with Roxy, Will, Becca, and Michael. So let's firstly to see where is kind of the current state of our general model in terms of this benchmark. So I'm here comparing two very popular representation models, mass autoencoder and MoCo. Mass autoencoder is kind of very representative model from generative models, and MoCo V3 is kind of a classical contrastive learning method. So in this kind of standard image that 1K benchmark, you can see there's a huge gap in terms of if you measure the quality representation using the k-linear saver or linear probing. There's a huge gap. So this work basically try to investigate what's happening and how should we improve it. So our design is kind of motivated from this kind of architecture design. So we have been paying attention to this kind of residual connections, which kind of golden standard for network design. And it can it allows us to train with different models, and it can make the gradient backpropagate efficiently. But there's the issue in the context of this kind of asteroid general models. So because the goal of the representation is to learn some abstract low rank features, but because of this kind of presence of this skip connections, so you can see this kind of the skip path will always propagate in this kind of low level features from the beginning to the end. So that means whatever you learn at the end of the encoder will have some sort of substantial portion of this kind of low level features. So that means whatever you learn at the very end is kind of mixing of high level and low level features. So you can see we realize this representation from the mass autoencoder models and using the color to indicate the feature similarity. So you can see this kind of the girl and the umbrella and the bush behind her, they have the similar color. So that means the model think those three different categories should have a similar feature. Maybe the model using some pixel neighboring to encode feature, but those not the feature what it want. Also, you can see the ground. You can see the magenta color here. That means that's corresponding to the shadow of the ground. So that means the model is very sensitive to this kind of low level lighting or style which we want our feature to be invariant to, because for high level understanding we really want to learn the concept of ground rather than the concept of ground plus the shadow. So our solution is very simple. So what do we do? Because the residual connection is an issue, so we propose to just decay the effect of this residual connection. So what we do here, we introduce this kind of decay factor, which is some constant, some scalar between 0 and 1, and then we apply this alpha to this skip connection. So that will decay this kind of contribution of residual connection. We also design some symbol scheduler so that it will decay from the beginning to the end. So at the very end, you have much higher decay. So then that means the features is more to not be harmed by this kind of shallow features. So this is kind of very simple. It doesn't introduce any learnable parameters. But you can see from the visualization, it's immediately improve the feature qualities. So in the benchmark we talk about, so you can see just introducing this decay factor, this significantly improve the representation learning of the mass autoencoder model. The only thing we change just adding the decay factor. You can see the improvement is huge, and effectively close the gap toward this state-of-the-art contrastive learning method. Moreover, we also apply our method to the diffusion models and evaluate on this kind of large-scale image that 1K data set. We also see a huge improvement in terms of image generation qualities. So you can see on the right, we're comparing the generated images. So we can see our method basically to improve this kind of coherence of generated object. So maybe that's the attribute to where our model learn better feature internally. So we also do the analysis on different scale of models. We can observe the similar behavior across all this kind of from smaller model to bigger model. So that means our design can be scaled with bigger models. Okay, so I will conclude here. So thanks for your attention. I'm here. We're happy to take any questions. Thank you.
Hello. I'm curious about the first paper and specifically the result you showed ablating on the different number of like hierarchical layers.
Okay.
To what extent can you attribute like the increase in performance to parameter count, sheer parameter count versus increasing that level of hierarchy?
Yes. Yeah, that's why we have the baseline. We also like try to increase the baseline to have a similar computing complexity for fair comparison.
Okay.
Okay. So that's why you can see the baseline have the similar flops as our like the 5-level system.
Any other questions? I had a quick one on the first graph actually. So you had mentioned like the unconditional problem is harder. Do you have like a sense of what like maybe one of these baseline methods would give in terms of FID for like unconditional generation?
The for the blue dot, the DITXL2, their FID, if I remember correctly, should be like roughly 40. So it should be here, and we're here.
Nice.
Thanks.
Awesome. All right. Well, let's thank our speaker again. Awesome talk. So, our next speaker will be Zhang Chen. He's a PhD student at the University of Illinois Urbana-Champaign, and the title of the talk is Versatile 3D/4D Content Generation and Editing by Mastering Spatial Temporal Consistency. And for the microphone, you can just clip this on your sweatshirt maybe.
Hello?
Just clip it on my sweatshirt really here, and then the whole time.
Hello. Hello everyone, I'm Jiahao. It's my great pleasure here. So today I present the versatile 3D and 4D content generation and editing by mastering spatial temporal consistency. So generation and editing tasks in 3D space has become a hot topic in both academia and industry, and is still out of the capability of large language models. So my research interest lies in this direction with previous research projects, including 3D ROM generation, training-based and training-free 3D editing and 4D editing, and finally the video-guided scene editing. The major challenge of this task, as mentioned in the title, is the spatial temporal consistency. So to understand this point, we will need to understand inconsistency with some examples. For spatial inconsistency, in a typical 3D scene editing task, the rendered view from the original scenes are intrinsically spatial consistent with the consistent appearance of the face and clothes from any viewpoints. When we edit to give him a plain jacket, inconsistent set of views will show different garment textures from different views, with a consistent one will show the same patterns as shown here. For a temporal inconsistency, let's just take 2 frames from this video, which is generated by the Sora on this technical report. So by comparing the same object in these 2 videos, we can clearly see that they are different, showing that this video is actually temporal inconsistent. So why do we encounter these consistency issues? One reason is the lack of global view, for example, as shown here, as the model is not natively working on the entire structure, but on a small parts, like only a view of the scene. These parts might be generated inconsistently. And another reason is that the lack of consistency awareness, that the model doesn't know the requirement of consistency. So just to generate some reasonable looking contents, but not necessarily consistent. So today, by introducing some of our previous projects, I will share various insights and methods to master spatial temporal consistency so that we can achieve high-fidelity editing and changing tasks. First, I introduce ConsistStreamer, a traditional work that can enforce 3D spatial consistency through training and working. So the task in this set of work aim to solve the instruction-guided 3D scene editing, to edit the scene according to the given instruction, like turn him into an elf, and obtain an edited scene like this. So a widely adopted solution is to distill a 3D editing signal from a 2D diffusion model so that we edit the rendered views from the scene with a pre-trained 2D diffusion, and then distill the editing results back to the 3D through a distillation and reconstruction pipeline. So the major challenge of this solution is the 3D spatial inconsistency when editing each view separately. As shown here, this is the same example as before, which will result in failures in editing, like some degradations or some blurred textures.
So to address this, we propose consistent streamer to achieve 3D spatial consistency in the 2D diffusion model, resulting in high-quality editing. So the core is 3 synergistic strategies: the structured noise, the surrounding views, and the consistency enforcing training. With these strategies, we designed a framework to achieve 3D consistency in 2D diffusion. So intuitively, the consistent editing result should also be denoised from consistent noises. So in this case, we explicitly control the structured noise to put the noise on the scene, so that when we can also render these 3D consistent noise maps. So in this example, we can observe that noise is also moving with this object in the 3D space, shown that it is on 3D. So this structured noise sets up a foundation of these consistent editing results, enabling a consistent denoising procedure from beginning to the end. So we also observe that, like in context of other views, leads to inconsistent and even sometimes abnormal editing results. Therefore, we constructed the surrounding views by surrounding a large main view with 16 smaller reference views, which is directly used the input to a 2D diffusion. So with this kind of text, and the correspondence implicitly reasoned by the self-attentions, we achieve desired consistent editing across all of the subviews. So we also deploy multi-GPU framework so that we can edit n surrounding views in parallel on 8 different GPUs, so that we can self-supervise the training on a diffusion model by first constructing a target through warping and averaging all these 17 n views, which are used to self-supervise the diffusion model, so that the model will be supervised to generate consistent results with the specific noises. So we also similarly self-supervise the predicted noise at each step to enforce a consistent denoising procedure from beginning to the end. With the framework composing all strategies, our consistent streamer will achieve high fidelity scene editing. So first, it generates this kind of high fidelity results with clear textures, bright colors, and high diversity. Not only in various portrait scenes, but also in complicated large scale and indoor and outdoor scenes like these examples. These are all indoor scenes, but can be transferred into various texture styles. So in this paper, we use the warping to find spatial correspondence, which is general strategy. We only have a steam model like NeRF and 3D.js, and we explicitly control the noises in the diffusion process to achieve consistent results and enforce the consistency through this training. So these ideas are not only working in 3D, but can also be transferred to 4D, leading to instruct 4D to 4D, the first instruction created 4D scene editing work. So 4D scenes means dynamic 3D scenes, or 3D plus time. And the objects are dynamic. And there is also in the 3D space, so it supports some novel view synthesis and rendering. This generation of 4D scenes are much more challenging as it requires both spatial and temporal consistency simultaneously. So here we try to transfer the idea here. A 3D scene can be rendered to and reconstructed from multi-view images. Similarly, a 4D scene can also be rendered to and reconstructed from multi-view videos as shown here. So similar to 3D editing, we also perform per view edit for multi-view videos of 4D scenes. We expect that each video should be edited in a temporally consistent manner, like this. So to achieve this, we apply a sliding window method that edits the frame segment by segment. Similar to consistent streamers using warping to find spatial correspondences, we use optical flow-guided temporal warping to find the temporal correspondences and propagate the previous frames to the current frames in its interval. So that it leverages the insight of the self-attentions in the diffusion to use the augmented diffusion model to inpaint and repaint all these frames all together, obtaining the consistently edited frames. After editing each video, we will synchronize them with a frame-by-frame warp and averaging aggregation with both temporal and spatial warping frame by frame, so that we can obtain the spatial temporally consistent set of multi-view videos, so that we will be able to directly reconstruct it into a consistent 4D scene. Like this. So we can see here are two views. One from a moving camera and the other from a static camera. So we can say that they are consistent. This work achieves high-quality 4D editing results across various tasks, like style transfer, object-centric editing, and even performs well in these very challenging Google immersive datasets and also long-term scenes of up to 300 frames. So this is because we regard the 3D scenes as multi-view videos. We can successfully transfer the idea from 3D and use both temporal and spatial warping. One is depth space and the other is optical flow guided to achieve both consistencies. So these previous two projects are relatively traditional and complicated. So in the next work pro edit, I want to share the new insights that simple progression is actually all you need. So you don't need all of the warping, you don't need all of the training, you just need a simple progression. So here we will take a revisit of the source of inconsistency. This is our previous observation that we lack of these two things. However, in fact, inconsistency does not always exist even if both happens. For example, if the instruction is to keep original, there will be no consistency at all by doing exactly doing nothing in each frame. On the contrary, an ordinary editing task like giving him a head cannot achieve this because it can generate different heads. But actually, all of them are valid heads. It didn't indicate it explicitly in the prompt. So this leads to the fundamental source of inconsistency. An instruction can be interpreted in different yet plausible ways, so that different ways are applied on different parts or views, which leads to the inconsistency. So to be more specific, if we define the feasible output space or FOS as the set of all the possible output scenes in each task, the inconsistency is rooted in the large FOS of the task. So which we'll show here that in the keep original, the FOS just has a single size, but like give him a head, the FOS will contain many different heads. So our insight is to explicitly control this FOS. So we draw an axis from the mild editing with small FOS to a significant editing with large FOS. We aim to find an intermediate task subtask with the medium change and acceptable FOS size. So if we pick a point R, which is closer to the left, it corresponds to a subtask with its prompt and linear combination of the left side and the right side. So that its FOS will be significantly smaller, so you can see it's just this small segment, showing us a way to reduce the FOS size. So if we execute this subtask to a scene, it will converge to a single scene in the FOS in the subtask as shown here. So starting from this scene, if we just simply repeat this process, we will finally resolve the original editing task. But differently, each edited view will only be sampled from a smaller FOS. So you can see the last segment intersected with the give him a head is very low with the blue intersection, so that it will only converge to a very specific scene instead of many inconsistent scenes. So with this controlling, we achieve consistency through such a simple framework that we just need to decompose and progressively performing them without any training process, any correspondence finding, any warping or training or anything else. So this subtask decomposition can also enable aggressivity control, as an interpolated subtask can be regarded as a partial completion because it is like a linear combination of the original one and the edited task. So for example, we can have different versions of the ELF editing from just changing the eyes, colors, and ears to completely reshaping the head. So with such a simple pipeline, ProEdit can also achieve comparable high-fidelity results as Composite Dreamer, but it's much faster and simpler as shown here. It can also support this indoor scene editing. So by investigating the root of inconsistency and controlling FOS through subtask decomposition progression, we obtain a simple and effective progression-based framework that achieves consistency. So at last, I will introduce one of my very recent projects, the V2 edit or V-square edit, that leverages video diffusion models for scene editing. We talked about spatial consistency in multi-view images and temporal consistency in the videos. So one may already notice that there is one type of video that requires both the rendered video of scenes. So for these videos, the temporal consistency implies the spatial consistency of the scene. Therefore, a video generator or editor that can generate temporarily consistent videos are strong scene generators for this kind of are using this kind of videos. So following this insight, we propose the render, edit, reconstruct process. We first render the video from the scene to get this video below, and edit it and reconstruct it back to the scene to perform an editing or reconstruction. our generation. On the other hand, in the language of generative models, the editing is actually a generation task but conditioned on the original contents. So that there are two aspects of editing, the instruction fulfillment and the original preservation. Consider this task that make her ride a dragon on this riding horse image. And it's three different results. The left one will preserve the original one, that it even preserves the face of the horse, but it fails to fulfill this task. And the right one is the opposite. By balancing both, the middle one can be regarded as a valid editing. So therefore, the key is to achieve a good trade-off between these two requirements. However, as the editing is implemented as generation, the fulfillment can be easily achieved through unconditional generation that we just ignore the original content and generating anything freely. It will match some of the edited prompt. So this inspires us to focus more on design of this preservation control strategy. So for the video, there is no end-to-end instruction guided video editors like instruct pics to pics for the images. So we propose a training-free preservation control method here. Due to time constraint, I will omit the details. It contains some noise control and attention map control. However, as all of the training-free methods, it has lots of hyperparameters, especially we combine multiple of them, so that it will require lots of hyperparameter selection by default. Because different methods will perform differently, and also the task also requires different controlling strategies. For some challenging tasks, there are even no such set of hyperparameters. To address this, we bring back the idea of subtask decomposition and progression, so that each subtask will have a very simple form after decomposition with a smaller FOS, so it will be very simple, and only mild changes. So it allows a consistent preservation control strategy. Or in other words, we can literally use the same set of hyperparameters that can be used for all the subtasks in all the tasks. It means we can even completely omit the hyperparameter tuning. So with this framework, our V2 edit successfully performs this high quality editing for very challenging tasks, even like adding a fiery ring with some dynamics or changing a person to a Batman. So all of the baselines fails in these tasks, as shown here, that we can see that there are many artifacts and even unreasonable generated things. And also with this render, edit, reconstruct process, our V2 edit becomes the very first method that supports very challenging geometry change, like this parrot and lion example. That the parrot and lion are not just background, but they literally exist with precise geometry in the 3D space. And also for this clock, you can see that all of the hands of this clock are consistent in every of the frames. So all of these tasks are not supported by any of the baselines. Like for example, this parrot standing and this lion, they are not supported by any of the baselines. So the key insight is twofold: to achieve spatial consistency through temporal consistency in the video generative models, and conclude the two requirements of editing tasks. We also leverage the subtask decomposition to achieve a training-free method that even does not require any hyperparameter training. So I hope that this work could inspire more follow-up research of this direction. That is all for today, and thank you very much for listening. So please feel free to scan again. Any questions?
Thank you so much.
How are you measuring consistency?
So here, you mean consistency?
Like, like in like a traditional 3D render, like it's deterministic, and so the same frame's always going to be the exact same. And like you go back, like you project a grid, the grid's always going to be the same. But in these, like, you're doing complex shapes, so how are you making sure that they're, like, do you have a digital twin, or like, are you just eyeballing them?
So for the consistency, actually, when the editing happens in the case that have the significant geometry change, it will go into very abnormal results if there is no consistency. For example, for these videos, you can see on the left that these are the results produced by other video editors. So you can see that the video editor results might be good, but when reconstructing to 3D, it will be completely abnormal. So in the geometry editing task, this consistency is even the very fundamental prerequisite to get some reasonably looking things. So in other ways, we can use some like clip or some GPT evaluation, user study, or some, for example, if we can have the precise depth map, we can directly compare some of the pixels, and these are some metrics used in these papers. That's it. Very nice. Thank you.
Any other questions? All right, awesome. Thank you. Thank you so much. All right, so it's time for our final speaker of the session. This would be Notre, and she is a PhD student at Carnegie Mellon University, and today's talk will be customizing large-scale text-image models. While you're sitting, just like put that on. All right, take it away when you're ready.
Hi everyone, I'm Notre. I'm a PhD student at CMU, and I'll be presenting today our work on customizing text-to-image models. This was a joint work with Meta during last year's internship. So I guess nowadays we have a lot of text-based generative models, and I've listed a few of them down here. But notably among them, some of the open source ones are like Flux by Black Forest Labs or SD3 by Stable Diffusion, which are based on flow-based models with transformer architectures. These models, given any text prompt, like an action figure on top of a mountain with sunset in the background, can generate really nice-looking images while following the text prompt. But for a lot of applications, just having a text prompt is often not sufficient. Like, I might want to generate a very specific action figure like this character from Demon Slayer and generate that on the mountain. So I'll be presenting, this task is called subject-driven customization, and I'll be presenting our most recent work on this, which can take these images shown on the right along with the text prompt and generate outputs like this. But first, let's take a look at some of the existing literature in this field. Some early works on this, like textual inversion, dream booth, and custom diffusion, basically fine-tuned a particular token or all or a subset of model parameters on the user-provided images. But this process can be time-taking and doesn't provide a very seamless user experience. To address this, a lot of encoder-based methods were introduced next, like Elite, Grid Diffusion, E40, to name a few. But one of the main challenges with these encoder-based methods is we really don't have a data set for this particular task. And what I mean by that is that there's no existing data set which shows the same object in different backgrounds, lighting condition, and pose. So these methods are usually trained on standard Lion or any other text image data sets, because of which the performance is really limiting factor. But how can we get the training data set for the task? A usual approach which we have always taken is scraping images from the internet. But this is really challenging here because these images don't really come with annotations about the object identity present in the image. Another common approach can be to use existing video data sets. But in our initial analysis, we found that these videos often capture only pets and humans. And if we want customization to work on static rigid objects, these data sets don't provide a lot of background variations. So in this work, we propose to create a synthetic dataset using the existing capabilities of the text-to-image model itself. And basically here we are taking motivation from some of the recent works like Consistori, which given a text description of describing a particular character like an old man wearing a hat, can generate multiple images together while keeping the same character consistency but changing the background. There's another concurrent work like Story Diffusion, which has a similar approach to create character comic sheets with a consistent character. These works mainly utilize attention mechanism in the text-to-image diffusion models, and to understand that, let's have a look at how an image is sampled from these existing models. Given a particular text prompt like this metal drum with blue and pink stripes, we usually pass it through some text encoder like T5, extract its features, concatenate it with a current noisy estimate of the feature, pass it through a text-to-image model, and more specifically, here I've visualized a DIT-based model like Flux, and get a denoised estimate of the image. This process is repeated for some T-sampling time steps to keep on getting a better estimate to have a final image in the end. During the sampling process, in each forward call, we basically have a bunch of attention layers, and in each attention layer, the features are projected into the query key and value spaces, where each query attends to all the key spaces, calculates its similarity to all of them, and basically attends itself by doing a weighted averaging of a weighted sum of the value features, using this attention softmax over the attention matrix. To achieve consistent character generation, these works basically treat multiple images as being in a set and denoise them together. And during each attention layer, the query feature not only attends to itself, but also all the features in the other images as well. And specifically only the background in the foreground regions of the other images where the object is present. So this mask basically denotes where each query feature should be attending to, including itself and the other images. By having this shared attention mechanism, it promotes generation of similar visual features in the object regions of the image, which leads to consistent character generation. Let's look at some qualitative samples. Given the description of this Russian blue cat, the model can successfully generate a similar looking cat, and having this detailed description is really helpful in these works. But if we try this for a 3D rigid shape like metal drum with blue and pink stripes, we observe that the model struggles to create a very consistent 3D shape or multi-view consistency of the texture. In our work, we basically address this issue and propose to use promote multi-view consistency using 3D assets like observers. Given any asset, we render it from different camera poses, get its depth map, and basically send this as an additional condition into the generation pipeline, apart from the existing text prompts that we have, which describe the object and the background. Having this depth guidance ensures that the multiple images that are generated in the stack have some consistent 3D shape when viewed from different camera poses. To further promote multi-view consistency, we also store pairwise corresponding points in each pairwise image and also use that during the generation process. Basically, in each attention layer of the Flux model, we first take the features, warp the foreground regions of the first image to all the other images using this multi-view correspondence information, and then pass these features into the shared attention pipeline with a corresponding mask denoting the foreground regions in the other images. Having this depth guidance and warping now lets us generate images with more consistent object identity across these three images. In summary, our pipeline consists of creating a set of object descriptions either via observer's assets, where each observer's asset comes with its own object description, generating some background prompts corresponding to each of these objects where we used Llama or any other LLM to create these background descriptions, passing these to the text-to-image model with the depth and multi-view correspondence information, and getting the output, multiple outputs showing the same object but in like different background or lighting conditions. But this pipeline is still not foolproof, and we still need to have some aesthetic and dino score sampling to reject any bad samples generated by the method. These are some of the nicer samples shown here generated by our dataset after the filtering step. So we can see that the model is able to generate these same objects in different contexts. Now, given this dataset, we can now train an encoder-based method where, for example, in the previous slide I showed like 3 images. We treat the first one as the target and the other images as the references to be conditioned to condition the generation process on. And during training, for example, DIT-based model, we use the same idea which we used in our dataset generation, which is basically shared attention to condition the generation on the reference features. So each query feature now attends on all the features of itself and the features extracted from all the reference images to predict the final denoise, to predict the noise that was added to the original image. And the training loss is a standard reconstruction loss common in diffusion or flow matching frameworks. Once trained, we use a standard classifier-free based image and text guidance mechanism to sample images, which was first introduced in Instruct Pix2Pix, where we first get an unconditional estimate of the denoising image based on a negative prompt, which is somewhat of a standard practice now, and update it towards the image guidance vector and the text guidance vector. One issue that we found in this mechanism was that sometimes with high image guidance values, the images can get saturated and lead to some artifacts. To rectify that, we propose, because the issue was that the image guidance usually has a much higher norm on average empirically. So to resolve this, we propose a simple solution to first normalize the image guidance and text guidance to be with the minimum norm, and then scale them by their respective image and text guidance. Having this removes any of the artifacts seen previously. Now, given this sampling mechanism, let's look at some of the results obtained by the fine-tuned model. For example, for the toy car, we can now generate it on a sidewalk with a Christmas tree and lights. For this purse, we can have it on a coffee table with a cup of coffee beside it. It can also work with single images, like for the shirt, we can have it hanging on a wire with green fields in the background, or generate this can but on a beach. For the qualitative comparison, here I show a sample comparison with a concurrent method, OmniControl. For example, this clock, but being in a jungle. And our method can preserve the object identity much better while still following the text prompt similar to the baseline method. Similarly for this cat in a firefighter outfit, or this duck but with a blue house in the background. For 3 images, we compare with Itai, which is another baseline which can take multiple images as input for this task. And our method can again has higher fidelity results while still following the text prompt. We also compare quantitatively against all the baselines, and our method performs on par or similar when compared across different metrics and model scales. Finally, we perform a qualitative analysis of the effect of importance of dataset scale on the final model performance. So we train different models with different dataset sizes, varying it from 100,000, 10,000, and the full dataset scale that we have of 95,000 samples. And we observe that with increase in dataset size, we get much higher pose diversity and better image alignment with the target object. Finally, this brings to the future improvement point of the work. Our dataset quality can still be improved. It has some limitations. For example, sometimes because of high depth guidance, the images generated shows the objects hanging in the air, which is probably not very realistic. Another common failure case is that when the rendered objects have very high pose difference, there's not much overlap for the warping step to align the features, and this can lead to inconsistent object identities. And this brings to the end of my talk. Thanks to all my collaborators, and if you're interested in the work, check out our webpage, GitHub, or demo.
Great talk, thank you so much. Any questions? I had one question on the, I wrote it down. Yes, so there was a slide where you had the different like the CFG stuff, and you had like the unconditional, the conditional from the image, and the conditional from the text. Did you find that like the norm from the unconditional was often smaller as well, or do you also scale that, or how does that work? Is that when that gets factored in?
Yeah, so I often found that just the image guidance vector has much higher norm, whereas all the other things have reasonable.
So it's the minimum of all three, though?
A minimum of just the text and image guidance vector.
Okay, cool, awesome.
I'm wondering, have you tried to reconstruct the objects from the customized the images generated by your methods, and then see if that is consistent or not?
So we don't, during inference, we don't know the camera pose.
Oh.
So I guess that's, yeah, because here we are, the only input to the model is just the images and the text prompt and not the target viewpoint. So if we knew the target viewpoint, we can then fine-tune NeRF to reconstruct 3D.
I think one potential way to do that is detect the objects with some SAM or something, and then run this callback to estimate the ones.
Oh, okay. Yeah, I don't think, maybe that's a good idea to do that.
Any final questions? All right, well, if not, let's thank our speaker again. And thanks to all of our speakers from the session. We're going to have a quick break for some more coffee, and we'll be back at 3:20.
Before the fourth and last session, let's reveal the present that we made for you, and let's run the diffusion on it. Let's see what we get. Oh wow! We got it, man. Okay, so before you leave, we prepared a map with the Graphics logo, so you're welcome to take one as a souvenir from the workshop. Okay.
Yeah, we wanted to pull together. Okay, I'll introduce you.
Alrighty, so yeah, now we have our fourth and final session of the day, titled Emerging Directions. And first up for that, we have Anand, who's a graduate student at the University of Toronto, who will be presenting subspace design for controllable physical simulation.
Oh, yeah, sure. Hello? Oh, I don't think it's on.
Hello.
Okay. Okay, thanks everybody for coming here. Thanks for inviting me, University of Chicago. I'm going to be talking about some of the work I've done throughout my PhD so far on subspace design for controllable physics simulation. I'm a third-year PhD student at the University of Toronto, advised by Professor Eitan Grinspan. And maybe my biggest weakness,
is that I spend way too much time on my phone. I don't know if you guys can relate. These are some of the apps that I spend a lot of time on. Recently, I got to deleting Instagram, which thankfully lets me spend way more time on Melon Maker. This is a really, really fun game that I can spend a lot of time on. It involves, the premise is very simple. You drop fruit onto other fruit, and if they're the same fruit, they combine into a larger fruit. And you keep making larger and larger fruit until you make a melon, and then if two melons touch, they disappear. What I really like about this game is that it makes use of a very, very simple physics simulation. This is a 2D rigid body simulation where the geometries are just circles. And it's very, very easy for me to interact and play with this game. I can make plans, I can choose where I'm going to make my next fruit appear just by selecting where I'm going to drop the fruit that I have. This is a very intuitive game for me. It makes me very satisfied. This kind of ease of interaction with physics simulations is not usually true in games. I don't know if you guys have ever played this game, Co-op. This is from 2008. The premise is also simple. You're trying to make this character run as far as possible, as far forward as possible. And the only things you can control are the angles of these hip joints and of these knee joints. By pressing Q, W, O, and P, you can make these angles larger or smaller. And this is just a slightly more complicated physics simulation. It's still a 2D rigid body simulation with boxes instead of circles, but this slight increase in complexity makes it almost impossible to control. I can't even make it past like 0.8 meters. And while this is all like fun or whatever, it hints at a deeper problem that, in general, the more complex your physics simulation is, the harder it is to control. Okay, come to think of it, what are ways that professionals interact with physics simulations in their day-to-day life? Well, they make use of a lot of physics simulation tools. These are unfortunately usually pretty hard to acquire in the first place. They can cost thousands of dollars for a yearly subscription, or they can be proprietary secrets that companies keep for themselves because it gives them a competitive advantage. That's disappointing. Of the free and available software that you do have available, you're usually met with an infinite array of sliders, buttons, and menus, which can be very intimidating and hard to work with. Some people even offer degrees that specialize in how to use each of these individual pieces of software. That's disappointing as well. Another way people interact with their physics simulation is through a software API. So you have to learn how to code in order to interact with a physics simulation. So much harder to use than Instagram. And on top of all of this, once you've become an expert at navigating all these tools, you go to set up your physics simulation. This is a simulation of a mammoth being blown by a hurricane, and it's super, super slow. And this is actually still simulating. We haven't even seen a single frame of this yet. Okay, the reason it's so slow is because there's a lot of vertices and a lot of tetrahedra in this mammoth model. But still, I spent a lot of time trying to set this up, and now I have to wait weeks to finish the simulation. Sad. Okay. This is really too bad because there's a lot of actual super serious cutting-edge technologies that are being held back by this kind of limitation. Engineers use physics simulations all the time to prototype large-scale infrastructure projects like bridges. Physics simulation, a physical model, is important for robotics applications if robotics is ever going to deliver on its promise of making a robot that can fold your own laundry. And there's also very interesting medical applications where the goal here is to model the human body, which is an extremely complex physical system. If you want to do stuff like virtual surgery or training or for educational purposes, you need to be able to have some sort of accurate physical model that's fast enough to interact with. Okay, and so my goal, I guess, is to try to flatten out this curve and make simulation as easy to control as possible. Okay? For artists, engineers, scientists alike. It should be as easy to use as any arbitrary social media app. Okay, and the core of the problem is that physics simulation forms an optimization problem. You might not know this, but every time step of a physics simulation, you're solving an optimization problem that looks like this, where you're minimizing this energy E for per vertex positions every single time step. And the problem here that becomes obvious is as you have more and more vertices, this optimization problem becomes larger and harder to solve and more difficult to control. Okay? And so to solve this problem, I usually end up using a methodology called subspace designs. It's old, it's been used before, but I think it's pretty underappreciated for all the things that it can do. The idea is very simple. You approximate your high-dimensional, difficult to work with, unruly space for your positions X with a low-dimensional, compact subspace where Z lives. And inside of this subspace, you can navigate with it, you can solve your physics inside of this subspace, and once you're satisfied with this, you can bring this back to the full space at the end at a final post-processing step. So at the end of the day, you use this nice subspace to solve all your physics, to do all your control and interaction, and bring it back to the full space once you're satisfied. It's a little bit like an encoder-decoder architecture, where the encoder goes from the full space to the subspace, and the decoder goes from the subspace to the full space. And of course, the thing that dictates this transformation from the reduced space to the full space is this matrix B. It basically defines what our subspace is. And what I'll show is that by thinking about how to design these subspaces, you can accelerate simulation, you can design better user interfaces for physical simulation, and you can also make feasible high-level control tasks for physics simulation. Okay? This brings us to our first contribution, skinning eigenmodes, which is a subspace that we propose to use to accelerate physics simulation. And it starts off with using smoothness as a prior. You say, I want to be able to capture deformations or simulations that are smooth at the very least. So you can ask the question, what are the smoothest function of my shape? And you get these smooth functions from an eigendecomposition on this matrix, Laplacian L. And the resulting eigenfunctions of that Laplacian matrix look like this. So these are the 8 smoothest function on this shape. We call these functions skinning eigenmodes because they come from this eigendecomposition, and they encode basically what our subspace for simulation will be. Specifically, each one of these skinning eigenmodes is associated with 12 different motions. So this skinning eigenmode is associated with 3 translations, 3 scales, and 6 shears. Basically, it's associated with the whole affine transformation, if you know anything about affine transformations. Okay, and so this link between the smooth scalar field and the affine transformation forms our subspace for simulation, B. And the specific structure of this subspace is such that you can represent motions that you couldn't with other subspace simulation techniques. For example, no matter how hard I yank on this poor alien's eyes, the ground truth simulation shows the eyes bending over backwards. A traditional subspace simulation technique will actually resist that rotation. But because our degrees of freedom are affine transformations, which span the space of rotations, you can reconstruct that rotational motion without a problem. Another cool feature about our subspace is that it can be made material aware, so it can handle heterogeneous material properties. Here's like this hard candy. You have this candy that's composed of stiff material in the middle and soft material apart, and you sort of twist it. Using subspaces that don't account for this property, for this material awareness, cannot accurately reconstruct that like crisp interface between the stiff and the soft material. So finally now, you have all the ingredients you need to make the simulation of this mammoth feasible. It's being blown by a hurricane. Okay? And we get this at 45 frames per second, which if you calculate is actually over 10,000 times faster than the naive method, the full space method. All because we chose to do this in a subspace. Okay? Okay, and so far I've described how to accelerate simulation, but I still haven't described how to interact with it. It sort of leaves us being able to observe this fast simulation, but not actually do anything to change it looking down from like this high window, not being able to change what you're seeing. Pretty sad. In order to add meaningful interactions, we're actually going to build off of a very popular technique that artists use to create any sort of 3D animation, and that's a control rig. So here, this is an animation that I made using a very simple rig, where the rig is parameterized by these two green bones. And I sort of pose these bones in space so that it looks like the fish is swimming forward. And that's very easy for even like an amateur like me to do, who's not a very talented artist. Of course, it looks kind of lifeless and not very compelling, and that's because it's missing all of the rich secondary effects that you would expect from an actual fish. In other words, it's missing some of the details you would get from a physics simulation. Okay, and so what we're going to see is that by bringing our fast physics simulation that I just described earlier into this mix with this control interface, we'd be able to control this fish with our rig while observing realistic physical simulation effects. And that leads us to our second contribution, what we call fast complementary dynamics, which is to say, we're going to show that by carefully changing and tweaking our subspace so that it can account for this rig space, we can achieve this natural agreement between our simulation and our control interface. Okay, so first we identify this rig space that the user is going to use to control this dragon. And we're going to specifically state that our subspace used for simulation be orthogonal to this rig space. So if you notice here, the rig controls more of the main body of this dragon, whereas the simulation subspace here, our skinning eigenmodes, are more focused on the tail and the wings. That way they're complementary to each other. Okay, and so with this complementary relationship between our simulation subspace and our rig space, we can get much more realistic behavior that is controllable at the same time. Okay, all just by making sure that our subspace satisfies this complementarity constraint. And now we can attach this physics simulation to any arbitrary rig control spaces, such as one defined by a face tracking app. And I can get, face tracking augmented with realistic secondary effects in real time. You can also interact with more than just one fish. I can interact with the whole aquarium, where all of these are different rig animations augmented with a physics simulation that I'm clicking on, and I'm clicking on individual fish and dragging them wherever I want while observing secondary effects. Okay? Finally, there are some limits of relying on a manual user interface for interaction. For example, one thing that I've wanted to do for a long time is to be able to make this mammoth walk. Instead of having a simulation of it just being blown around by a hurricane, I want to be able to state, how does this mammoth walk, and get an animation of it walking. In other words, I need a higher level control task. I need a higher level way to interface with my physics simulation. The best that I could do is attach these control points to the feet of this mammoth and tweak some parameters that'll move these control points sort of sinusoidally, and that gives a walk that looks like this. It took a very long time to set this up, and it's not something that I would want to do. And I especially wouldn't want to do this for a whole array of different characters if I wanted to organize, say, a race between all of these meshes. So in other words, now I'm looking for a new kind of control interface that could maybe answer a higher level control test that answers the question, how do each one of these meshes walk? And this brings us to our last contribution, is actuators a la mode methodology, where once again, by designing an appropriate subspace for motion, you can solve higher level control tasks for finding these locomotions of these characters. And the subspace here is going to look very similar. You're going to use a prior of energy efficiency. You're going to say, I think that animals walk in a way that conserves energy, in a way that is most energy efficient. And you can get these kinds of motions that are energy efficient through an eigendecomposition of this Hessian matrix, Hessian of the elastic energy. And this is what the eight most energy efficient motions of a seal are. So using these 8 energy efficient motions of the seal, I can then define this new actuation control strategy where I can specify which one of these actuations of this frog I'm going to be using and have a corresponding impact on the simulation, on the simulated version of the frog. And from then on, it becomes very, very simple for me to ask a control problem and an optimization algorithm. What are the actual control signals I need to give on the input to make my simulated frog walk, essentially. And here we see a result on a lizard, where a lizard figures out how to walk using its most energy efficient natural vibrations. Now, this does take 21 minutes to find using our current optimization scheme, which is a genetic algorithm. But this is a 50x speed up compared to the solution that does not use any subspaces at all. It also provides some more avenues for control of these locomotions. If you use different vibration modes, to define your control space, you can get sort of like a back and forth motion of this gorilla, where it's swinging its arms back and forth in order to locomote. But if you pick a control space that has that has these natural modes with limbs moving in synchronicity, you can get this more hopping-like behavior of the gorilla, where it's sort of like doing this weird locomotion like this. And because we haven't relied on any actual physical data, we can even make things that are fantastical walks, such as this couch. And finally, we can make all of our characters walk all at the same time and compete in a race that the gorilla clearly wins. So in conclusion, we found many ways to improve the game of co-op. But in actuality, we've shown that by designing just the right subspace, you can use this methodology to accelerate simulation, design better control interfaces for physics simulations, and solve higher level control tasks. I'd like to thank all of the collaborators that have worked on so far throughout each one of these projects and ask if there's any questions. Cool.
Any questions? Okay, I have one. So you showed that the eigenmodes of like the Laplacian, for example, correspond to different, let's say like control spaces, right? And I was wondering whether you could somehow extend that idea to representing different types of materials in your physical simulation, because you kind of showed like everyone with the same floppy motion.
Yeah.
I was just wondering if you could, if there's something there.
Right. So yeah, you could have. So some animals like a snail have a hard shell and a soft body, and so your eigenmodes should be able to account for that in the actual locomotion. Yes, totally. Instead of doing an eigenfunction on the Laplacian, you would do it on this elastic energy Hessian, which would be aware of the materials, and you would get what you're looking for, I think. Yeah. Yes, question?
I'm wondering if it's possible to apply this simulation on real-world videos. For example, you capture a real like walking dog or something, and you change his trajectory or movement.
Yeah, that would be really cool, and it was something that we were putting as a to-do, as a stretch goal to acquire real-world video and try to edit it so that you can change the trajectory of these things. It just takes a lot of like engineering effort. But I think once you have a 3D model of this dog, you should be able to redesign its locomotion patterns with this methodology. Thanks for the question. Cool.
All right, let's thank Anand one more time.
Thank you.
Next up, we have Chih-Hao Lin. Cool. So just give some brief background. Chih-Hao Lin is a current PhD student at the University of Illinois Urbana-Champaign. And he is going to be presenting on realistic and controllable weather simulation in real-world scenes. Oh yeah, always forget to.
Hi everyone, I'm Chih-Hao from UIUC, advised by Professor Shen Wang, and I'm very excited to talk about this topic today, realistic and controllable weather simulation in real-world in real-world scenes. So why is weather simulation important? First of all, extreme weather conditions fails the computer vision system. Imagine you turning on the full self-driving mode on Tesla in a very foggy day. And in this video, the car failed to detect the objects clearly and almost collide with the train. So we argue that the realistic weather simulation is essential for testing and improving computer vision system under this adversarial weather condition. And how is the weather created in movies or TV shows? The film industry often use elaborate setups like the water pipes, and other devices to simulate the rain, and also same for the snow. And these effects usually require very expensive equipment and are difficult to modify the results once it is filmed. So we ask, can we create a weather simulation system that is more affordable and controllable? So in our research, our goal is to simulate the weather that in videos that are realistic and also consistent over time, and it can be precisely controlled. So some previous methods like image editing, they added images with some generative models like gain and diffusion models. Like climate gain is targeted for flood simulation and also some fog simulation. And Intrinsic is a diffusion model to change the image according to text instruction. But their limitation is they cannot create consistent editing in the videos, and also they don't have precise control. And more recently, there are some methods use text condition video models to edit the input videos, like the token flow, fresco, a lot of similar works in this line. But they also have some limitation. For example, they still cannot create realistic weather conditions, like the raindrops or snowflakes in the videos, and also they do not have precise control. So this led us to the first work, Climate NeRF, Extreme Weather Synthesis in Neural Rhythms Field. This is a collaboration with some Professor Jiabin from the UMD, and also the first author is from Zhejiang University. So this is the overall pipeline. The input is multi-view images or videos with the camera poses, and the target effects, an example is snow. And we first built the NeRF or any neural construction from this input, and this recovers the rough, the approximate 3D scene representation for this input. And then we stylized the scene appearance with the input images, like the snowy images, to change some appearance to make it look more snowy. And then the most important part is that we insert weather-related entities or particles into the scene, and our ray tracer then merge the physical entities and the NeRF models by carefully accounting for the ray effects during the rendering. And then, well, we can finally produce realistic physical phenomena like flood and snow and fog. And this is some of our results. So this is a data set in text and tempo. So Climate NeRF is able to create a realistic flood. Let me replay this again. And snow and fog from these multi-view images and videos. And since we insert the physical entities or particles into the scene, so it is very controllable. We can control the density of the fog, the height of the flood, and also the density of the snow. We can also simulate the rising sea level in large-scale scenes
So in order to raise the general public awareness about the climate change. However, there are still some limitations. For example, climate NeRF performs simulation in the 3D space, so it relies on the high quality geometry. So if it is a sparse capture, for example, just a single image, this type of methods will just fail. We can see there's some artifacts here, and it is because that we cannot get very high quality geometry from the input images. And also, because we insert new particles into, or entities into the scene, so you cannot change the shading successfully. But during a very dense foggy day, the shadow on the ground should be removed, which, so the results we currently have do not make it super realistic. And also, current method do not, the climate NeRF does not simulate the dynamics like the raindrop or snowflake. So this led us to my next project, controllable weather synthesis and removal with the video diffusion models, where we target on the same problem of the weather simulation, but we take a different approach, where we leverage the video models to edit the videos directly without relying on 3D representation. So the weather synthesis model adds diverse weather effects to input videos with precise control. So for example, we get input videos on the top left corner, and we can synthesize the rainy day, the foggy day, and a snowy day. And we also have the raindrop and snowflakes in these videos. And it also works in video games. So this is the recording of the game called CSGO. And we can simulate these different effects, rainy, foggy, and snowy, without actually exercising the asset geometry. So we also target on weather removal, where we input the video with weather, which is foggy in this example. We can remove this fog and also generate the sun behind this fog that is not visible in the scene, and also recover its shading. And it also removes the heavy rain and puddles of the input videos, and turn the rainy videos into a sunny video. And the model also handles snowy videos, where it removes the snowflakes and recover the clear sky, and also the shading on the ground. So how do we do that? First, the input videos is encoded with pre-trained encoder from Stable Video Diffusion. And in the latent space, we inject some weather effects maps, like we want to simulate the cloud with intensity 0.6, snow 0.7, and snowflakes 0.7, and snow cover 0.8. And then during the iterative denoising step, we use the diffusion unit to remove the noise of the input. And then we get the latent representation of these output videos, and we decode with the pre-trained video decoder to get the final video with specified weather effects. And similarly, the input videos with weather can also be encoded and decoded. And we also specify the weather effects, and we can get the clean video without any weather effects. And by combining these two pipelines, or these two modules, we can we can first remove the original weather in the input videos and add new weather to create new videos. So in order to train this video model, we need data to optimize. So the first option we explore is to use a simulation engine, where we use Unreal Engine and some assets designed by artists. We collect sample camera trajectories in these scenes and control the weather parameters to create paired videos with ground truth weather strength labels. However, the number of assets is limited, So in order to increase the content diversity, we use generated images as a second data sources. We use a image generator. We first create paired text prompts that describe diverse scene contents and weather conditions. And here, for example, which is historic plaza in Rome, and we have another prompt that describes a snowy scene, a snowy version of it, which is the same description with covered in snow. And then we use text-to-image model, stable diffusion XL to generate and the strategy code prompt-to-prompt to generate the paired images while preserving most contents, but only change the weather conditions. And in order to enhance the data quality, we do very aggressive filtering to filter these paired images according to the alignment score. As a result, we can get very diverse paired images with only weather change, and this is our second data source. But these two data sources still have realism gaps to real videos. Therefore, we leverage the real-world videos as a third data source. We first download YouTube videos such as snow walk, rain walk in Chicago, for example, and then we remove the weather in the input videos without pre-trained weather removal model to get a video without any weather. And then now we have paired videos. Then we still need the strength label for the weather effects. Then we leverage the VLM model to help us label the strengths of the weather, and by providing some examples in the simulation data as a reference. So now we have three different sources of this weather data. And each of them has its distinct advantage. For example, the simulation data has the most precise control over weather parameters and the camera trajectories. The generation data has the most diverse contents. And real videos is the most realistic data sources, and Weather Weaver is trained on this data and try to leverage these great properties from all these three data sources. So after training on this data, our model is able to precisely control the weather effects. So here we show that by increasing the cloud coverage, the cloud pattern in the sky increase, and the overall shading of the building or the general scene becomes darker, and also the harsh shadows on the ground is removed. And we can control the fog density, where the fog starts to blurring the distant scene, indicating that the model implicitly utilizes the depth information of in this video. And the snow is accumulated on scene surfaces such as the road and rooftop, which is learned from the data without requiring 3D geometry. And the reflection in the puddle is synthesized without expensive ray tracing in 3D. We can take a look at here, the reflection of the tire is simulated. So with this controllability of the model, we can create an application called Weather Time Machine, where we can simulate how weather change during a rainy day. Here, the cloud increase, start raining, and the puddle emerge, and the rain stops, and the cloud disappears, but the puddle is still on the ground. So we can simulate this type of effects, which we cannot capture in the real world environment. And this is for the snowy day. The cloud increase, start snowing, snow accumulated on the ground, snow stop, snowflake stops, and becomes sunny again. But the snow on the ground is still there. So here are some qualitative comparison of the weather synthesis. In this fog synthesis, this is our model. And we can see that we are not only simulate realistic fog, and it also removes the harsh shadows on the ground that previous methods failed to. And for the rainy synthesis, we simulate the rain dynamics, the reflection on the road, and also the overall shading of the structure. And this is for the snow simulation. And we also compare with the previous, the work I introduced earlier, climate NeRF. And we can see that we not only have the dynamics of snowflakes, but we also have the better snow simulation on the statue. Because the model learns from, just performs the simulation in the video, so it does not require very accurate 3D geometry. And this is some qualitative comparison of the weather removal. The input video is very foggy. Our model not only removes the fog, recover the blue sky, and also hallucinate the shading of the tree. Makes it looks sunny. And this is another example I also showed earlier, where previous methods like histoformer and weather diffusion are designed for weather removal, but still they cannot, because they are trained on synthetic pattern of the weather, so they cannot generalize to these real-world videos. And this is the snow removal. So this is some images of the video I showed earlier, where for the foggy input, I run the grounding SEM to detect the objects. And the bottom one is that after I remove the fog in the video and then run this the perception model again, and the model now can more accurately detect the objects in the scene. So in supporting our argument that the weather simulation and weather removal is essential for testing and improving the performance. So in order to validate, we conduct the user study to validate that our methods outperforms all these baselines. And this is a summary. The goal is to create a realistic, consistent, and controllable weather simulation. And in the first work, climate NeRF, we use simulation in 3D. And the second work, Weather Weaver, we adopt a different approach, which is use the video diffusion model and customized data strategy. Thank you, and I'm ready to take any questions. Yeah.
Because of time, we have probably time for one quick question, if anyone has it. Yeah, last one.
I was wondering how you trained the weather removal method. If you're using it directly on real world, do you just train it with Unreal Engine?
No. So for weather removal model, we actually use two different data sources. So we have the paired videos in the Unreal Engine and also the generated images in the from this.
And that worked well enough that it was good for.
Yes, they already generalized to real world videos.
Thanks.
Thank you.
All right, let's thank Xiao one more time. Yeah, so next up we have Daniel River. He is an assistant professor of practice at the University of Notre Dame, and he'll be presenting maximizing parallelization for dynamics in interactive textures. And these clickers are over in slide 6.
Cool. Well, thank you all for having me. Very excited about this new workshop that is occurring, gathering everyone from the Great Lakes area. So thanks again. So I'm a little bit different in terms of my research topics, mostly because I'm a professor of practice. This is because of industry experience, a return to academia because I like research topics. What I'll be discussing today is an undergraduate research project that is ongoing still. The big thing about focusing on game engines and simulation systems, that's the name of my lab, because I focus on video games, is it's the largest entertainment industry in the world, but there's a lot of risk aversion when it comes to actually working on new R&D topics. But the funny thing in terms of innovation is it actually comes about from indie titles, because they aren't investing tens to hundreds of millions in a project. So you can see some very novel things come out, but you can also see some problematic issues. And we'll talk about one situation that we're tackling that was faced by a popular indie game. One of the big motivations in working in the space of game engines is they're pretty complicated, and you can't hog resources. You need everything to work as promptly and quickly as possible. What I have here is just a diagram from one of my classes where I teach students how to build a video game, start to finish. And I keep on adding things to this, and they keep on gasping and freaking out, but they're doing good with it. So, but the big thing is you have to share all of your system resources. You have to share performance. So in terms of lab projects, going to some concepts of simulations, the particular project we're going to be talking about today deals with particle simulation in 2D textures, specifically 3D particle simulation. What I have going over here on the left is two identical simulations of n-gons that are just being pushed into a space, just falling down. It's a stacking problem. And this is using a traditional constraint solver. We have a Lagrangian solver on the top, and then we have a Verlet approach on the bottom. You can see the very different outcomes based on the computational models that we use to actually simulate physics. So that's just something to keep in mind here. But for the problem space dealing with dynamics and textures, we don't necessarily want to do this type of constraint solver problem. There's really no need to if we have this uniform grid and we know where everything can be at any point in time. Okay, so the problem actually extends from a traditional utility that's used in video games, which is height displacement maps. If we have a uniform grid for a mesh structure, we can define a grayscale image that says, okay, these vertices translate this much in the vertical direction. This has been repurposed in contemporary games just because of better general compute, better bandwidth with the GPU, where you can effectively do things like display snow or mud, these continuous types of structures. So effectively, if I have a terrain and I define its height values, all of these vertices to begin at a certain state, I can just draw into a texture, so this would be like a character walking around in the game world, and you can see in real time the actual terrain displace. This is as opposed to doing something like decals where we just put information in a 2D space as well. A funny thing exists with this though, kind of a curiosity, is why are we only working in grayscale spaces? And this isn't exactly always the case, but we have additional color channels that are available to us where we could supply more information into what it is we want to do with these displacements. A very simple example is if I just wanted to do some real-time procedural grass generation with the geometry shader, I could use the additional color channels to represent in the tangent space which way the grass blades would fold if I were to trample them. So we can kind of see this crudely happening with these grass blades folding in different directions. But more interesting and a harder problem is, can we add to the displacement of mud, the displacement of snow? And can we deal with harder problems, specifically things that are not so continuous, things that don't have these cohesion properties? So disparate things like sand particles. So an extreme scenario to consider here, going back to the snow and mud, is if we had solid particles, rigid bodies that need to interact with each other, that aren't going to be glued together. We can't just press down the surface, we want to actually simulate the particles moving. So the conventional approach, if we were to do this in a real-time setting, kinematic update, we just move all the objects. We don't want them to care about any other objects in the configuration space. Find violations, set up constraints, run some iterative solver to be able to resolve those violations. Again, we don't necessarily need this full conventional approach, this constraint solver, if we just have a uniform grid and could potentially deterministically say that particle needs to move here or there. In conventional games, that is already the case. If you've all played Mario, you all know that like these older pixel art games would do pixel perfect detection, collision detection, first doing an update on a horizontal pass and then a vertical. The challenge, though, is how well can we parallelize this? Okay. So when it comes to parallelizing this, let's say that if we were to simulate something like snow and mud, we actually have a set of particles that are stacked within this tangent space. So we can use one of our color channels, just like we did before, for a height map. And we can say this is how many particles exist here. Then we just need to figure out what are we going to do with the other color channels so that we can figure out in parallel how to move all of these in unison, or as close to unison as possible. And a key premise to consider here is if we're considering this mud scenario where a character is walking around, they're only interacting with the top layer at any given point. So we don't need to worry about the particles underneath, we just need to track the top layer. Okay. So, indie game that did this type of extreme pixelized simulation, Notre. GDC, they did a presentation on how they actually update their game in parallel. It's a game where all of the particles are just pixels and all of them can be destroyed and moved. One of their statements was effectively, if you use the same buffer, which is something you ideally want to do in these types of real-time constraint situations, just because you want to minimize memory footprints, if two threads are trying to update the same pixel, all hell breaks loose. So their solution was basically a checkerboard pattern where they update states over here in serial, and then eventually get the states in between. Very simply, why this is a hard problem, at least from that perspective, from the conventional particle motion perspective. If we weren't doing any time flag locks or anything, we can't guarantee the coherency of the information we've modified in memory, so that's not too crazy. But if we applied atomic rules, say I have some particle I, it wants to move to location P sub j, but there's competition with some P sub k, I could use atomicity to maximize the hardware level locking mechanism between the motion of these particles, and one of them would win if only one of them was allowed to go to P sub j. Okay, so that's beneficial. I could use hardware level atomics to try to help me solve this problem. However, there's kind of this back error that's going to propagate, and so this still does not end up being an ideal solution to maximize the motion of particles in this uniform grid. So the problem is, if I have some P sub I minus 1 that's trying to move to P sub I, and it can, if and only if, P sub I move to P sub j, and that was allowed, the order in which those executions occurred determined whether or not they all moved, or if one was blocked out and only P sub I moved. So this just involves a fairly quick paradigm shift. Instead of considering the traditional perspective from a kinematics means of motion, instead of just saying, where am I trying to go? Can I move there? Is there a violation that I need to adhere to? We can change this into more of a kernel space where the thing we update in parallel is actually the P sub j, the location things we're trying to move to. Instead of saying, where do I want to move to? I can say, who's trying to move to my location? If we define the computational rules of this centroid, then we can guarantee that particles are not going to be competing for the space from their own independent perspectives. It's all regulated by the cell that they're all trying to move to. Okay. So under this sort of rule structure where we have this P sub I and its height value, so just this is the basic rule. If I have some height value and the height value of the location I'm trying to move to is less than or equal to me, particle's allowed to move. But as long as we do the update from the location where information is trying to move to, we can guarantee that if everything was moving in the same direction, we've maximized potential parallelism here. This works pretty well and is funny because under traditional perspectives, we might want to deploy something like wavefront parallelization, where we take the entire data set and transform it based on executing dependencies, maximizing the number of dependent things that need to happen before everything else. So this is a very simple perspective shift. We don't need atomic operations in this perspective either. We can use our 4 color channels to be able to figure out all of this unison motion. Effectively, I can have one channel used for a height value. I can have one, so I split this up because it's a kernel problem, so we don't have to look at all 9 cells around where we're trying to converge to. We can do things like we do for Gaussian blur. We can do a two-step process, a horizontal update, a vertical update. So if I am only considering motion along one axis first, I update that state. If a particle is trying to move to me, I can use one color channel to modify their value and say your height will actually decrement in the next step. I can modify my own value to say that my height will increment in the next step. And then between moving to the next vertical pass, we go ahead and update the stack, the height values of these particles. This is just a mock demo that I'm releasing for undergrads so that they can play around with a fairly simple interactive computer graphics representation here of this particle simulation. And they can also just play with parameters, changing numbers of threads, whether it's running CPU or GPU. The benefit to this model is it fits a data parallelism pattern either for the architecture of CPU or for the SIMD-MEMD sort of approach on a GPU, because there's not much going on in terms of what instructions are actually required to even move these things. Now, there's quite a bit more actually going on. This entire presentation is just to talk about that computational model. Some of my undergraduate researchers are here right now. They're focusing on what are the applications that this sort of problem can go into. We already described the idea of maybe moving sand around, having characters actually displace particles, as opposed to leaving little decal footprints. This includes simulating dilatancy, the effect of sand getting a little bit taller, and appearing dry momentarily, because that's something that's deficient in video games. Water droplets on surfaces, you've already seen some degree of this type of simulation probably in racing games. The nice thing is we can generalize this approach to a very low footprint in terms of the execution cost and the amount of memory needed. You can just apply this for a bunch of different techniques within a game. We have already working to some degree impulse-driven decals, because it doesn't matter actually how we want to move these particles or what information we apply to them to move them. We can arbitrarily add new particles. We can have particles be removed as they're evaporating also in this image. And we can apply external forces arbitrarily. Thank you, and I'm open to any questions.
Thank you, Daniel. Any questions? Yeah, I want to ask about, I guess, the extension of this framework into, like you said, about regarding like more sophisticated, maybe like sophisticated particle simulation.
Yeah.
This may be dumb/naive, but I was wondering whether you would encounter, because like I guess in particle simulation you have this like sort of dynamic system where there's potentially long-ranging physical interactions between like particles depending on the physics that you're trying to simulate. I was wondering how that would play with your framework in terms of synchronicity issues, or like sort of that thread locking you were talking about earlier in the presentation.
Well, so I can't really imagine too many detrimental synchronization issues when we're looking for physical plausibility first and foremost. This type of interactive simulation doesn't need to be truly accurate. One of the reasons we don't need the full-blown constraint solver is we're not looking for a proper simulation, which again, if we were even doing that, we'd have to be concerned with the number of iterations, what's our numerical error as we're converging to a solution. Right. So in terms of sustained interaction, something like applying a footprint as a series of impulses into this texture space, we can control that pretty well by saying how much how deep into the texture does it actually affect information? Yeah, so the stability is funny because you're not simulating the stability, you're just assuring that these particles are going to remain stacked. So it's not a conventional rigid body problem.
I see.
Yes.
Okay, thank you.
Thanks.
All right, let's thank Daniel one more time. All right, last but not least, we have Professor Matthew Walter from the Toyota Technological Institute of Chicago. He'll be presenting SPLART, articulation estimation and part level reconstruction with 3D Gaussian scaling.
Great. Great, thanks for having me. Okay, let's see. Yeah, it's not the most catchy name, Splunk. It's better than the alternative. So this is joint work with some folks at TRI, which is the Toyota Research Institute, which is completely unrelated from GTIC, despite having the Toyota in the name. And the work, all the work really has been done by Chenxi here, who is finishing up hopefully soon. He already started working, so yeah, I hope he's finishing up soon. And folks at TRI and myself. But really, Chenxi gets all the credit. So a little bit about TTI. I imagine most people here are familiar with it, but I know some people from out of town. So TTI, or Toyota Technological Institute in Chicago, is a pretty unique place, at least in the US academic scene. We're a university with one department that's computer science, and we are and just a graduate program, so just PhDs, and we are very small. 45 students, 12 tenure track faculty and 7 research track faculty. And the picture, we are in my dad, but I think we're right around here right now. GTIC is right down here, so we're really close. It's a pretty awesome place. And just another plug, for those of you who are interested in robotics, on June 2nd and 3rd, we're having our Midwest Robotics Workshop at TTIC. So if you're from out of town, please come back. If you're in town, please come to the workshop. It's mwrw.org. Okay, so this talk is focused on learning articulated objects, and this is something that I've been interested in for a long time. I'm a roboticist. I want to develop robots that can be useful in our homes and workplaces, and our homes and workplaces are full of articulated objects, in our kitchens, doors, drawers, et cetera, et cetera. And I would like robots to be able to reliably interact with these objects. And historically, the way the robots have done this is that they have a hard-coded policy for interacting with these objects that is painstakingly, requires extensive supervision. And so this is something that, again, I've been working on for a long time. We'll see in a bit in a slide, a picture of me from 10 plus years ago. But we see this right in our, if we ever have humanoids joining our home, maybe they can get us something from the refrigerator. We see this also in applications outside robotics, so augmented reality. If you're working on something, you can have these overlays telling you how to interact with an object. Something that's become popular of late is, robotics is data scarce compared to other domains. We like to do, you maybe have heard of the sim to real gap. We'd like to go the other way around. So take the real world and embed it in a high fidelity simulator. So we can collect far more data than we could in the physical world. And so you can imagine, again, bringing articulated objects into a simulator, and you want them to be high enough fidelity such that the policy you train in simulation generalizes to the real world. This is a picture of me, 12 years ago, doing this again for robots using high amounts of supervision. So in this case, ground truth depth and SIFT image feature tracking. I would manipulate the refrigerator in this case, and then I would the robot would build up a model of how that object works, and then we can use that to manipulate the object. Okay. We're interested in doing this with less supervision. We want to do this in a self-supervised way. So in particular, what we want is we have some articulated object, and this articulated object has 2 states. So in this case, it's a drawer, and the drawer is closed in one state, and then it's open in the other. And what we're going to assume we have as input is poised images of the object in one state, so a bunch of RGB images, no depth, and then poised images of the object in the other state. And from this, we'd like to be able to detect which are the static parts and which are the mobile parts, and what's the kinematic model that describes that motion from these 2 sets of images. Okay, so that's what we're doing, and we're going to do this using 3D-GS or 3D Gaussian splatting. And this is just a pictorial showing what we like to be able to estimate. So standard 3D-GS parameters, plus this mobility label. What is static, what is dynamic? And then from that now we can, unlike other methods that exist, we can, again, because we have 3D-GS, we can render novel views of the object, but we can also do this at novel states. So now I can synthesize views of this object at states I've never seen from novel views. That's the goal. So the self-supervised, image-based, category-agnostic framework for reconstructing articulated objects. And again, many other people beyond me have done this, and they've done a better job than I have. These are just a small sampling of the paper. Some of our earlier work, again, 2014. We did this with language in 2017. There are a number of other papers that have done this. Most of the methods out there require extensive supervision, such as ground truth depth, require significant annotation, labeling, and are category specific. There are some exceptions. So there's Paris, which is a paper by Liu and others, ICCV, that does this similarly in a self-supervised way using NeRF. And we'll compare to them in a bit. So the way that we work is basically we have 3 stages to this method. The first is just taking the object at 2 states here. So this is a bit case. Partially open versus fully open. We just generate a 3D GS of each object. So we have proposed images. We generate a 3D Gaussian splat of each object, minimizing photometric loss. Everything's standard here in terms of 3D GS. The next step we want to do is we want to estimate which part is mobile and which part is static. So I should say that in our objects, there are 2 parts and 1 degree of freedom right now. We're working on extensions to multiple degrees of freedom. And the basic idea that we have here is that, so we have 2 Gaussian splats of the object, one in the closed state, one in the open state. And the idea is that, again, we have a bunch of Gaussians. We'd like to assign a label to each one. Are you on the static part of the object or the mobile part of the object? And the intuition is Gaussians that are on the static part should be consistent between the 2 Gaussian splats. So if the part is static, it should look the same in both Gaussian splats. And that's basically what we're saying here. So we have this mobility label that's 1 when it's mobile, 0 when it's static. So these are the 2 static parts. And these arrows are showing that for the Gaussians that are labeled as static, it should allow us to reconstruct that part of the object in both Gaussian splats. That's basically the idea in a nutshell. So that's all this equation is basically saying, is that we're going to do exactly that. We're going to assign a mobility label such that it allows us to that it gives us the best reconstruction of the 2 Gaussian splats. Right. So that gives us this mobility label. It's actually a continuous label between 0 and 1. And the details are in the paper, though the paper's not out yet, but it will be out in a couple days, hopefully. So that's the first part, is just estimating the mobility part. We actually have a geometric component to our objective as well, using a weighted chamfer distance, where the weight is a function of the mobility label. So we can now minimize this geometric distance here over the mobility label, this m, and then we do that through the weights on the chamfer distance. That tends to be a little bit noisy, so we use that to initialize our mobility labels, and then we use a photometric loss to refine that. The next step is sort of similar. Now, or I should say, the next step is to estimate the articulation model, so the SE3 transformation that describes the motion of the object. And the intuition is sort of the same. So just like I said before, the idea that the static part of the object should persist between 2 Gaussians. Now, the idea is that if I look at the mobile part, subject to that transformation, should be consistent between the 2 Gaussian splats. So if I take the mobile part here, which is this part here, so this M is sort of like a binary label indicating motion. If I apply the transformation to it, if that transformation is correct, it should allow me to reconstruct the other Gaussian splat. So that's the idea. So, and we do this through a combination. Again, I won't go too much into the details, but a combination of both a photometric loss and a geometric loss to improve this. And again, with the multi-stage approach, using a geometric objective to get an initial coarse estimation, and then a photometric loss to get to refine that. Okay, so we evaluate this on, there's sort of what's become a standard benchmark in this area, which is based on PartNet mobility. So the Paris paper from a couple years ago created a data set based on PartNet mobility for articulation estimation. So we look at that, and then we have our own extension of it for various reasons. They didn't have segmentation labels in the the original PartNet mobility-based data set, so we have our own. We look at more challenging objects that were left out of that, and so we call this SPLART PMS. The other one, and the other one's Paris PMS. And we also look at this on real-world objects. So we take a phone and collect Gaussian splats of articulated objects. We compare against Paris and this other more recent method, DTA, which does require ground truth depth, but just to get a sense of how do we compare. And we look at how accurate is the articulation model, how accurate is the geometric model itself, so reconstructing the mesh, how accurately can we reconstruct the mesh, and then success rate, which is basically just a threshold that as long as the accuracy is above some amount or the error is below some amount, we denote it as success. And again, don't worry too much about the numbers, but again, this is a comparison between SPLART for revolute, or a rotational degree of freedom objects, prismatic, and then just overall. And we find that our method performs far better than Paris across all metrics, and does, in many cases, does better than DTA, despite the fact that DTA has ground truth depth. So both in terms of success rate, geometric reconstruction, so that's with the chamfer distance here. Again, in some cases, DTA does better, so your lower is better, but we're comparable despite not having ground truth depth. But in terms of the articulation accuracy, we're much better than the others. So our model is more accurate. Also, as I said, we will look at, as with Gaussian splatting and NeRF-based methods, how accurate is the view synthesis. So we look at this in terms of standard metrics, so PSNR, MAE, and MIOU. And we find again that our method performs quite well in terms of novel view synthesis, despite again not having ground truth depth. It's just some visualization. Oops. This is on the Paris PMS data set. It's not playing. I have others. Okay, so this is just some rendering showing the part segment, the objects here, novel view synthesis, and novel articulation states. So you can see the drawers opening. We only saw it all the way open and all the way closed, but we can synthesize intermediate articulation states. And for objects with fairly complex articulation and complex models, so this is the blade, might be difficult to see, but this blade of this knife, so it performs, surprisingly well. Some other qualitative results. Let's see. Again, these other objects here comparing to Paris. So it might be difficult to tell at this scale, but yeah, you can see here there are some artifacts with the blade here that we have in Paris that we don't have. Artifacts with the stapler here that Paris has. The scissors that are just not apparent in ours. Same thing with the USB stick. Because again, they can't simulate novel articulation states. Paris cannot. They do novel views, but not novel articulation states. Let's see here. Again, this is what we looked at before. Let's see if this lets me. There we go. So this is our data set, which is again based on part net mobility, some more challenging objects. And it's not perfect. You can see this clock. Obviously, it gets it wrong. And that's actually because it's not clear what is it. I'm happy to talk about it later, but it's not clear based upon seeing the hand at one time versus another. It's not clear. There's no indication that it should rotate. There's no information that it should rotate. It's equally valid that just the hand translates on the screen. The globe, just let that play again, is similar here. There's this inherent ambiguity in these objects. Okay. So let's see. Here we go. And it's a real world. No. Here we go. Some real world objects that we collected. Again, we just set it on a table, take a cell phone and move it around the object in two different states, and then we can reconstruct this object. In this case, this object has multiple degrees of freedom, but in our case, they're actually treated as separate. So separate instances of SPLART. Really, we'd like to be able to do this with one model. Okay. Let's see. And again, I have more qualitative results, but I think for the sake of time and for your sake, I'll skip through this. You can see maybe this one I'll go through here. So this is showing now the object, the static, what we determined as being static and what we determined as being dynamic. And it's not perfect. You can see with the scissors, like this part here, there is some ambiguity there. And then now, as I said, you saw earlier, we can do this novel view and novel articulation state synthesis. This object. And again, there are several examples like this USB, but again, for your sake, I'll skip through this. Okay, so just to summarize, we and really this is, as I said, Chenxi and folks at TRI propose this novel self-supervised category agnostic method for estimating articulation states of objects. So the part labels and then the SE3 transformation that describes the articulation. We do this by augmenting 3D Gaussian splatting with a differential mobility term that lets us, again, assign these labels. The mobility label that results in a most consistent reconstruction of the 3DGS at both states. This method is fast, so we can do this in real time. It's state-of-the-art results on standard benchmarks without ground truth methods. The limitation, it's not perfect. When there's ambiguity, it's not able to handle it. Right now, as I said, it's limited to objects with 1 degree of freedom, but plenty of objects in our homes have more than 1 degree of freedom, so that's currently something we're working on. The code and paper should be out, hopefully very soon. And when it does, it will be on our webpage. But yeah, happy to take any questions.
Questions?
Hi, thank you. Really cool results. What do you think is the thing limiting you from doing multiple degrees of freedoms with like 2 axes, basically?
Yeah, so I think that's a good question. So I think that one way of doing this is with a hierarchical approach. So I don't think there's anything fundamentally limiting it. I mean, ideally, so right now ours is a little bit more pipeline than I would like, and I think there's a pipeline extension of it where we have this hierarchy. But I'd like a more ground up, or a better approach to doing multi-degree of freedom. We can do it if we know the number of degrees of freedom. I think that would be pretty straightforward, but I'd like to relax that assumption. But no fundamental limit.
Is there any thought about I know SE3 might be like a simple assumption to start off with, but more like object deformations that aren't so simply represented?
Yeah, that's a good question. So people have looked at this in articulation modeling. I think most objects that I've been looking at are sufficiently captured by SE3 transformations, but there are certainly plenty that are not. We've done some work in soft robotics. So for example, some deformables, which are inherently not captured by any SE3 transformation. I think that's far more challenging, but is very important, especially if you're doing soft robots or deformable materials. It's important. And people have looked at that. So David Held at CMU has done a lot of good work on modeling soft objects.
I'll ask one last final question. I'm kind of curious about whether you've attempted or you've thought about modeling articulation limits, in the sense that currently your framework would basically, if you had simulated the tape measure and you just kept pulling it out, you'd probably just get infinite.
Yeah. So right now ours sort of is the limits come from the 2 sets of states that it sees.
Okay.
So that's how it estimates the limits. But you can imagine if you ignored that, yes, it wouldn't fully simulate the tape coming out.
Yeah.
If you had some prior over the object, so if you did this in a not category agnostic way, you could incorporate some information over the limits. But right now in this work and in the previous work that I've done, it's when I'm opening the refrigerator, same thing. We just look at the limit, the extremes of the motion that it's seen, and that defines the limit of the articulation.
Gotcha. All right.
Thank you.
Let's give it up for Matthew Walker.
Okay, great. So let's wrap up quickly. I want to thank all of you for attending. I had a great time. I hope you did as well. I want to thank again all the speakers. The talks were very interesting and very exciting. I want to thank all the organizers again, Richard, Dale, Naman, Brian that should have been here, and Rana for their help for planning the workshop and for their help during the day. I would like to thank again the University of Chicago for supporting this workshop. And some special thanks to Ashland from the audiovisual team for helping with the recordings. For Miranda, thanks to Miranda for taking photos during the event, which we'll share with you. And a special thanks to Christine from the business assistant that helped a lot in coordinating the catering, the breakfast, the lunch, the coffee breaks, and handling the printed materials, and for her help throughout the day. Please let us know your thoughts so that we can improve. I will share a poll later today so that you can tell us what went well and what could be improved for the next edition of the workshop. Regarding the mug, I understand that several of the people have had to left already, so if you can take a mug for your colleagues, that would be very appreciated. So we have enough, so go ahead and take for...
They're over there.
Yeah, okay. The mugs are over there at the table there. So do not forget to take one for yourself and for your friends. And now I encourage you to, although it's a bit late, I encourage you to join us to a tour at the beautiful campus of the University of Chicago. We will see beautiful places like special the Mansetto Library, which is a dome-shaped library, very unique structure. We'll see Roby House, which is a house museum. We'll see a memorial, the Memorial Rockefeller Chapel, and Botany Pond, and much more very nice and beautiful places. So you're very welcome to join the tour. And I hope to. This was the 2025 edition of the Great Lakes Graphics Workshop. And we would be very happy to see you again next year at the Great Lake Graphics 2026. Thank you so much. Let's reconvene here, let's say in 5 minutes, at 5 to 10 minutes. And here is the entrance, and then we'll go